Okay, so first of all, good morning and welcome to Trieste. My name is Rosario Fazio. I'm here at ICTP and together with Massimo Inguscio, Sandro Stringari, Roberta Sessoli, Marc Mesar and Luciano Maiani, we organized this conference on, it's a joint ICTP-Lincei conference on quantum physics from foundations to emerging technologies. This conference was selected and supported as a global event for the United Nations 2025 Years of Quantum Science and Technologies. I would also like to acknowledge the support of Fondazione Compagnia di San Paolo, ICAM, Institut Français. They all support this conference and we thank them. I think we will hear a lot about quantum, but I will not say anything about the year of quantum science and technologies, and I just invite Professor Atish Dabholkar, Director of ICTP, on stage, please.
So good morning and welcome everybody to the Abdus Salam International Center for Theoretical Physics. All of you are very familiar with ICTP, so I will not dwell upon it. We are very happy to be hosting this prestigious conference in collaboration with Accademia dei Lincei and to have this very distinguished lineup of speakers. As Saro mentioned, this is one of the 6 global events that are taking place around the world during the International Year of the Quantum. So, as you know, 2025 is 100 years since the new quantum theory was unveiled. And it was proclaimed by the United Nations as the International Year of the Quantum. And in fact, ICTP was a founding member, one of the first proponents 3 years ago, maybe. And also my colleague here, Professor Rosario Fazio, is the co-chair of the International Year of the Quantum. And it is, the lead organization is UNESCO. And so we are very happy as ourselves, ICTP as a UN organization, to be hosting this very excellent conference. So it was 100 years ago that Heisenberg wrote this magical paper which ushered in the new quantum theory. And it's actually interesting to look at that paper. It's about a simple toy model of anharmonic oscillator, one-dimensional anharmonic oscillator, in which Heisenberg formulated his scheme for computing the quantum energy states. And it's really extraordinary that that sort of was the essential seed for the very rich harvest of all the amazing technological and scientific revolutions that followed in the last 100 years. So we are, in fact, it's actually interesting that Heisenberg's 1932 citation to his Nobel Prize is, of course, for the creation of quantum mechanics. But then it says that, which among other things led to the discovery of the allotropic form of hydrogen. And if you look back, it looks like a very curiously particular and contrived application to single out as the most important outcome of quantum mechanics. Because as we have seen since then, we are now at a point where we are manipulating single atoms and single photons, and also the more subtler aspect of quantum mechanics having to do with quantum information, I mean, quantum entanglement and superposition. So I'm really looking forward to, it's a wonderful set of lectures, and I'm looking forward to exciting 3 days. So welcome.
Thank you, Atish. So I would like to invite Professor Massimo Inguscio on behalf of Accademia dei Lincei to say a few words.
So let's start. I give you the greetings of the president of the Accademia dei Lincei. And yesterday we started our adventure for the quantum year of UNESCO in Rome, in the headquarters, essentially having an event for students of the high school, of schools, and just to advertise all the beauty and the dreams which are opened by, and the practical effect of quantum mechanics. Then we, together with Sandro, Saro, Mark Medà, and Luciano Maiani and Roberta Sessoli, as a committee for this conference, we wanted to ask ICTP to have the conference in this location, because for all of us, the ICTP has always been a sort of a bridge between different cultures. All of us came here maybe 30 or 40 years ago, or the youngest, no, but to learn about science, everywhere. So it was the perfect location, and indeed we thank ICTP, friends from the ICTP for hosting and reinforcing also this conference. You know that all the protagonists, practically all the protagonists of the 1 century-old adventure of quantum physics have been members of the Accademia dei Lincei, and including a few of those who will talk today. So we look forward a very interesting conference.
Okay, now I invite Assessor Alessia Rosolen, representing Friuli Venezia Giulia region.
Good morning to everyone. Today I will tell you something you know better than me, but I hope I will tell you something that you don't know about our region. First of all, my thanks to the director of the ICTP and to all ICTP and to Accademia dei Lincei for the invitation to the opening ceremony of today. A warm greeting to the many participants present today at the opening ceremony. Today, research and the application of research results in the field of quantum physics constitute one of the most advanced and strategic frontiers of scientific knowledge. Its application, from quantum computers to quantum communication, are destined to radically transform the production system and the industrial world. In particular, just think of security issues and how quantum technologies complement key technologies such as artificial intelligence. The proclamation by the United Nations of the International Year of Quantum Science and Technology on the occasion of the centenary of the birth of quantum mechanics is a confirmation of just how central this field is to sustainable development and innovation worldwide. In an increasingly competitive environment, investing in quantum research is not only a scientific choice, but also a geopolitical one, with significant economic spin-offs in the medium to longer term. In this scenario, Italy has chosen to invest decisively. Also, ICTP, University of Trieste, SISA, CNR-IOM are in this important project, but I think now I tell you what region is doing. Our region is firmly committed to supporting projects and initiatives related to quantum physics. It strongly supports programs that enhance the skills present in the scientific community in our region in order to attract talent and investment. Some examples. The University of Trieste and the University of Udine are now united by a quantum connection running on fiber optics, thanks to the Quantum FVG project financed by the region. The first step is in an infrastructure that aims to become a reference model. The region has also financed the project for the construction, always in Regione Friuli Venezia Giulia, of a permanent fiber optic infrastructure for secure communication by means of quantum technology with uses in maritime, port, and backport logistics called EQIP-FVG. Q3 is the free space quantum communication projects towards satellite quantum communication developed by the University of Trieste and financed by the region. The objective of the Q3 project is the realization of a free space connection in air for the secure exchanges of keys generated with quantum technology, stressing the collective commitment to develop more and more expertise in the subject, whatever the destination of that expertise. I close my speech with a call for collaboration. Global challenges require collective responses. Let us work together, institutions, scientists, companies, to transform knowledge into shared prosperity. Thank you for your attention. I beg pardon for my English.
So last but not least, I invite Professor Marc Mézard, Chairman of the Scientific Council of ICTP. Marc.
Thank you. It's great to be here to celebrate this anniversary of quantum mechanics. It's probably the most extraordinary and astonishing discovery of all times. And I can say it, I think Massimo mentioned the words beauty and dream, and I will ask questions. And with these three words, I can characterize the reactions of my students every year when I teach them as freshmen. They are exposed to quantum mechanics and start to teach to them, and beauty, dream, and questions. This is the reaction, and this is extraordinary. So it's great that it has been that it is celebrated here. Of course, I think that having this big conference, this very prestigious conference as ICTP, was an excellent move. Together, of course, with Lincei. I think you all know that ICTP has a mission both of a very high-level research in science, and quantum mechanics has a big weight in this research, which is carried here. We all know that. And at the same time, it is also exposing, with this anniversary conference, exposing it to the global world and developing countries and all the colleagues from developing countries who are here, who come here, and who visit here regularly. So I think from all these points of view, it's a great event that I'm looking forward to it. Thank you.
So, as was mentioned, this is a global event of the 20-25 years of quantum science and technology, so we should show a video prepared by APS for the, it's a short video, which should, okay. Okay, so Massimo Enguscia will be the chairman of the first session. We are 20 minutes ahead, which is amazing. I mean, typically we are behind, so I don't know. Shall we start now, or you want to? We should start. I mean, we can start now, and we will be behind schedule sooner or later. So.
Senti, tu vuoi 5 minuti di discussione? Okay, we start immediately, also because we want to respect time, and because the last talk of this session is made from remote by Federico Capace, must start really at noon 10. So we would like to leave 5 minutes for maybe for questions or discussions. And we have the honor of opening this conference with Professor Anne Lullier from Lund, Sweden, who, just to say, is one example of Nobel Prize winner and also members of the Accademia dei Lincei. And she will talk us of how to watch the quantum world with attosecond light pulses. So, Anne, thank you.
Good morning. It is really a pleasure to open this conference. Is this working? Okay. So I'm going to tell you about applications of attosecond pulses to look at electrons. And let me start by a quotation from Heisenberg, 1925. And he said, the formal rules which are used in quantum theory for calculating observable quantities may be seriously criticized on the grounds that they contain as basic element relationship between quantities that are apparently unobservable in principle. So I don't know what he was thinking of. Was it matrices or wave function? I don't know. But anyway, this is also something we learn in quantum mechanics. This is Born's rule. What we can observe is the square of the wave function, modulus square of the wave function. But can we actually measure the wave function or the time dependence of the wave function? So this talk is about trying to do that for electrons. And I'm going to concentrate on photoionization, very basic process that happens when an atom is exposed to radiation with high enough frequency. And this is a photoelectric effect, which is also a basis for quantum mechanics, discovered in 1887 by Hertz and explained by Einstein with the help of the concept of photons, which was introduced by Max Planck 1900. And this was done in 1905. So I'm going to really look at this process, and especially look not so much as the photon here, but at the photoelectron. And I'm going to ask 3 questions. First one, how long does it take for an electron to be emitted? Can we measure this time? Second question, I'm sure you think of this photoelectron as a particle going away from the atom and then being detected. You can measure its energy, maybe its momentum. But can we do better than that? Can we measure really the wave property of this photoelectron? We know that it's both a wave and a particle. Can we measure its wave property? A little bit more generally, its quantum properties. Last question, how do we do that? And actually, I will start by that. How can we measure these quantities? So we use attosecond light pulses and high-order harmonics. This is kind of a one-slide summary of why I got the Nobel Prize 2023. I've been going around talking about this, but now it's a one-slide summary of this, because I'm going to concentrate on the application. So when you focus an intense laser, femtosecond laser, into a gas, you generate high-order harmonics of the laser field, and in the time domain, at least in certain conditions, you have a train of attosecond pulses. One pulse every half laser period, and the spectrum in the frequency domain, you have a frequency comb, you have a harmonics of odd order. The condition to have this phenomenon is that you need a strong laser atom interaction here in the medium. And this is a nonlinear optics process. You also need to achieve phase matching, which is normally achieved in a partially ionized medium. This is not enough to get temporal information. So yes, one more thing. Of course, you can choose to generate one attosecond thing, one attosecond pulse. In that case, the spectrum is, of course, broadband, continuous. You can also isolate a harmonic, and in that case, the pulse duration is longer, femtosecond. But you can also choose to work with the pulse train or these high-order harmonics. The advantage is that you have a better spectral resolution given by the harmonic spectral widths, and you keep the very nice attosecond time resolution. And actually, I will show you results obtained both with the train of attosecond pulse and with only one harmonic. If you have that, so let's use these tools now. But if you only have this radiation, you don't have any temporal information. Let's say if you ionize an atom with high-order harmonics, frequency comb like this. In the time domain, this is a pulse train of attosecond pulse. You ionize your atom with this radiation. What do you get? You get electrons at different energies corresponding to absorption of the different harmonics. You don't get any temporal information. It's just photoelectron spectroscopy in a different way compared to what has been done with synchrotron radiation using this comb structure instead. So you need something else, and what is often used is simply a fraction of the laser, which is used to generate the harmonics, so frequency omega. In the time domain, this is your optical wave. And now you can obtain two photon transitions. So you have absorption of harmonics plus a laser photon, creating a sideband. Or you can also have stimulated emission of radiation here, leading to the same final state. So you see, we create a quantum interferometer through this technique. This state here, the continuum, can be reached by two quantum paths. Quantum mechanics, we add amplitude. We have a method that gives us access to the phase of this quantum path. Looking at interferences, we would like to have something that varies to be able to follow interferences. And what we do is simply to vary the delay between the train of attosecond pulses and this optical wave. With that, we get this phase information and temporal information. So this technique is called reconstruction of attosecond beating by interference of two-photon transition, RABIT. We follow the tradition of ultrafast optics to call by animal names a method for characterizing the wave, and this was called RABIT. This was based on an idea by the group of Alfred Mackay and shown experimentally for the first time by the group of Pierre Agostini in 2001. This led to the first measurement of attosecond pulses in a train. But now we're not going to characterize pulses. We're going to use this technique to look at photoelectrons. How do we do that? What is the experimental method? Well, first of all, you need to have an optical interferometer, and very stable one, very precise. Very often it's based on a Mach-Zehnder type of interferometer, as shown here. So in the pump arm here, we generate the attosecond pulse train. You remove the fundamental here. So you get this attosecond time pulse train. And then in the probe arm, we simply have a delay. So we get our tool, attosecond pulse train, and the probe with a variable delay. And then we send this into a chamber containing a gas, which we want to study, and we detect the electrons. We do electron spectroscopy. What do we see? We see what is now called RABIT spectrograms, as shown here. This is an electron spectrum as a function of delay. And what you see are peaks. You have main bands here corresponding to absorption of the harmonics. And then you have these side bands due to these two photon transitions. And you see that these side bands very nicely oscillate. And this is really the information that we try to get, is what is the phase of this oscillation. And the period of the oscillation is half the laser period. For titanium sapphire radiation, this is 1.3 femtosecond. So we are really in the almost attosecond regime. So again, the information is to extract the phase out of the oscillation here. So now I'm coming to the first question. How long time does it take for an electron to be emitted? And I'm going to focus on one experiment, in one case, which is the ionization of argon atom in the 3s shell. And the reason I choose this case is because, first of all, it's very spectacular, and then because it's, as you will see, and then because it's a problem we have been working on 15 years, and only now we start to understand what is happening. So I'm going to look at, to ionize an atom using attosecond pulses. You can think that we create a broad wave packet. And we would like to know to find the intensity of this wave packet, which is the probability that you get electron as a function energy. This is easy. But again, what we try to obtain is phase information, or spectral variation of the phase, which is the group delay of this attosecond wave packet. This is actually a quantity that was already introduced by Eugen Wigner in 1955 in connection with collision theory. And in here, I'm not looking at a collision. I'm just going to look at photoionization, so it's half a collision. So Wigner introduced this group delay equal to the derivative of the scattering phase. The scattering phase is the phase that the electron acquires during scattering, going through a potential. And it's relative to the phase of a free electron. So Wigner introduced the derivative of this phase and gave this interpretation as a group delay of the electron wave packet. How do we do this measurement of this Wigner delay? Well, again, we use this tool, which I have already introduced. So we probe this wave packet at different energies using this interferometric technique. What do we get? Actually, it's a little bit more complicated than I mentioned. This delay that we get in the measurement has actually three contributions. The contribution of the excitation pulse, of course, this attosecond pulse. The contribution of this ionization process, this Wigner delay. And there is also a small correction due to the measurement itself, to the fact that you need to have an infrared laser pulse. So this affects the measurement, especially at threshold. In the case I will discuss, this term is really very small, so let's forget it. Okay, so here is now the measurement I want to show you. And first of all, I'm going to show you the cross-section. This is something we know from the 70s, 80s, is the cross-section of argon in the 3s shell in this region, close to 40 electron volt. This is called Cooper minimum. It's not a real Cooper minimum in the sense that transition is going through zero. It's a kind of effect of the Cooper minimum of the 3p ionization, but which is seen in the 3s ionization due to very strong 3s, 3p interchannel coupling. So this was really a success of many body perturbation techniques in the 70s, particularly by Amusia, Russian scientists, to explain the presence of this Cooper minimum in argon. But you see a very nice agreement. I don't want to discuss any detail here. A good agreement between experiment and theory. So at that time, 70s, people thought this is well understood. We know what is happening. Now let's look at the group delay of the wave packet created in this spectral region. What do we get? So first of all, well, I have these two terms here. How can I see the difference between the two? Well, what you can do is you can ionize your atom both in the 3s and 3p shell. You will get electrons with different energies. And you can take the difference between the two time delays here. And by taking the difference, this term is removed. It's the same in both cases. And this is the measurement showing this difference in time delays in the same region. This is an experiment performed by a group in China. And then you have a theoretical calculation. Let's forget the red curve for the moment. The blue curve corresponds to the blue curve here. This is the theory from the 70s called random phase approximation with exchange. Perfect agreement for the cross-section. Strong disagreement in this region. And let me focus a little bit on this. First of all, doing a little bit of atomic physics, you can convince yourself that this is the region of 3s ionization. This is where 3s ionization influenced the delay. And this is 3p ionization leading to this bump here. So let's concentrate on this region here, where you have strong disagreement between the blue curve and the experimental result. And again, this is a problem we have studied during 15 years. Why there is such a strong difference between experiment and theory? Are the experiments wrong? This was the first assumption. And we did this experiment again and again in Lund, in Saclay, in Zurich, and now in China, leading to the same result. It goes negative. There is a strong delay, negative delay, which means actually it's an advance of the electron wave packet. The theory shows this result. Until recently, where theorists did a different calculation, added some more physics and some more correlation effects, adding the influence of shake-up processes where the 3p electron is excited, one is excited and the other one is ionized. And doing that, they get this red curve. So now we have a final agreement. So this is to show you how important this type of measurement is to refine the knowledge in atomic physics. Let me also point out the physics behind. If we do a little bit of physical interpretation, we have very different electron dynamics. In here, when you are here, the electron is really trapped in the potential. It takes a long time for the electron to get out. It takes almost 400 attoseconds. It's kind of trapping effect. While in this case, it's just the contrary. The electron is pushed out of the potential. So very different electron dynamics. Now I'm coming to the second part. What are the wave or even quantum properties of the photoelectron? And here I'm going to start by looking at a very, very well-known process, which is autoionization of helium atom close to this 2s2p bond state. So this is a prototypical process where you have a beautiful quantum interference effect between direct photoionization and photoionization via a discrete state, followed by autoionization here. Same question. This type of process have been studied for decades, particularly using synchrotron radiation. Can we do something new using our techniques and using this Attosecond pulse plus infrared radiation as a new tool? In other words, can we get phase information on the wave packet that is created here? We know how to measure its amplitude has been done before. Can we now measure its phase properties? The answer is yes. We use the same technique, this interferometry technique. We kind of make a copy of this photoelectron wave packet here, and we can read its phase. And here is the result showing for the amplitude a beautiful interference effect and a phase jump of pi in this region. So now we have the spectral phase and amplitude of the wave packet. We can go in the time domain by Fourier transform, and you get the temporal information on this wave packet. We can even do better following tools of ultrafast optics. We can do a time frequency representation to really follow in the time domain the photoionization process. And this is shown here. It's using a so-called Wigner representation. This is the definition here. And what you see here is really the kind of movie of the photoionization in the time domain with first a broad feature here corresponding to direct photoionization, broad in energy and short in time. And then you have a region where you have strong interference effects between the two paths. And finally, longer time scale, you have only photoionization via excitation on the discrete states, narrower in energy, longer in time. So these are the two processes. Can we always do that? This really assumes that this is fully coherent. I'm considering the photoelectron as an optical wave. But sometimes we create a photoelectron. You have different initial state. And what you get is non-coherent. So can we do better than that and actually measure the quantum state of the photoelectron? So just a few years ago, we looked at this and thought that, oh, maybe we can actually determine the density matrix of a photoelectron using a slightly different scheme compared to what I have told before, using this time a bichromatic probe. So we have our pump parts. This time is just a harmonic. but we have a bichromatic probe pulse with 2 colors. So the excitation scheme looks like this. We create a wave packet, which we want to characterize. Now we want to really determine its density matrix. But then we probe this wave packet using 2 different colors here. Again, we generate a sideband. Just to explain a little bit the principle of the method, you can split the XUV radiation into 2. I take 2 photons with slightly different energy, and I look at 2 energies of the wave packet projected on the final state. And you can see now clearly the interferometric scheme. I can reach the same final state by 2 quantum paths via epsilon 1 state or via the epsilon 2 state. So this way, I can really probe this wave packet. In particular, what I get here will depend on whether there is a phase relationship between these 2 states. In other words, it allows us to measure the coherences of this wave packet. So doing this, and again, varying the delay, you get an interference signal that looks like this. So now it's not 2 omega anymore, it's delta omega, which is the difference between the 2 frequencies here. So this is, and the coefficient that you get here is proportional to the coherences. The phase is the argument of the cosine function. So this is a quantum state tomography of this electron wave packet. This method has been called Kraken by one of my students. I'm not responsible for the acronym, but somehow it stayed there. It's using Swedish that you see here, and yeah, using the letters that are in the Swedish version of this. How do you do the bichromatic probe? We use a Forer shaper where you, in the middle you have a grating, focusing mirrors, and here you can put slits, and we can extract part of the spectrum of the fundamental. So we really sculpt part of the fundamental spectrum to obtain our bichromatic probe. And this is results showing you this oscillation at different delta omega. So you have different results here. And each oscillation allows us to determine one of the off diagonal of the density matrix. So here you have a density matrix of the photoelectron, energy versus energy. We are in the continuum. This is continuous wave density matrix. The diagonal is in this direction. It's a bit different from quantum optics. It's in this direction. Now, of course, this is only a few measurements. So then you would like to do a fit, and this is what we have done. And in this case, we obtain a very nice round density matrix. This is obtained in helium. Nothing special, nothing strange. It's a pure state. And the purity is being calculated to be 0.94. So we don't learn very much here. But we, again, this is developing a new technique. Let's look at argon instead. And here you see that the density matrix that we measure is really elongated. Obviously, we lose coherences on this part. We have a mixed state. What it is due to? Well, it's due to the spin-orbit interaction, which leads to a splitting and of the final state of the ion. So the ion can be left in the P1 half state or in the P3 half state. So you can get an electron coming from with the ion in the 3 half state, or an electron with the ion in the 1 half states. In other words, what we have, if you consider the system ion plus electron, in this photoionization process, we create an entangled state. Again, ion in the 1 half state, or ion in the 3-half state. And since we are only looking at the degrees of freedom of the photoelectron, what we measure is a reduced density matrix. It's a mixed state, and the purity is equal to 0.65. It's a bit higher than what is predicted if in the case of its maximally entangled state, which would be the case if there were no overlap between the two electron distribution. Because in that case, if you detect an electron with certain kinetic energy, you know that the ion is in a certain state. In our experiment, there is a small overlap here, which means to a slightly higher purity. Okay, I am coming almost to the end. I have answered this question. And what else can we do? Can we, so I would like to finish with a little bit of outlook. Can we do really, using these new techniques, we can learn atomic physics, we can learn molecular physics, but can we do really something in quantum mechanics? Can we test quantum mechanics? Well, there is something we have started to try to do is to test actually Born's rule using the Sorkin test and using the photoelectrons that have been telling you about. So this is the idea. It's Born's rule tested with the help of 3 slits. If you apply Born rule, which you see here for 2 slits, for 3 slits, then you find that in this expansion here, you only have 2-term interferences. And it was proposed by Sorokin in the 90s, actually, to try to, doing a 3-slit interference, try to see if there could be some 3-term interferences. And so you can write these 3-term interferences, if it exists, as a difference between what you get through the 3 slits minus what you get to 2 slits, and then plus what you get through 1 slit. And Sorkin introduced a parameter which is more or less the quote, the ratio between this 3-term interference term minus some background, and then more or less the 2-term interference. So how can we do such an experiment? Well, we use the same idea, but this time we have three chromatic probe. We sculpt our probe with 3 different wavelengths, and pump is a harmonic. Same type of phenomenon we are looking at, 2-photon transition, this time using these 3 different colors. We look at the side bands. And using the same experimental technique, this 4F chipper, and here now we make 3 holes in this focal plane between the 2 focusing mirror. So we made 3 holes in order to make 3 slits, and you can see that we can measure this by, you can have only 1 slit, 2 slits, or 3 slits, and we can vary. What do we get? Well, now you are really excited. You want to know what we get. Well, we get something which is really different from 0. If, according to quantum mechanics, this parameter should be equal to 0. We measure actually not 0 at all. I don't think we violate quantum mechanics. It's just that we have to do a better experiment. This is by simulating this process. What is very interesting is that it's predicted that we could get a better resolution than using photons. This is a test with photons. So this is to be continued. With that, I would like to thank you very much for attention. Thank all the members of my research group that you see here. I'm very happy to be part of this conference and to celebrate the International Year of Quantum Science and Technology. Thank you for attention.
Thank you so much for this ultra-fast but also ultra-deep picture of our world. And now, Sandro Stringari.
Are these new experiments providing a novel insight on the temperature, on the time as an operator, or not as a, let's say, traditional parameter that we use to understand the physics and the time evolution?
I don't think so. I think the question should go to the theorists here in this room. But no, I don't know. I don't think so.
I suppose that to obtain your results, there is an average over many atoms,
Yeah.
and an average over many pulses.
Yes.
How many? Just to get an impression. How many atoms in your observation zones, and how many pulses do you average to obtain so beautiful results?
This is a difficult question. Yeah. I don't. I mean, with one laser shot, we are not. We don't. We're seeing mainly single events or maybe a few events. So for one shot, not very many atoms participate, but then we average over 1,000 of shots.
How many atoms do you have in the interaction zone between the gas and the lasers?
We have millions.
Millions?
Yes.
No, it's
yes.
just to get a
Yeah.
number. Millions.
Yeah.
Okay.
Yeah, thank you, Anne, for this very nice presentation. So at the end, how long does it take for this photoelectron to escape?
Yeah, so I can answer several ways. I show you an extreme case where it's in the 3s Cooper minimum. Theory says 300 attosecond and experiments say minus 300 attosecond. But I'd like to say the following. In general, if you ionize an atom without things happening, or in a kind of flat continuum, simple case, it's very, very fast. It's a few attoseconds. We can't measure it. Okay? But if you have cool atomic physics interactions, then it can be delayed or advanced depending on what is happening. That's a short answer. We have looked, for example, at the ionization in the 4D shell of xenon atom, where you have a beautiful giant resonance. And here we measure delays like plus 20, 30 attoseconds. So we can measure these delays. But in general, if you don't have a resonance or something, it's very, very fast.
Okay. So we thank you again. Yes. Yes.
Okay.
Thank you very much. Can you hear me? Yes.
So, physics is one. We shall learn this from Professor Maciej Levenstein from ICFO Barcelona. Go ahead, Maciej.
Grazie mille. Good morning, everybody. It's really a great honor to be the speaker at this conference, and especially it's very challenging to speak after Anne. So I start always with the logos of the agencies that finance research of my group at ICFO, and with the group itself, which is still 20 people working on very many areas, as you will see from the talk. So the idea of the talk is that it is kind of overview of different Nobel Prizes in low energy physics. So I will jump between different Nobel Prizes and Nobel Prize winners, which at least were supposed to be present here, and some of them, and many of them are. And I will also go beyond. So let me start with the Nobel Prize for trapping and cooling of atoms by laser light for Steve Chu, Claude Cohen-Tanucci, and Bill Phillips. This area was blooming. I have to mention the name of Ted Hensch in this context. This area was blooming in the 90s. In 93, I was Gila Fellow, and I started to work with Peter Zoller, Ignacio Cirac, and Ivan Castin. And all of us at that time were completely obsessed by the obsession of Claude Cohen-Tanucci, how to reach the quantum degeneracy, Bose-Einstein condensation, with laser cooling only. And we worked with many models of this thing, but the most successful was maybe described in this paper, written a little later when I was collaborating with people from École Normale, in particular Ivan Castin. So the idea is that in laser cooling you have an atom which you drive in a controlled way, but then it spontaneously emits a photon, producing a recoil energy. This photon can be reabsorbed, producing another recoil energy, and reabsorption leads to heating in general. So what we proposed in those days was a limit which is called festina lente, so hurry up slowly. So roughly speaking, we wanted to control the width of excited state here to be very narrow, narrower than the trap frequency. And this can be done if you use Raman transition, because you can use the tuning here to control the effective width of the two-level transition. The point is that if you produce a photon in the spontaneous emission that has, let's say, +5 trap frequencies, then you have to absorb the same photon because the line is narrow. So you gain 5 and you lose 5. You gain -3 and you lose -3, and so on. So only the last photon, which leaves the system, give you a recoil energy. This was observed in experiment, but much, much later. In the first paper is from 2017 in Science or Nature, I don't remember, by Vladan Vuletic group at MIT. This is a PRL in which they explicitly mentioned that they work with our festina lente limits. Okay, at that time, I was, as I mentioned, at Gila, and I had the honor to run BEC seminar, which was a joint seminar of experimentalists and theorists. And as you can see, the gallery of the people who were participating in it is just amazing. Many of them are here. And this is when I started to write papers on Bose-Einstein condensation, in particular scattering of short laser pulses. This was my first PRL on BEC, and a paper on scattering of light on BECs, where we observed some kind of collective narrowing of the line. We were at that time extremely influenced by the papers of others, in particular by David Politzer. It works, or it stopped to work? Well, it works. To whom I will come back talking about another Nobel Prize. Also Boris Svistunov, Zhora Shlapnikov, Juha Javanainen, and mentioned David. The Bose-Einstein condensation was achieved in 1995, but the Nobel Prize was given in 2001 for both the achievement of the condensation, but also for fundamental studies of the properties of condensate for Eric Cornell, Wolfgang Ketterle, and Karl Wyman. I have to mention here two Italian names who are in the organization of this conference, because they contributed, on one hand side, Sandro for the theory of this physics and Massimo for experiments. 2001 celebrations was a real feast of science because it was 100 years of Nobel Prize. And so they invited all the alive Nobel Prizes to come. Every second person you were meeting in the corridor was a Nobel Prize or a partner of the Nobel Prize. And I had the honor to be there after the Bose-Einstein Nobel Symposium in Göteborg. Then I was in Stockholm several days. So in the end of the 90s, I moved to Hanover, and I started to work very intensively in experimentalists on Bose-Einstein condensation, in particular with the group of Wolfgang Erdmer and Klaus Engstock and Gerhard Bilk. And this is our second PRL from that period, in which we demonstrated the generation of dark soliton in Bose-Einstein condensate of rubidium. Rubidium atoms, if you don't do anything, are repulsing each other. So the only kind of soliton that you can get is this kind of dark soliton, which means it's a dip in the density with a phase that is making a jump of pi in the position of this dip. And this you can generate by using a technique which is called phase imprinting. This means that you shine the laser on one side of your elongated condensate, and you indeed, for a short time, apply a strong potential which imprints the phase on the wave function of the condensate. This paper was published in December 1999. I remember calling George Basbas, the chief editor of PRL, and asking him, please don't do delays with reviewing. And he didn't. The paper was published 1 week after being sent to PRL, after referees. And in this way, we won the race against Bill Phillips' group, who were doing a very similar experiment, except with a little more spherical traps. And that was published in Science, but in 2000, so a little later. What we have been, with Peter Zoller in particular and Zhora Shlapnikov, very interested in those times, beginning of this century, were ultra-cold dipolar gases. Dipoles, as you can see on this picture, if they are like that, they repulse each other. If they are like that, they attract each other. In general, the interactions are very complicated and isotropic. And of course, this is the first paper that we wrote with Luis Santos and Peter and Zhora. As you can see from this picture, the properties of the Bose-Einstein condensate must depend on the geometry of the trap. If you take a pancake trap, and you put the dipoles perpendicularly, obviously they repulse each other mostly, and therefore everything is stable. You can put more atoms, you can make dipoles more stronger if you can. Nothing happens, it's stable. If you do it in a spherical trap, then you have many pairs which are attractive, and therefore at some moment, if you put too strong dipoles or too many atoms, you will have a collapse. At that time, we didn't have any idea what happens after the collapse. And the first observation of dipolar Bose-Einstein condensate was in chromium, done by Tillmann-Pfau in Stuttgart in 2005. This is a picture of absorption images, time of flight images from isotropic and anisotropic trap, where they already see some signatures of dipolar interactions. We have been studying excitations in the skies of gases at that time, and together with Luis Santos and Jora, we have discovered the presence of Roton-Mach, a kind of analog of Roton-Maxon minimum in the spectrum of excitations. I mean, normally if you have excitations in a Bose gas, you have a linear part of the dispersion relation which corresponds to phonons, and then quadratic part corresponding to more or less free particles. But here in dipolar gas, because of this interplay between attractive and repulsive interaction, you have a minimum. This minimum becomes deeper and deeper as you have more atoms or more stronger dipoles. At some moment, it hits zero energy and there is instability. Again, at that time, we didn't know what happens after. Now we know that there is creation of the so-called quantum droplets, which are stabilized by the famous beyond mean field correction to energy of Young and others. This was observed in an experiment by Francesca Ferlaino. Here you have the spectrum that she has measured. As I'm saying, she was able then to follow this, so to say, the fate of this instability and observe the quantum droplets in dipolar gases, similarly as Tillmann-Pfau. A little later, Laetitia Taruel et al. Observed similar quantum droplets in short-range interacting gas. What was very hot subject in the beginning of the century was moving toward strongly correlated systems, and this was induced by Peter Zoller and Ignacio Cirac in this famous paper with Crispin Gardin and Dieter Jacks and Christoph Bruder, where they proposed to use strong optical lattices to simulate the Bose-Hubbard model with ultra-cold atoms, or Fermi-Hubbard model if you put fermions there. And this was observed in this seminal experiment by Ted Hens' group, Immanuel Bloch, Markus Greiner, and Tilman Esslinger were there, and Olaf Mandel. They observed transition from the Bose-Einstein condensate to a Mott insulator state. Bose-Einstein condensate is a superfluid. It has a tendency to spread all over the lattice, and it has a phase coherence. The wave function of all atoms has the same phase all over the lattice, and therefore you observe these wonderful Bragg structures because of the phase coherence. In the Mott insulator state, you have fixed number of atoms per side, no phase defined, so you see the blurred pictures. And this was a very, so to say, sound idea to look onto quantum simulators and various interesting systems in condensed matter or even in high energy physics, in particular the strongly correlated ones, which are difficult to simulate with classical computers. This goes back to the idea of Richard Feynman from 82. We have written this reference book with Anna Sanpera, Veronica Finger, this book which covers all these subjects from weakly correlated ultra-cold gases to various kinds of strongly correlated. This book is still very actual and is used by many. I have no time to talk about this subject because I have no time. But I will talk about some. The one that I want to mention is in 2003, we pioneered the idea of simulating disordered systems, both weakly correlated and strongly correlated with ultra-cold gases, by using random potentials, light-induced potential or laser-induced. So for instance, speckled potentials or quasi-random potentials using incommensurate standing waves. And this is a theory picture in which the standard wave function of the condensate, which usually is an inverse parabola in the trap, becomes exponentially localized because of Anderson localization effects. Anderson localization, of course, was predicted and awarded Nobel Prize for Philip Anderson much, much earlier. Sir Neville Mott got it also for localization due to the repulsive Coulomb interactions between electrons. John Van Vleck for something else, but also very important. But I think that the most beautiful demonstration of Anderson localization is in ultra-cold gases. And it goes to Alain Aspect and to Massimo Inguscio. Alain did it with speckle potential, so random, really random light potential. Here you have a photo of the wave function of the condensate, which indeed shows a beautiful exponential localization, of course, in quasi-1D system. Massimo has done analogously beautiful experiment with quasi-periodic, pseudo-random, let's say, potentials. Okay, the localization occurs not only in weakly interacting cases, it also occurs in interacting systems, and here is, and there it is termed many-body localization. It goes back to this paper by Igor Alainer and Boris Altschuler with Dima Basko. Here are the photos. So what they say is that there are systems that, due to interactions and disorder, interplay between the two, fail to reach thermal equilibrium. Okay? They are non-ergodic. This has been very quickly generalized to case of strong interaction and strong disorder, especially by David Hughes. And it's a very hot subject in quantum many-body physics because it's open of, it's really open of controversies. I mean, this was original title. The editors didn't agree. This is a Rice review which showed that. So the main question, which is not really answered, is there a many-body localization phase transition? Are there systems that at certain values of their parameter, disorder, interaction, etc., never thermalize for infinite times? This is open question. Okay, of course, non-ergodic behavior happens in classical system also, and the best example is spin glass. The first so to say, very interesting model of spin glasses was proposed by the late Sam Edwards and Philip Anderson again. This is a short-range Ising model interacting by a random potential, equally probable to be ferromagnetic or antiferromagnetic. This mimics the randomly located magnetic impurities in the real spin glasses. It was very quickly generalized to infinite range model by David Sherrington and Scott Kirkpatrick, who have then proposed a exactly solvable model of spin glass. And indeed, they used the so-called replica trick. They wanted to calculate the free energy per spin averaged over disorder. So they did it by introducing n copies of the system, which are n replicas, averaged over thermal and fluctuations and quenched disorder, -1 divided by this small n here, and then took the limit n going to 0. This gives you exactly the logarithm which you want to calculate, which is the free energy. And looks horrible mathematically, but it works. And indeed, they use the probability distribution of these couplings in the model, which were centered at J0. When J0 is positive and large, you are, of course, ferromagnetic for sufficiently low temperatures. For high temperatures, you are paramagnetic, but here you have a region which is a spin glass. Unfortunately, from the very beginning of their work, it was clear that the solution is not correct because the entropy in the low temperature region was negative. And there come the ingenious or the genius of Giorgio Parisi, who has proposed to break the replica symmetry, not to in the solution of Sherrington-Kirkpatrick, all the copies were treated on equal footing. Giorgio proposed to break this symmetry and make different copies different. And the meaning of that, I especially like this paper of Giorgio from JFIS A, from which I learned all that. He considered here a matrix QAB, which is in the spin glass, the spins can freeze in various configurations. And what you look at are overlaps between these configurations. So alpha and beta are different configurations, and Q alpha beta is a matrix of overlap. And the properties of this matrix are, well, you construct it step by step, but you construct it in this kind of hierarchical way, breaking the symmetry first into blocks, then blocks into blocks, and so on and so on. More or less, it corresponds to the situation that the energy landscape has hierarchical structure, has minima, then minima within minima, then minima within minima, and so on. Amazingly, the Parisi formula turned out to be exact, rigorous, and this was proven by Michel Talagrand in the beginning of the century, and he got Abel Prize for this in 2024. Whereas in 2021, the Nobel Prize was awarded to Giorgio Parisi, half of the Nobel Prize, the other half went to Manabe and Hasselmann for climate research. Giorgio got the prize for discovery of interplay between discovery and fluctuations in physical system at all possible scales. So here is a photo of Giorgio, and this sentence is maybe the most important. The non-ergodic aspect of spin glass was instrumental for awarding this half of Nobel Prize. I have to put the people who were collaborating with Giorgio on this physics very, very strongly. In particular, they wrote a fantastic book on this kind of problems. So Marc Mézard, who is organizer of this conference, and Miguel Ángel Virasoro, who was a director of ICTP for many years and passed away too early. I started to work on this in the 80s. My mentor, Fritz Haacke, told me after my PhD that quantum optics is not a separate discipline of theoretical physics, so I have to do statistical physics or something more fancy. And this is my second PRL, in which we consider two replicas of the Edward Anderson model and calculate average over disorder and calculate effective Hamiltonian for the overlaps between the two copies of the Ising spin, and then apply some high temperature expansion to estimate the presence or absence of phase transition in different dimensions, 3 to 1. We came back to this approach a few years ago on a very sad occasion of passing away of Fritz Haacke. And also this paper is dedicated to one of my mentors from Poland on disordered system who passed away in 21. Had I written this paper later, I would have had to add my friend, mentor, and also teacher in statistical physics and disorder system, Łukasz Turski. Okay, let me change the gears now and talk about some other things that we do with quantum simulators, mimicking topology. So there are many papers when you try to mimic integer or even fractional quantum Hall effect with ultra-cold atoms. Here we look at the vortex nucleation. So vortex is a topological state. And this is happening like that. You have a small trap in which you have, let's say, 8 atoms or something like that, and you rotate it. When you rotate it slowly, everything is described by mean field theory. You have a wave function for the atoms. All the atoms are in the condensate, so they have the same wave function, so to say. And it's kind of peaked in the middle. When the vortex is created also, mean field theory works well, except that the wave function now is a little more complicated. It has a hole in the middle corresponding to the vortex, and it has a phase dependence corresponding to the unit of angular momentum. But here in the middle, when you go from one to another state, nucleation, this is a very complicated, in this case, 8-body, but anyway, many-body quantum state, which is full of entanglement, full of quantum correlations, and so on. And this is what we studied in this case. This brings me to the Nobel Prize to, unfortunately, late David Tholes, Duncan Haldane, and Michael Kosterlitz. This was given for theoretical discoveries of topological phase transition and topological order. Here is a very beautiful experimental paper from Hamburg group, Klaus Zengstock and Christoph Weitenberg, who, by the way, now is a professor in Dortmund, where they study experimentally the so-called Haldane model. Haldane model is a model on a hexagonal lattice. You have a tunneling between nearest neighbors, which is normal, so it's positive. It relates to the spreading of the wave function all over the lattice. But you have second neighbor tunnelings, which is characterized by the complex phase phi, okay, e to the I phi factor. And this leads, the system doesn't break time reversal symmetry, so it's not like magnetic field, but it has very similar effect. There is an anomalous Hall effect, you may say, and therefore there are 3 phases. One is topologically trivial, but these 2 others have topological invariant, the so-called Chern number equal +1 or -1. And this has been observed in this experiment. And moreover, the data was analyzed using machine learning, supervised machine learning. We have repeated the same problem using unsupervised machine learning together with Hamburg group, or I should say Hamburg-Dortmund group in this paper. And again, the data are not so nice because it's an unsupervised machine learning, but still it's very nice application of machine learning for experiment, or neural networks for experiment. So this brings me to attractor neural networks, and in particular Hopfield model. In Hopfield model, you have Ising spins that have configuration as j at time t. They couple to this couplings jij to the ith spin. Then if the signal coming to the ith spin, which is a sum over all j's, is bigger than a certain threshold, then this guy becomes +1, so we say it's active in the time t+1, or is, if it's smaller, it's -1, it's inactive. And the genius of the gentleman, which is here, John Hopfield, was that in 1982, in the PNAS paper, he proposed these couplings to be symmetric. And this means that this whole dynamics is just the local minimization of the energy of the Ising model with these couplings and these magnetic fields. You can think they are kind of random because they are not clearly specified. So this looks like that. You have a complicated, let's say, landscape of energy. If you start close to this minimum, you will go in the evolution to the closest minimum. If you start here, you will go to other minimum, and so on and so on. So the stationary states are here, minima of energy. If you add thermal noise, it will be minima of free energy. Recognition is attraction, that's why attractor neural networks. This is pattern recognizer, content addressable memory, and however, it has very interesting property which was discovered by John Hopfield in his paper, numerically, that if you want to store P patterns in this system, if the number of patterns is much bigger than, is comparable to the number of neurons, then if this proportionality constant is too big, you cannot do anything because the storage becomes impossible for alpha, for proportionality constant too big. And what happens, you go to a chaotic state, which is nothing else but spin glass. Of course, you may say that the Beatles have discovered this effect in '67 already, singing in the song A Day in Life on Sgt. Pepper, how many holes it takes to fill the Albert Hall. I mean, just think about the sandbox and digging holes. I mean, if you have a finite size spade, if you want few holes, it's easy. But if you want to fill everything with the holes, they will start to overlap. You go to chaos. Okay. This brings me, of course, to the Nobel Prize in 2024 for John Hopfield and Geoff Hinton, who got it for Boltzmann machines and backpropagation algorithm for feed-forward networks. And this is my gallery of the people who contributed to this area very strongly. Some of these photos were already discussed, but there are others who were my friends and very close mentors, I would say. I learned actually neural networks from the book of Daniela Mead in the 80s. And I started to work on neural networks also in the 80s. And I worked quite intensively on the subject with Andrzej Nowak, who was a social psychologist with very good mathematical skills. And we wrote very many papers, and I have two PhD students at the time. One was this Wojtek Tarkowski, who was working on storage capacity for correlated patterns. At that time, we have been competing or discussing even when I was in Paris with a group of Marc Mézard and with, at that time, young Rémi Monasson. Okay, this is, of course, when I started in the 80s, it was for me trivial to jump into machine learning and artificial intelligence in the last 5 years. And in fact, in my group, I think I have supervised in the last 6 maybe years, 6 PhD students on this subject, and maybe we have written about 50 papers on applications of machine learning and neural networks for various quantum, usually many quantum many-body systems. I show here this book, which you can buy already. I think it is formally not yet published, but you can order it already from Cambridge University Press. I'm very proud, not only because of the cover, which is very beautiful, but also because of the fact that 9 of the authors of this book are from ICFO and 8 from my group, were in my group. Okay, let me change the gears and go to quantum simulators of high energy physics. Here is an idea of creating synthetic gauge fields, non-abelian gauge fields. And Peter Zoller, who pioneered the idea of simulating in optical lattices abelian gauge fields using laser-assisted tunneling that adds phases to the tunneling matrix element. Here is a very similar idea. We use the laser-assisted tunneling, but now at each side of the lattice, you have 2-state atom. So the tunneling corresponds to the unitary matrix that transforms you from one side to another, laser-assisted, but it can change in a coherent way internal state. And then when you go around the plaquette, you get the product of these unitaries, which is a kind of non-abelian Aharonov-Bohm effect, in contrast to the abelian Aharonov effect, if you have just phases. And this brings me to the Nobel Prize to David Gross. Mentioned already David Politzer, who was writing about Bose-Einstein condensation, and Frank Wilczek. I just want to comment that the quantum simulators of synthetic gauge fields and of lattice gauge models, theories, is really a very hot subject. As you can see, I organized here with colleagues, of course, a workshop in 2024. This is a review, one of the last reviews on the subject. It's a very hot subject because there is a lot of, we are very far from mimicking quantum chromodynamics, but still we can mimic quite interesting models and the quantum dynamics of these models. And there are a lot of experiments with ultra-cold atoms, ultra-cold ions. And also, this is one of the most interesting applications of the quantum simulators with digital quantum computers. This brings me, or I jump now to the prize from Ted Hensch, who deserved it from the beginning. So this was the prize 2005 for Roy Glauber and John Hall. And Ted, Glauber got it for optical coherence, and Dave for frequency comp that was mentioned by Anne. So the Glauber was my friend and my mentor. I worked with him on quantum optics of media, and also at Harvard when I was there 3 years. I started to work really intensively and seriously with experimentalists, which has changed my life as a scientist. However, forget for a moment about this aspect. Let's go to frequency comps. Anne has already mentioned that. This is like a system in which we have a spectrum made of discrete modes, more or less of equal strength. In the temporal domain, it shows the sequence of pulses. Normally, these frequency comps are realized in low. So frequencies, they connect, let's say, optical part of the spectrum with the much lower frequencies in a coherent way. But Ted Hensch was from the very beginning very much in trying to do it with extreme ultraviolet, and in particular, he wrote a paper, first paper of high harmonic generation about interference of two harmonics generated by two sources with Anne Lurie many years ago, but very important paper showing coherence of high harmonics. And this is the first paper in Nature or Science, I don't remember, Nature, in which they demonstrate indeed, together with Ferenc Krauss and together with Thomas Udem, they demonstrate using this very sophisticated way of build-up spectrometer to separate harmonics from the fundamental. They have created frequency comp in extreme ultraviolet using ideas that was explained by Anne. Nothing would be possible, and these ideas are very much similar to the ideas of church pulse amplification, which was awarded the Nobel Prize for Gérard Mourou and Donna Strickland in 2018. Arthur Ashkin, who unfortunately passed away, got it for optical tweezers, which are now used for quantum simulators of Rydberg atoms. I don't know if Misha will be talking about it, but it's possible. But anyway, this church pulse amplification is, in principle, simple, like all the ingenious ideas are simple. You take a pulse which is short and strong. You use gratings and chirping to stretch it so that the intensity is smaller. You amplify it when intensity is smaller, and you compress it in time, having a pulse which is much stronger and still sharp. And this is the idea of high harmonics. I have a few slides, but she has reduced it to one, so I don't have to explain it anymore. But I will tell about this because this has not been discussed. The physics behind this generation of harmonics is very well described by the so-called three-step model. So electron tunnels out from the parent ion when the electric field is very strong. So it gives this linear field of the potential. The oscillation of the fundamental laser are slow in comparison to the electrons, 10 times slower or even much more, depending on the wavelength you use. Then the electron is accelerated in the continuum, and then turns back and comes back to the parent ion, and here it can recombine, producing high harmonics. And this was proposed by Paul Corkum and independently by Ken Kullander with his collaborators. Unfortunately, Ken has passed away also in 2024. We have proposed together with Philippe Balcou, Misha Ivanov, Anne, and Paul Corkum, a kind of quantum description of this three-step model, which was very successful because it's easy to apply and to experiments and so on. So in the celebration of PhysRev A a couple of years ago, when they were saying the most cited paper in PRA was this one exactly, which now has over 5,000 citations according to Google. And this brings me to Nobel Prize that we have heard about, to Pierre Agostini, Ferenc Krauss, and Anne Lullier. I mentioned these names on the side of people who also played important role in achieving all this attosecond physics. How do we do attosecond pulses? Anne has explained. Either we take longer pulses and plateau in the spectrum of harmonics, or we take photons from the cutoff region of the spectrum. And the attosecond pulse trains were first maybe predicted by us in this paper, where we point out that in principle, in order to have an attosecond pulse train, harmonics must be emitted in locked-in phase. But they are not, because they are produced by different electronic trajectories and everything is very complex. But the propagation effects or even focusing effects may select single type of trajectories, and that leads to generation of attosecond pulse trains. This is a famous paper of Pierre, where I don't have to explain what rabbit was because Anne has done it already fantastically. The attosecond pulse train that he was able to measure in this pioneering Nobel Prize-winning experiment was 250 attoseconds. And this is, I have to mention my Italian colleagues for Politecnico Milano, Mauro Nisoli, Sandro De Silvestrius, Orazio Svelto, who had the fantastic idea that if you have a strong and short pulse, you put it into a hollow fiber, and then this pulse doesn't lose much intensity, doesn't lose coherence, but becomes even shorter. And this way you can create pulses that have 2 cycles or something like that. In this first paper, I guess they produced a 10 femtosecond pulse with the photons of T times 7. And this has led to this famous generation of single isolated attosecond pulse by Ferenc Krauss. The duration of the pulse in this first experiment was 530 attoseconds, and the technique to measure were very similar to the ones that Anne was explaining. So this brings me, well, I had an honor again to participate in this ceremony, but okay, it's funny in this penguin dresses. And recently we are very excited about quantum electrodynamics of quantum of harmonic generation. So what we do, we put, let's say, coherent state on the target, we look what comes out, and then we measure it after some tricks by conditioning of the production of the harmonics and some other aspects. Anyway, the effect is a kind of superposition of 2 different coherent states, and this is a Schrödinger cat state. So if you don't do anything, you have this, Wigner function, which is Gaussian. If you do something, you have a beautiful Schrödinger cat. Okay, let me tell you that this brings me, sorry, I need a few minutes, to the Nobel Prize of Serge and David for generation of Schrödinger cats. Here is a famous book of Serge with Jean-Michel Raymond, where you can learn about it. And the Schrödinger cats in particular are good for quantum metrology here of electric field. And okay, another kind of states which lead to very strong quantum correlation and can be also used for metrology are the ones that discovered or demonstrated by Alain Spee, John Clauser, and Anton Zeilinger. Some names of important people are around here. And the first violation of Bell inequality was in Delft. But there was soon 3 independent observations by Anton Zeilinger, by Paul Quiet, and by ICFO. The most important thing of ICFO was contribution of ultra-fast quantum random number generator, which is essential for being sure that when you violate, you use true randomness. This is a picture from Alain's article in Physics. And this brings me, well, we work on that also for years, but doesn't matter. This brings me to the last Nobel Prize I want to mention, on detection of gravitational waves by LIGO and theory by Kip Thorne. I mentioned some important names on the left. And this is, why is it important for us? Because it is nowadays, LIGO surpasses the quantum limit using squeezed light. And this is due to pioneering experiments by Jeff Kimball. So with this sad picture of Jeff Kimball, who passed away in the last year, I want to finish this talk. Thank you. Thank you for being tolerant.
Showing how deep and general is the activity that we do. And as an Italian, I would like to thank you for the many Italian flags.
Well, that was on purpose. I know where I am.
Now we have questions, comments. You should ask him who will get the next Nobel Prize, because we do new work which is.
No, I have no guess.
Let me say that I appreciated everything, but I also would like to mention that you very well illustrated those magic days when the Bose-Einstein condensation was announced, and in the next days it will be the 30th, anniversary.
Yes.
And just for after your consideration on laser cooling to achieve the BEC, I just remember, maybe with Guglielmo was there in Capri, the talk before, just before the Eric Cornell presentation, given by a French, had exactly this title: Is it Bose-Einstein condensation possible?
Yes.
So really, and also,
Deep question.
yes, and also your work that how to detect the Bose-Einstein condensation with ultra short pulses, all these efforts that we didn't know how to detect the Bose-Einstein condensate. So this really, you gave an important picture of that fundamental achievement together with all the others.
With others, I mean.
So thank you, Maciej. Dziękuję.
Dziękuję bardzo. Now is a break.
We have 10 minutes before the formal coffee break, so I suggest, together with Saro, to anticipate the coffee break and come here 5 minutes before the starting the lecture by the lecture by Alana Space should start at 11:20 if possible. So we are in time for the next remote talking.
Esatto. Niente, 2-3 secondi, sa che mi sono. Il video dove è stato? Allora si è fatto male. Invece Zacchete Sound mi ho accesso ai volumi dei microfoni o no? Ai volumi sì? No, perché volevo regolarmi i 2 gelati che sono un po' bassi. Everything okay? Yeah, so far so good. Let's see. Hey, 1, 2, hey. Hey. Hey, 1, 2. Come sei? Ovvio, che monade. Ti hai dubbi?
Scusa.
No, perfetto. Aspetteremo per le sorprese.
Magari no. Che vita piatta.
Esatto, sempre sorprese, se no emo. Ciao. Un PC audio no, perché è notebook. Sarà da tenere de 8 il room PC audio quando facciamo Zoom. So che non mi senti, ma non potete rispondere, quindi. Sir, your laptop?
That's it, no?
Yeah.
No, so far.
Thank you.
Do you have an adapter for USB-C?
On peut parler en français.
Ah bah oui, bien sûr. Ah, c'est pas vous, je croyais que c'était le technicien qui venait.
Non, désolé, je vous dérange pas.
Ben, là, je suis en train de préparer ma présentation quand même, mais dites-moi rapidement.
Non, c'était juste... Merci beaucoup parce que le travail de vulgarisation que vous avez fait.
Ah ben oui.
Et même avant le prix Nobel.
Oui.
Parce que pour moi, vous avez vraiment été
C'est vrai.
une des personnes qui m'a
ça me fait
qui m'a donné le goût de la physique et je voulais vous remercier pour ça.
Vous me faites un grand plaisir de me dire ça parce que je pense que c'est important.
Oui.
C'est important de motiver. Et bien sûr, après le prix Nobel, je fais encore plus, mais j'ai toujours pensé que c'était important, oui.
Donc voilà, je voulais vous remercier.
Merci beaucoup. Vous êtes qui?
Paul Herbert.
Et vous êtes ici ou...
En fait, je suis à l'ENS Paris-Saclay.
Oui.
Et c'est que je fais mon stage à Sissa, donc juste à côté.
Oui, très bien. Bon,
donc,
très bien. Oui, bravo. Merci de me dire ça, ça me fait un grand plaisir. Bon, je ne sais pas où est le technicien, il va falloir trouver quelque chose. Qu'est-ce que c'est ça?
Hello.
Good. Do you have an adapter for that?
Please. Okay, so
I have to authorize.
yes, sure.
Voila.
Okay, and you're on already.
Yes, okay. Let me make a maneuver because you are going to be surprised. Now, there is a bug, but I know how to fix the bug. There is still a bug, and I know how to fix it. And now that's it.
Wow.
You know, you should know that. If you have this kind of problem, you change
2 times.
2 times. You say changer d'affichage, change the projection.
Yes.
It change 2 times, and then it works.
And then it works. It's the magic secret. It's like when you use a USB stick.
No, I use that.
No, I mean, when you use a USB, the first time doesn't work. The
Okay.
second doesn't, and the third, it does.
Okay.
So,
And here I use the pointer on
yes. You can transform the pointer in a present. Oh, perfect.
I do it with that.
Perfect. Okay, now you are on.
Bonjour, bonjour. Voilà.
Wait.
It's better to remove that, otherwise it makes noise.
Yes.
Thank you.
You're welcome.
Perfect. You don't have water because.
Water. There you go.
Ah, okay, excellent. Because sometimes it helps.
Yeah.
So let's start with the technical communication. After the second talk, you stay here because the photo of the group will be taken here after at the end of the session. I mean, I'm rather glad on how we started, and I think that also the continuation of the conference will be at the same high level. And now we start from the doubts of Einstein to reach the quantum technologies with this non-locality in action. And just to introduce Alan, Professor Aspe, who also...
Wolfgang.
Who also is, just to go back to the beginning of today, he also is a member of the Academy, who was the Lincei, which organized this conference. Then I want simply to mention that during the coffee break, somebody told me that somebody made the following comments. This conference is a sort of a Nobel condensation. Which means that you are bosonics. All of you are bosonics, I think.
Depends, not all of us.
Alan, to you.
Merci. Grazie. Well, it's a real pleasure to be here. It's not my first time, and each time I am impressed by the variety of people, and also it's a famous place. So it's an honor and a pleasure to be here, and thank you for listening to this. So I think that my subject is right in the title of the conference, From Foundation to Emerging Technologies. Yes, I will start with a fundamental question raised by Einstein long ago in 1935 and show how progressively it evolved into an experimental question, because physics is not only theory but also experiment. And to my surprise, years later, some smart people found that there was a possibility to apply these concepts for nice, smart applications. Okay, so how did quantum technology emerge? There was first the discussion in 1935 between Einstein and his colleagues Podolsky and Rosen and Niels Bohr, and then Schrödinger, who added a nice grain of salt as usual. Schrödinger was especially smart in saying that he was writing a paper not in the hope of clarifying the subject, but in the hope to show how complicated the subject was. And then 30 years later, or 29 years later, John Bell added a fundamental step. We will see that. And finally, another 2 decades, and Feynman launched the idea that entanglement can be used for something. So entanglement is more. Okay. And entanglement is indeed at the root of many quantum technologies. Okay. So, are we living a new quantum revolution? I will not answer fully the question. I will partly answer the question. So let us start with the Einstein-Podolsky-Rosen-Bohm Gedanken experiment. Why Bohm? Because Bohm is the man who understood that it was good to state the problem with observables which are discrete, which have only 2 values. Remember that. If you remember only one thing from my explanation on Bell's inequality, when you find people who tell you, oh, Bell's theorem is not true because look, I have a classical model violating Bell's inequality. The classical model is not about 2-valued observables. So, and Bohm is the person who understood that you need 2-value observable to have the full flavor of entanglement. Okay, what was the question that Einstein was asking? It was the following. Quantum mechanics give with the Born rule. We heard about the Born rule. The quantum mechanics make statistical prediction. And Einstein had no problem, of course, with statistics. His paper on the Brownian motion is wonderful. But he thought that the fundamental theory cannot be probabilistic. So he thought, in a sense, that quantum mechanics was like a statistical theory of an underlying level where things would evolve, like when we use Boltzmann description for the velocity of the molecules here in the room. We have no doubt that each molecule has a velocity and bounce on each other. And so Einstein thought that there was an underlying level to discover. And he made all efforts to demonstrate that there should be an underlying level. And there was a first famous discussion in 1927 in the Solvay conference, where Einstein was coming with a Gedanken experiment and say, look, Bohr, here I have an experiment that can measure simultaneously position and velocity better than allowed by the Heisenberg. This proves that there is an underlying level. And each time, Niels Bohr could reply in a perfectly convincing way. And Einstein stopped asking questions about a single particle. And in 1935, he came with a situation with 2 entangled particles, and then, to me, the reply of Bohr is not convincing at all. In 1927, it was absolutely convincing, but in 1935, it was not convincing. I will explain you. So let us start with 2 two-value observable that we measure, which is the polarization of the photon. You know that when you send a photon on a polarizing splitter, if the polarization is along X, it goes in the +1 channel. If the polarizer is oriented like that. If the polarization is Y, it goes in the -1 channel. If it is a classical beam at an intermediate polarization, a fraction will go up, a fraction will go down. But if it is a single photon, the single photon is not split in two. It goes either up or down. And you have to repeat the experiment. And quantum mechanics allows you to calculate the probability to get +1 and -1 if you specify the state of the photon. Now, in the Einstein-Polowski-Rosen-Gedanken experiment, you have two photons emitted simultaneously, and you measure the single probabilities to get +1 and -1, and more interesting, you measure the joint probability to have +1 and +1, or +9 and -1, etc., as a function of the orientations of the two polarizers given by the unit vector A and B. So you measure single probability, you measure joint probability, and up to this point, there is nothing quantum in this experiment except that you have two particles emitted in the same pair. Now, if you have the entangled state, so I don't have to elaborate on the fact that this state, which is a superposition of a pair of photons polarized along X and a pair of photons polarized along Y. Why is it surprising? Because there is no way to factorize that. You cannot say the first photon has a property and the second has a property. It's only the pair who has the joint property to be both XX and YY. And if you think about it, it's as surprising as a Schrödinger cat, which is both dead and alive, except that in a Schrödinger cat, there is more than two photons, okay, which makes a complication. And so with this entangled state, if you calculate the single probabilities, you get same probability for +1 and -1, whatever the orientation. So it looks like ordinary unpolarized light. But when you look at the joint probability, P++ of AB, P++ of AB, etc., now it depends on the relative angle between the two polarizers. So you have cosine square, sine square. And what is remarkable, if the two polarizers are along the same direction, then you have a total correlation. You are going to say 1/2 is a total correlation? Yes, 1/2 is a total correlation because look, probability to have +1 is 1/2. And the joint probability to have +1 and +1 is also 1/2. It means that the conditional probability to have +1 on the second side is 100% if you get +1 on the first side. And to be sure, look, the cross probability, P ± is 0, which means that either you have +1 or -1 and never +1 -1. Total correlation. We are scientists, and correlation, we know how to define a correlation coefficient, and it turns out, the calculation is simple, that if you inject the quantum prediction into this formula, you get cosine of 2 times the angle. And if you take the angle equals 0, if the two polarizers are along the same direction, indeed, the correlation coefficient is 100%. Okay, so now we have a tool, and now we have a situation where there is a strong correlation between two random variables. And as a physicist, I would like to have an image. I know that not all physicists demand to have images, but I am a naive physicist, and I want to have images. And so the question is, can I derive an image from the quantum mechanical calculation, which is done in the space where you describe the two photons? And the answer is no, I cannot make an image because that Hilbert space, or Fock space, whatever you want, but it's a tensor product of the space of the first photon by the second photon, and it's difficult for me to make an image in our ordinary space where we live, okay? And so it's impossible to extract an image from this calculation, but on the other hand, I fully like this statement from Asher-Perez, and Asher-Perez was strictly Copenhagen, the standard theory, but he wrote in his book this sentence that I like very much: quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. And I have a laboratory, I have a source here, I have a detector over there, I have a detector here. I want to understand in my space. Okay. And there is a way to make a quantum calculation a little more involved to get an image. And the idea is the following. If this polarizer is a little closer to the source than the other one, I will first make a measurement here, and then a second one. So I can decompose here. What happens here, and then what happens there. Okay, so the result here, I already told you, can be either +1 or -1. +1 corresponds to polarization X, -1 to polarization Y. Then how do I continue the calculation? Then I go to the Bible. The Bible is your preferred textbook on quantum optics. My preferred textbook is Cohen-Tanuji and Company. So I go to Cohen-Tanuji, and he tells me, just after a measurement, I must project the initial state vector onto the eigenspace associated to that. So if I do the projection, boom, I have XX. Now it's factorized state. But if I find Y, then the projection gives YY. So you see, now I have an image which is absolutely clear. When I do the measurement here, if I obtain X, then immediately the other photon is X, and then of course I get +1, +1. And if it is Y, then the other one is Y, and of course I get -1, -1. And in between, just use the Malus law, and it works also. So you recover all the result of the global calculation, and in addition, you have an image. Nice? Well, it seems that the measurement on the first photon seems to influence instantaneously at a distance the state of the other one. We call that non-locality, and this, of course, was unacceptable for Einstein. So keep in mind that the basis of the reasoning of Einstein, Podolsky, and Rosen is the fact that the two measurements are far away from each other, and because they are far away of each other, they can be what we call space-like separated, so nothing should connect the two measurements. Okay. And so this image is not acceptable by Einstein, and Einstein suggests that there is a way, which is extremely natural, is to introduce supplementary parameters. From the beginning, the two photons have a property that will determine that this pair will give +1, +1. That pair will give -1, -1, and then you complicate the model, okay? So that's the idea of introducing a parameter from the beginning determining the result. Okay, so it's image simple and convincing thing of twin brothers, okay, who have the same color of eyes, etc. And because they have the same chromosome, so it's an image which is convincing. And Bohr disagreed. Why did he disagree? Because Bohr had the strong intuition that when you add anything to the standard formalism of quantum mechanics, it will no longer be fully consistent. But I say add the intuition. And if you read the reply of Bohr to Einstein, I am sorry, but it's more epistemology and philosophy than physics demonstration. It's not a criticism. We are on different ground. And to make a long story short, and you are allowed to disagree with me, but my vision of that is if you accept the epistemology of Bohr, that an object has no physical reality in itself and that the physical reality depends on the way you observe the object, then you are convinced by Bohr. But if you are on the side of Einstein, who says an object has a physical reality independently of the way you observe it, then you are convinced by Einstein. And that's it. What happened after this debate of 1935? Nothing. Nothing. Because most of the physicists do not care. They do not care first because quantum mechanics accumulates success. Also, they have heard of the discussion of 1927, and everybody is convinced that Bohr replies satisfactorily to Einstein. I heard that many times when I embarked in the subject and said, but you know, Bohr replied. I say, yes, he replied in 27, but not in 35. His reply in 35, I disagree with I'm not convinced. Disagree is not disagreeing, but at least I'm not convinced. And more than that, when people thought a little bit about the debate, there was no discussion about the correctness of the prediction of quantum mechanics. Einstein need not argue against the result of the calculation. He wanted to have a supplementary interpretation, that's all. So physicists did not care, okay, until John Bell came on stage. John Bell said, let us take seriously the idea that you have supplementary parameter lambda, and then you need to have a model where once you know the lambda, you must say what is the probability to get +1 and -1 once you know lambda and the orientation of the polarizer. And once again, I insist, when somebody comes with a model, check that he has a model that can give only two values, either +1 or -1. Otherwise, it does not fit into the reasoning of Bell. So you have a similar function on the other side. Then you describe the distribution of the supplementary parameters. And once you have that, you can calculate the correlation coefficient. An example where the two photons would have the same polarization, whatever it means, okay? And then you invent a response function which tells you that if the polarization is along the axis, you get +1. If it is perpendicular, you get -1. And when you are in between, you put a frontier at 45 degrees. Makes sense. And with this, you have a beautiful result that the red line, which is here, you have full correlation at 0, full correlation at 90, and in between, you are never too far from the quantum prediction. And so you can legitimately ask the question, this model is so naive and so simple, probably there is a model with more sophisticated functions, special function, I don't know, Hankel, Bessel, whatever you want. There is probably a more sophisticated model which allows you to mimic, to reproduce all the prediction of quantum mechanics. In fact, it is not the case, and Bell's theorem is the fact that no, there is no way, it's a no-go theorem, there is no way to reproduce all the prediction at all angles of the quantum mechanics with a model involving lambda, etc. Okay? There is no local hidden variable theory in the spirit of Einstein's local realism, I will comment about that later, that can reproduce quantum mechanical prediction at all orientations. I just give you a flavor of the Bell theorem, but I will not do the demonstration because I have only 40 minutes. I know that in 40 minutes I cannot do that. But if you ask me a question at the end, I can show you it. Yeah? Okay, so Bell's theorem tells you that if you can calculate the coefficient E, correlation coefficient, by introducing the lambda, in the spirit of Einstein's idea, then there is a quantity S which is restricted to be less than 2 or more than -2. And this quantity S involves two orientations for the first polarizer, A and A prime, and two orientations for the second polarizer, B and B prime. So you measure AB, AB prime, A prime, B prime, A prime, B. And you make this spatial combination with 3 plus and 1 minus. Why 3 plus and 1 and minus? I don't know. But probably the only answer is Bell was a genius. Or he tried so many things that at the end he found the interesting case, okay? And then remember the prediction of quantum mechanics. Consider this set of angle pi over 8, so 2 times pi over 8 is pi over 4. Cosine of pi over 4 is 1 over root 2. So you get 1 over root 2, 1 over root 2, 1 over root 2. And here, because the angle is bigger, the cosine is negative, and you again have 1 over root 2 here. And so you have 2 root 2, which is obviously bigger than 2. So that's it. That's Bell's theorem. You know, that's the importance of Bell's theorem. You have some prediction of quantum mechanics that you cannot describe with such a model, period. Okay, so the possibility to complete quantum mechanics is no longer a matter of epistemology, of taste, call it, no, you name it. It has turned into an experimental question. So this demonstration of Bell's theorem, I will go over it. Well, between you and me, it's not more complicated than high school physics, okay? High school mathematics, at least when I was in high school, okay? Now, very important point for me. Bell locality condition. To demonstrate Bell's inequality, you must be sure that the response of this polarizer does not depend on the other one, okay? Similarly here, and you must also makes the hypothesis that the way in which the lambda are distributed in the source do not depend on the arrangement of the polarizer. You are going to tell me, obvious. No, it's obvious for the physics that we know. But maybe there is an unknown interaction. Why not? And so this is a reasonable hypothesis, but Bell insists in his paper that it is only an hypothesis unless you can do an experiment in which you change the orientation of the polarizers while the photons are in flight. Because if you change the orientation of the polarizer while the photons are in flight, there is no time for information on one polarizer to go to the other one. And obviously, when the photons are emitted, they do not know, between quotes, they do not know what will be the orientation. Okay, so I was fascinated by this statement of Bell, and I decided that I would try to do an experiment of that kind. Okay. So in an experiment with variable polarizer, you have a full conflict between the concept of Einstein, the physical reality, and the fact that it is local, that is, things cannot go faster than light. Okay. Experiments. 3 series of experiments. The heroic pioneers, Clauser and Friedman in Berkeley, Pipkin and Holt in Harvard, they found conflicting results. At the end, it turned out that Clauser was right. Clauser repeated the experiment of Harvard a few years later. Fry in Texas repeated, etc. And so the situation there was, the score was 3 for quantum mechanics, 1 for local hidden variables. And it is a moment when I embarked into that, and my goal was not to settle that debate, it was to make experiments with schemes really close to the ideal scheme I have described, because these first experiments were quite different. I don't go into detail. So I did a few experiments. I will show you, just flash a few transparency on that, with schemes closer and closer to the ideal experiment. And the key of my experiment was a source of entangled photon much better than the one of Clauser and company. And then, starting in the 1980s, there was a series of experiments based on a source of entangled photon much better than mine, okay? So mine was much better than Clauser, and Gizeng and company, these people at sources, much better than mine. So it was much better, much better, much better than mine. Okay, and with this I could do beautiful experiments. I will flash something about that. So this is the key of my experiments. I could excite the upper state of a radiative cascade in calcium directly with 2-photon absorption. And once the atom is here, it has no choice. It has to decay here. And in fact, there are 2 paths to decay, emitting sigma plus, sigma minus polarized light, or sigma minus, sigma plus. So you have this, which is already an entangled state. And if you change bases, if you re-express the circular polarization as a function of linear, you get exactly the state that you need. Wonderful. And with this, so it was a complicated experiment, 3 lasers, etc., vacuum chamber, atomic beam, etc. Complicated experiment, but it took me 4 to 5 years to have it working, but then it worked. And with this, I first repeated the experiment of Friedman and Clauser, but repeated in a few minutes rather than in hours and hours and days, okay? Because I had a much better signal-to-noise ratio, and I did something they had not done. I pulled my polarizer far from the source. And the reason was the following. Some people told you entanglement is a property of the microscopic world. So in the helium atom, the 2 electrons are entangled. Oh, fine. But when you go at large distance, entanglement will disappear. So you ask your theorist friend, you say, what is large? He scratches his head, he said, well, coherence length of a photon. Okay, I had a coherence length of 1.5 meters, so I pulled the polarizer at 6 meters, entanglement was still there. So this was the first improvement compared to previous experiment. This was a major improvement. Using 2-channel polarizer. In previous experiment, they did not have access to the -1 channel, you know, like a Polaroid. Polaroid transmits one polarization and absorbs the absorb. So it made the experiment complicated. I could get, for the first time, polarization splitter for my wavelengths, and it was a gorgeous experiment, because in a single run, you get 4 numbers. N plus plus, N plus minus. And so you just normalize your coefficient by the sum of the four things. Just one run, no calibration, boom, you have the correlation coefficient. And with this, we could show that the result of quantum mechanics were vindicated by the experiment, and we got a violation of Bell's inequality by 40 standard deviation, more than 40. So people at CERN know that when you have a difference of 40 standard deviation, maybe it's time to publish. Okay. Last experiment we did, you remember, I wanted to turn the polarizer while the photons are in flight. Well, this is a view of our polarizer. 30 kilograms. You know, you have photomultiplier, shield of copper, of lead, of, well, so very heavy. You're not going to rotate it in a few nanoseconds. So my idea from the beginning was to build a switch able either to let light go or to redirect light towards another direction. Here I have a polarizer in orientation A, here a polarizer in orientation A prime, and if the switch is fast enough, this is equivalent to a single polarizer switching from A to A prime. Same thing on the other side, okay? To make a long story short, I had ordered it, but the company was not able to deliver, so I had to build myself, and just, I like this kind of small details. The problem of the company was that when sticking the transducer on the crystal, because there was variation in temperature, it was breaking because the dilation coefficients were different. And so I was despair because I could not deliver, so I started to study acousto-optic interaction, and suddenly I read in a book that water is a good medium. And of course, if you put transducer in water, you don't have problem of dilation. So I built this with two transducers in water, and it worked. So this is how an experimentalist works. When he is despaired, he has to find a solution. Okay, he or she, of course. Okay, so anyway, it was an experiment more difficult. It took a little more than a few minutes. It was rather a few hours, but just a couple of 3 hours was enough. And then we found a violation of Bell's inequality by 6 standard deviation with changing the orientation of the equivalent polarizer while the photons were in flight. Okay. Third generation experiment, I mentioned it. I told you the source was much better. In which sense was it much better? It was much better because, in my case, the photons are emitted in any direction in space. Non, j'en ai plus que 5. 7 ou 8. He is trying to cheat on my timer. No. I have the chronometer here. Okay. You are a meteorologist, but I have a chronometer good enough. Yeah, I was emitting photon in any direction in space, so you need to have lens to collect them, etc. In the new source, they use a nonlinear phenomena called parametric down conversion, and for people who have worked in nonlinear optics, there is a so-called phase matching direction, which this condition forces, if you manage well, it forces a photon to be emitted in a well-defined direction. And so well-defined that you can inject them into an optical fiber, okay? And with that, of course, you can do beautiful experiments because once the photons are in an optical fiber, you can go far away to make your measurement. For instance, Nicolas is made in '98 an experiment where he was introducing the photon in Cornavin, which is close to the station in Geneva, and he was observing at a few kilometers in a village called Bellevue. I don't know if it is a village, but it's a place called Bellevue, and another one called Bernex, and he found violation of Bell's inequality at 10 kilometers, Nicolas? Okay, like 10 kilometers. Anton Zeilinger, he was in Innsbruck at that time. He had the optical fiber of 200 meters long, but it was long enough that he could launch a random number generator to select the orientation of the polarizer. In my experiment, I was switching as fast as I could between the two orientations. Zeilinger, rather than switching like a crazy, could launch a dice, a random number generator, and choose between the two directions. Okay, in both cases, Bell's inequality are violated, quantum mechanics wins, wins, wins forever. Okay, there is a whole story of loophole-free experiments, and I have no time to go in details, except that I insist this paper was already cited this morning by Maciek, which is the news and views that I refuse to do for Nature. I will tell you only in private why I refuse to do it for Nature, and that I put on Physics, which is the APS journal, free online, okay? And if you read, say, this paper, you will learn that you have to be very careful when people quote the quality of their result with p-values. I don't want to insult anybody, but p-value is good for psychologists or sometimes medical doctors. When they have a sample of 3 people and they want to make a statistic with 3 people, they speak of p-value. We should not speak of p-values, and in my paper here, I convert the p-values of the 3 papers in standard deviation, and then you make your own judgment. Okay. Conclusion is that Einstein's local realism has to be abandoned. It's untenable. What should we conclude? Einstein told us, because he was making a reasoning ad absurdum, and he was telling us, if I was not right, if my image of the world was not the right one, this is what you should accept. And we know now that is not right, because we violate Bell's inequality. So he told us what we have to accept. So these are sentences of Einstein. We have either to drop the need of the independence of the physical reality present in different parts of space. I will comment about that. Or accept that the measurement on the first system changes instantaneously the real situation on the other one. Exactly the image. Well, I see strange things on the screen here, but that's okay. This one is good. So the non-local image that I described, you know, at the beginning of my talk. Okay. The first thing, we call it quantum holism, the fact that 2 entangled objects, even space-like separated, anyway, have a single description. You cannot say that the physical reality of the whole object is the addition of the properties of the first one and the property of the second one. You have more in the entangled system than in the addition of the 2, and these are the root of the power. Ah, that's Federico Capasso who is online already. Ah, because it's strange, you know, he's here. Bonjour, Federico. So quantum holism is at the root of quantum computing. And the other sentence of Einstein, he said either or. The other one is what we call non-locality, and non-locality is at the root of quantum communication. I will just give you a flavor of that, otherwise the chairman will not be happy. Okay, so I just flash an example of using the idea of non-locality. I love non-locality. Non-locality allows me to have fast intuitions of the reason why a quantum technology is useful or not useful. So I just give an example, that quantum cryptography with the Eckert method. You know, I don't go into details, you have heard that many times, Alice and Bob want to communicate secretly, and the spy, the eavesdropper, want to intercept, and there is a mathematical theorem proven by Shannon, which is that if Alice and Bob have the same random sequence of 1 and 0, if Alice uses it to encode and Bob uses that to decode, there is no way to understand the message, provided that the message is not longer than the key, the encoding key, okay? And so the problem boils down to distributing the same random series of 1 and 0 to the both partners at a distance, okay? And quantum key distribution is the solution of that. So in the method invented by Arthur Eckert, he uses entangled photons, so you have a modern source of entangled photons, sending a photon to the left and a photon to the right, okay? And until the last moment, I insist on that, that's non-locality. until the last moment. It can be as well +1 as -1. And at the last moment, if you have +1 on one side, you have +1 on the other side. And if you have -1 on one side, you have -1 on the other one. And because it is at the last moment, non-locality, there is nothing to spy in between. That's the key. This is why I love non-locality, because it allows me immediately to understand. Of course, then you have to make reasoning to prove that if the spy is smart enough, etc. But from the beginning, you can instantaneously see, yes, this is a good idea. Okay, let me continue. And as you know, we heard that there is a program with Trieste, but we have our Chinese friends who have done that from a satellite at more than 1,000 kilometers, exchanging at this distance. Okay. Now, just I flash in 1 minute, Massimo, not more than 1 minute, I flash the reasoning, you know, of quantum teleportation. Basically, quantum teleportation is, I want to teleport the state of that photon. I mix it with a photon nu1 on the beam splitter, and this nu1 is entangled with nu2. I do a measurement here, and the result of the measurement I transmit here by a classical channel, and then, depending on the result of that measurement here, I change the state of the second photon, which is entangled with the first one, which was part of the measurement here. And then this transformation, depending on that, gives me that. And if you think in terms of non-locality, you say, okay, when I do my measurement here, instantaneously the second photon takes a polarization or takes a quantum state that depends on that. But to finish the teleportation, I need, in addition, to receive the classical signal, which arrives here, and it is only after this transformation that I have copied the initial state onto that. Which means that here, I have to put the photon on hold for waiting for the arrival of the classical, which means that I need a quantum memory. And this is why quantum memory is so important. And there is a beautiful experiment of that kind, which was done in the group of Nicolas Gisin, where they use, elementary quantum memory, which is just a long coil of optical fiber, just for waiting the signal of arriving. So remember that when people speak of quantum teleportation, it will work well only when we have excellent quantum memories. Okay. So again, the non-local image has suggested the necessity of a quantum memory. Okay, to finish, do we live a quantum revolution? Remember that the first quantum revolution was first conceptual, we know, 1 century ago. And then with this, people could immediately understand why matter is stable, chemical bond, emission and absorption of light, etc. Then, so 1925, okay, we have all the equations, okay? 20 years later, first technological application. Transistor, 47. Laser, 60. Integrated circuits in the 60s, etc. It took decades and decades, and now it has totally transformed the society of information and communication. When you speak to political people, I do that all the time, explain, or to the public, explain them. It took decades and decades and decades from the first concepts of quantum mechanics to the society of information and communication. Okay, do we have something similar with the second quantum revolution? The concepts are first entanglement, this you have understood, but also the fact, which was signaled already this morning, that we can observe, manipulate, and control single quantum objects. So there are atoms, photons, ions, electrons, etc. And also artificial circuits with superconductors, etc. I have no time to go in details, okay? And then we can ask a question, with this, do we live a new technological quantum revolution? What would it be? Quantum communication, cryptography, teleportation, I mentioned it. Quantum computing, imperfect or perfect, I have no time to comment, but you can ask questions if you want. Quantum metrology, it works. Will the new quantum revolution transform our society? What, by the way, all the time you hear about quantum advantage. What does it mean? Well, many people think only of the fact that the quantum computer could calculate faster or more complicated problem, but there may be another phase to quantum advantage. If you could do with a quantum computer same calculation as with a classical computer, but with less electricity, it would be very important. So this is open. We don't know yet. It's not really fully demonstrated, but there is no proof that it cannot happen, okay? So nobody can answer with certainty. Many believe that there will be something of that kind. So what you have is Europe, France, Italy, of course, and then these companies which have big pockets also, and many, many, many startup companies who are doing extremely well, okay? And to finish, I want just to say that the experiments that I refer to were between 75, our experiments were between 75 and 82, and for these experiments, I had two fantastic engineers. I had two master students at the end. When it was time to collect the data, I say it's time to have physicists to work with me. So I engaged two master students who turned out to be really bright people, because maybe you don't recognize them, but they are Jean Dalibard and Philippe Granger. Really, they came as master students to do the test of Bell's inequality, and so fair enough, I invited them to Stockholm to share with me the pleasure of the Nobel. Thank you very much. Forty minutes sharp. 40 minutes sharp, my friend.
Congratulations, even for your metrology.
Yes.
And this year is also the 150 years of metrology, and quantum metrology is another. So we have time for a comment, a question, two questions, okay? Three, and then we have to go to Federico, who is waiting for us.
I wanted to make a comment, and you started talking about the so-called classical violation of Bell inequalities, which stimulate a lot of discussions. Obviously, I had discussions with another late friend, Joe Everly, very strong ones.
I had a hard time to convince him.
In my opinion, the reason why they can violate inequalities is because they measure two-body correlations directly. There is no Alice and Bob who make their measurements independently and then correlate the results, but they measure the two-body simultaneously, so to say, without separation of systems. So this is not, I think, the problem with the many outcomes of the Bell inequality. Nicolas Gisin has derived a lot of, it's of course best to have two outcomes, but Nicolas has derived thousands of Bell inequalities with many outcomes, and they are equally good to test non-locality, although I don't think anybody has done it so far.
Allow me a comment. Azim Barout, I was in a summer school in Santa Fe in '84. Azim Barout came with his model and say, I have a model which is classical and violates Bell's inequality. And then I look into his model, and his model was on each side, you have a continuous result. And I say, okay, I want now to have digital result. So I have to invent a black box converting the analogous signal of the input into a digital one. And you can calculate what should be the transfer function of the circuit. It should have negative probability and probability bigger than 1. So this is not classical, obviously. So this is why I insist that you need +1 or -1 to have the violation of Bell's inequality. But we, yeah. Okay.
Hi. Would you like to comment on Toft's attempt to restore determinism?
Yeah. Well, it should ask to the people who try. I mean, you know, my vision is simple and naive, okay? But At least for simple and naive model as that, in my PhD thesis, that you can have online, I derive Bell's inequality with non-deterministic model. That is, here I tell you when I have lambda, there is a function which tells you +1 or -1. But I have shown that you can, I am not the only one, but I think it's a clear demonstration in my thesis. You can show that if once you have lambda, you only know the probability to get +1 or the probability to get -1, you anyway get Bell's inequalities. So I don't think that determinism is the main reason for the conflict between quantum mechanics and Bell's inequality. But I'm not a deep theorist, so, but at least this is what I understand.
Alain, maybe that's not so much a scientific question, but I always feel a little bit uneasy to talk about the second quantum revolution. Because the second quantum revolution, because if you look what happens in the 20s and early 30s, within a decade, so much happened. And if we now want to say the second quantum revolution is working with single quantum particles and entanglement, well, we have started to detect single ions, single photons 30, 40 years ago. So if something emerges over 40, 50 years, I think the word revolution is maybe a misnomer.
No, I think it will be a revolution if at one point the technological deriving from this change society. This is what I said explicitly. The first quantum revolution was not only concept, not only transistor, etc., but the fact that we have society of information and communication, which is totally transformed. And we will have a second quantum revolution only if the new applications totally transform the society.
So you would say we are hoping that the second quantum revolution will come?
I don't know when. Probably I will be dead. Probably you will not. But no, but really my speech is clear. We are in the process of a maybe second quantum revolution.
Okay.
It's already conceptual, no doubt. Technological, yes, there are some technologies directly coming from that. And will it change the society? I don't know.
Okay, maybe you go ahead about the
So nobody asked the question about the demonstration. You know, I was once in Princeton, and I asked Duncan to raise his hand. It was arranged between us. He raised his hand and said, "Can you show us the demonstration," which is indeed high school mathematics. I don't. Thank you very much.
I think, Wolfgang, it depends on the definition of a revolution. You know, you have also the revolution of Earth around the sun, so all these are revolutions. However, we have now the last talk of this session, given by Federico Capasso. We thank Federico, grazie Federico per essere qui ed anche per aver aspettato con pazienza, and so you can now give us your talk.
Thank you very much for the invitation, and I'm sorry that I cannot be there in person. Assume everyone can hear me and see my screen. So I'm going to be talking about meta-optics for wavefront shaping, the interesting physics that you can do, and some of the applications. So basically, the key element for this work is the so-called metasurface. What a metasurface is an array of individual optical elements that in general can be conceived as phase shifter that are spaced by a distance significantly less than the wavelength. So if you like, you can call this a two-dimensional metamateria. And it's an interesting way to do wavefront shaping, and you can see this by this picture here, where each meta-atom is designed in such a way to produce different phase shifts Then what you can do is, using the Huygens-Fresnel principle, you can say that the far field will simply be the envelope of the actual wavelengths. So at least qualitatively, you can see then that by engineering the landscape of meta-atoms, you can engineer practically an arbitrary wavefront. This is very interesting from the fabrication point of view. You can realize this simply by lithography, which is widely used for integrated circuits and so forth. You can make optically thin type of structure, compact, and is also the possibility to do some vertical in integration of these meta-atoms. The key point that you can locally design the actual meta-atoms, and you have an unprecedented control of dispersion. What do I mean by that? If I simply take cylindrical pillars, they are all of the same height, and I just change the diameter. What I change is the overlap with the optical field, as you can see here, and so light will see a different effective refractive index depending on the diameter of this pillar. So I can really engineer the dispersion in an arbitrary way. I can overcome the limitation of conventional optics, and for example, if we try to design lenses, the control of the aberration is much easier. Moreover, there is a point that I will stress throughout my talk. You can make metasurfaces that are multifunctional. And this is sort of a vision where this meta-optics will actually lead us. So the key point is you can have an arbitrary control of the wavefront. I will give you quite a few examples of how you can generate arbitrary vector beams. By that I mean structured light and also structured dark. I will explain that. I will show you one interesting application to quantum optics. The key point now from an application point of view, that flat optics, because it can use, and this is the key point, the standard fabrication, semiconductor fabrication technologies of semiconductor chips, okay, it's a new way to produce optics. So there is a convergence between electronics and actually optics. And this is happening right now in our smartphone, in our smartphones, as I will show you. So we are really talking of CMOS compatible flat optics platform for high volume markets. The examples are lens in cell phone camera modules and so forth. So in the next slide, I will tell you about the sort of the actual dark side, the design of optical singularities. Singularities, they occur when a parameter is not defined. For example, at the north and south pole, we have a coordinate singularity because the longitude is not defined. Likewise, we know we have gravitational singularities, and in the optical field, we have optical vortices, where the pointing vector follows a helicoidal path. Okay, so if you look along the axis, you have a vortex of light. The intensity at the center is exactly zero, and the phase is undetermined. So these are on-axis singularities. Now, in my group, we have asked our question, can we generalize this notion to singularities that are of different dimensionalities? So you can think of this, you can describe light as with a complex scalar field with a real and an imaginary part. So if I now look at the two equations, I set the real part and the imaginary part to actually zero. This will be the intersection of these surfaces gives the actual singularity. So we can design, and we have done so, zero-dimensional singularity. In this case, the real and imaginary part touch in one point here. You can make one-dimensional closed singularity, or as I showed you before, you can make line singularities. Finally, you can also overlap these two surfaces these two function on a surface, and you will have a 2D singularities. So the design is quite complex, but I'll give you what the recipe is. For example, we try to design sheet singularities. You have to maximize the phase gradient orthogonal to the desired sheet. I'll start simply with, sorry about that. This is the design of an array of zero-dimensional singularities. Basically, I have a meta-surface with meta-atoms such that I have basically phase sheets here with different phases here. Okay, so I have a cylindrically symmetric phase profile. And that is designed in such a way. In fact, I have 1,000 radial phase values to create an array of equidistant singular points. This shows the numerical simulation here. This is designed with for light at in the near IR 6760 nanometer. And this is the fabrication we use. The platform is titanium dioxide, which is a highly transparent material in the actual visible here, and it's produced in this case by E-beam lithography. You can see the quality of the fabrication is actually excellent. And here are the experimental result, okay? You can see the experimental in intensity. If you take a horizontal X cut or a Y cut, and this is actually the full intensity profile here, and you can see where you have the dark regions here. That's where you have the singular spot. So it's an interesting type of application of creation of singular, and this is the experimental setup. I don't have really time to go in the experimental details. The next question that we asked is, can we make a two-dimensional singularities? Basically, this is a two-dimensional sheet where the phase is undefined. And again, we use the same technology of titanium dioxide nanopillars here. And so optically what we do, we can actually translate the actual setup and try to image basically these cross sections here, these cross sections. Okay, so this is an example of one experimental cross section where we have a heart-shaped singular region here. Now, from an experimental point of view, you see there is quite a bit of background, but I think the point is should be well taken that we are able to design these interesting regions, and in fact, this shows a see-through as we translate the optics here through these singular regions here. You can see, right? So this is interesting. Now, see, when we structure the actual dark, we are not subject to the diffraction limit. We can make arbitrarily small, essentially dark region, dark spot. And so we are now considering that there might be some interesting type of application to use a structured dark to actually probe materials at a scale much less than the wavelength, okay? Particularly, I'm interested in developing a tomography, stress tomography, where essentially the idea is to try to image defects which are at the atomic scale, really. At the all the failure mode of material starts at the atomic scale, then they grow into arrays of point defects, and eventually you form dislocations. So I think there is potentially some very interesting application to material science of structured dark. The next thing we have been exploring, can we structure light along the propagation direction? So in Tereschnica, we design a metasurface where, as we propagate here, the polarization actually changes. Or can we structure light that as we propagate along here, the topological charge of the vortex changes, so you're changing from one optical angular momentum to the other. Now let me stress an important point here. We are not violating, of course, conservation of angular momentum here, because if I integrate, in this case, the spin angular momentum density along any transverse plane, I see that that is a conserved quantity. Only locally in the actual paraxial region, I see an evolution from one polarization to the other. Same thing here. Of course, the optical angular momentum is a conserved quantity, but near the paraxial region, I can arrange things so that the vortex changes size from one value of topological charge to the other. So we have done this experiment, and it's a very interesting way to structure light. And essentially, I'll just tell you the flavor of what we have done, okay? We can, essentially, this is all a game of interference. The metasurface implements a superposition, in this case, of pencil-like beams. They're really bezel beam with different cone angles and different polarization states. So I create essentially a comb of amplitudes which are equally spaced. Kz is the propagation, is the projection of the wave vector along the propagation direction. And so these interfere in such a way to create the desired behavior. For example, these are the experimental data of a z-dependent polarization. So if I move along the optical axis, near the optical axis in the paraxial region, I will see that the intensity fades away for incident polarized light along the x direction in a way that is as if you had a virtual analyzer position, different virtual analyzer position along the optical axis, okay, until you get eventually zero. And if you use the opposite polarization, you'll get the complementary behavior from low intensity to high intensity. The most interesting case where we can use a complex, we now create a situation where light propagates. As it propagates, the vortex changes along the propagation direction. So we have done this for different input polarization. In this case, we have used eigenpolarization that are elliptical. So as I change from this ellipticity to the next, you see I can have a different propagation. In this case, from one optical angular momentum L1 to L2, in this case from L'1 to L'2. So there is essentially infinite possibility of structural light, and we have done these experiments here, okay, to actually probe this behavior. And again here, what is the guiding principle? It's based on spatial beating of harmonics. So what we are doing, we are really creating two comb states. These are comb states in K space, where they are equally spaced in actual K. And one comb is designed from one optical angular momentum, L2, the other one for L1. Then we let things propagate, and these are the simulations. You see, we propagate from one vortex to the other vortex. So it's all a game of destructive interference, okay, that we use. These are the experiments. where we have used two different input polarization. The blue is elliptically polarized this way, the red is polarized this way. So here on top you actually see the experiment. We are measuring structural light along the propagation direction over a distance of basically of the order of 1 centimeter from here to here. So we evolved from one vortex, small vortex, to a large vortex, and here in between we have a superposition of vortex. And this is actually interesting, you know, to start doing some quantum optics, you know, to start to look at this phenomenon at the single photon level. If we now change the elliptical polarization, we have a different evolution of these optical vortices, and these are the corresponding simulations that are in agreement with the experiment. The next. So the key point of metasurface is really the multifunctionality. By designing the meta-atoms, you can achieve an arbitrary evolution, an arbitrary structure of the optical field. And of course, there are quite a few applications that I will mention. I want to move to polarization optics. You know, until recently, polarization optics has not been very different from what the Vikings did using calcite for navigation. The big innovation was many centuries later with Land, who produced the polarizing sheet. But I will try to explain to you how metasurfaces have really created a lot of new possibilities for control of polarization. Let me actually tell you that if you use conventional polarization optics and you try to make a polarization sensitive camera, it is extremely complicated. You have to use either moving wave plates like here, or you have to send light along different directions where you have different birefringent elements and so forth. Or you can use, like the Sony camera, the division of focal plane, where you can have, you know, super pixels here with different type of orientation, but you are only sensitive to linearly polarized light. So we have asked really what is really a fundamental question. Can we do a polarization sensitive camera using a single metasurface to replace all these componentry? Well, the answer is yes. And I want to give you here a short summary of how you analyze polarization. There is this technique of Stokes parametry, Stokes polarimetry. So when you have in general partially polarized light, you have to use the Stokes polarimetry. And this was a major achievement by Sir Gabriel Stokes in 1851. And it's really the first time in physics that a quantity has been defined through a sequence of measurements. It's a very modern point of view, was forgotten after a few years because people really did not understand it, was rediscovered by Chandrasekhar, the famous astrophysicist, who looked back at the old papers of Stokes and said, wow, we can use this technique for many types of applications. So basically, you define the polarization of light through intensity measurements. So you can use an analyzer oriented along the x direction, one along the y direction, and you can measure these corresponding type of intensities here. You can orient the analyzer at 45 and 135 degrees, okay, and you can measure this quantity here. This is the third component of the Stokes parameter. The first is just the intensity. And then you can use essentially a circular polarization filter. You can use a linear polarizer followed by a quarter wave plate. And you can then measure this quantity here, the difference between the percentage of right and left circularly polarized light, and you can define the Stokes parameter. The first is the intensity here. You can normalize everything by the intensity, so you just have these three components, and you can represent them on the Poincaré sphere, okay, where the North Pole and South Pole are circularly polarized light and so forth. Now this is interesting because it's widely used, this technique for polarimetry. See, the modern point of view is now that metasurfaces, because you can make these atoms, these meta-atoms, as anisotropic. Okay, here light sees a different effective index depending whether it's polarized this way or this way. So you can describe this behavior with the so-called Jones matrix, where phi x and phi y are the phase shifts for polarization along the x and the y axis. If you look at the near field, you have different type of polarization. Then what you can do is, how does the far field looks like? And that's where the novelty comes in. You see, normally you use Fourier optics. What is Fourier optics? You say the far field is a series of plane waves along different directions. What are the coefficients? The coefficients are actually scalars. But if we have an aperture, a metasurface, where the polarization is structured point by point, you cannot simply use traditional Fourier optics. And so we introduced in this paper here what we call matrix Fourier optics. So that it's a very powerful generalization of Fourier optics. In fact, when we conceived this, we went to speak to the father of Fourier optics, Joe Goodman, who works at Google as a consultant, and he just gave a thumbs up. He says, Federico, go ahead. This was enough for us. Okay, so essentially what matrix Fourier optics is the following. The far field is now still a plane wave expansion, but the coefficients are what? They are Fourier transform of the Jones matrix in the aperture. I said locally you can describe the metasurface by a Jones matrix. So that you take a Fourier transform of these, and these are really the coefficients of these plane waves. So depending on polarization, the coefficient has a different value. It is a matrix. And we use that to do what? To actually create a new kind of Stokes camera, which answers the question, can we use just a metasurface, essentially, to analyze point by point the polarization of a scene? And this is very simple idea conceptually. We have a metasurface grating where we design 4 diffraction orders, and each order acts like an analyzer for a given polarization of light. What does that mean? Assuming I have light which is oriented along a certain polarization, this is a designed polarization. Then as I change the incident polarization, the intensity of the diffraction order will follow Malus' law, the conventional law of analyzer. So here you see the novelty is the diffraction order acts as analyzer for the incident light. So we create a periodic structure here of where each unit cell is a metasurface. And then it's very simple. We analyze the scene is analyzed along different polarization. So on the CMOS sensor, we have 4 different images analyzed along different polarization. And then what we do a process called co-registration. We overlap point by point these images here, and we have the full polarization information of the scene. This is a dramatic simplification of existing cameras. I'll show you one application here. From these we can derive all the important points like the azimuth of the polarization. So this picture here gives you the azimuth of the polarization. These here you see are the 4 images, intensity images on the CMOS sensor. This is just the 0th order, the light that goes directly through. And so let's see if I can, as I'm rotating this, you can see that because I'm seeing polarization point by point, the azimuth, I see depth. I get a much greater feeling of the depth. Okay, so that's what polarization can give you. See many more details and also give you depth type of information. So we have used this to do a number of interesting things here. Okay, we have analyzed the situation where you have water here, right? And if you take a polarization picture, you see far more details. You see very clear, even a small amount of actually liquid. We have looked at cars turning in a parking lot here, and so forth. And you can also measure the degree of polarization. So I now want to give you one application to quantum optics. We all know about linear quantum optics, okay? And the actual challenge of linear quantum optics that using conventional optics required an intricate arrangement of many component and bulky system. So the challenge is you can use integrated for photonics to simplify this. And I'll give you now one recent application from my group of what we can do. And here I want to go back to the basics of quantum optics, the famous Hongu-Mandel interference experiment, where we use two photons. We have a beam splitter 50-50. We have one photon here in this mode and one photon in this mode. And we are asking, where do the photons appear, basically? And this is a famous result in this paper here. You have to look at the different amplitude, okay, of where the photons can actually go. Two photons can go here. They can also go here to the right, but you can have this here. And if you now calculate, these diagrams here, you will see that this here actually cancels out with this here. So you are left essentially with a linear combination of two photon states, where the photon states go here or they actually go here. The experiment is a famous one. You vary the delay between these photons, and you can observe this so-called Hongu-Mandel dip, which basically tells you that there is a cancellation of amplitude here, and actual two photons, can only go in this direction here or in this direction here. So we have asked ourselves, what can we do with metasurfaces? So this is what we call generalized Hongu-Mandel type of a setup here. The aim is to generalize the Hongu-Mandel interference phenomenon to multiple output modes here, right? So, to essentially engineer the correlation, the actual correlation landscape using a single optical element, which is the actual metasurface. So it's a design of these diffraction orders in such a way to produce interesting coincidences and anti-coincidences. And this is the actual setup, which is quite conventional. We have a photon pair creation and synchronization. We can vary the delay between the actual photons, okay, and we can test the interference. So we have looked at the equivalent of the beam splitter type of experiment with two diffraction orders. And then we have said, well, let's look at this more interesting case where we have multiple ports here. And these are diagrams to actually better understand what we have done. And this is an example of the equivalent of the beam splitter, where we are looking really at the correlation between the diffraction order. So this shows, you see, you have a Hongu-Mandel type of interference here, with a minimum here that is below the actual classical limit. This is the comparison with an experiment done the traditional way using a polarization beam splitter. So you can see you can go well below the classical limit. This is the reference experiments done with a polarization beam splitter. More interesting is what we can do with multiple diffraction order. So here we have engineered things that on these two diffraction order, -1 and +1, +1 and -2, we have Hongu-Mandel interference here, but on the other diffraction order, and so for other diffraction order, but for other diffraction orders, we actually have an anti-coincidence here. We don't have Hongu-Mandel type of interference. So I think this, with metasurfaces, we can make a new class of multiple output kind of interferometer, which can be used to make interesting quantum gates like Hadamard gates and so forth. It's just the beginning of this direction of work that I wanted to give you. And finally, I want to go quickly in application. You know, we realized many years ago that we could make an actual flat lens using meta-atoms. And the idea is very simple here. You arrange the meta-atoms in such a way that all the rays constructively interfere in one point. So basically the meta-surface must be phased, simple type of equation here, to compensate for the phase difference between any ray and the chief ray. So almost with no calculation, you know this is what you have to design. What is the beauty of this? That this lens is automatically without third order type of aberration. There is no spherical aberration, there is no coma, and there is no astigmatism. Here I'm talking, of course, for normal incidence. If I come at different incidence, I will still find coma. So we designed the meta lens sort of to, you know, to design the phase point by point, okay, so that I have a 0 to 2 pi phase coverage. And so we wanted to prove one thing, that we could make large meta lenses, 10 centimeter diameter, using the standard techniques of semiconductor manufacturing, which is deep UV lithography. Why is this important? It's important because this can lead to unify two industries. Semiconductor integrated circuit and optics, because the same foundries can fabricate the optics and the chips. So the first lenses were glass lenses where we focalized diffraction limited light in the actual red, okay? And these, you have 160 million nanostructure per lens. The next is to make a 10 centimeter lens. As you see here, we have 18 billion glass meta-atoms. And again, this is the significant, and I would say that industry has taken notice of this possibility. Here I can show you a meta lens, which is 10 centimeter diameter. If I use a refractive lens, it's much more bulky, thicker, and the control of aberrations here is really critical. Okay, I'm almost finished, Massimo. So there's clear advantage to go the flat way, the flat optics way. These are the characterization of this light, and we decide, I have a student who is good, he likes to look at the sky, so we decide to look at take images, some interesting images, by mounting this meta lens on an actual telescope. This is the images that you get from the nebula. I don't claim that we did really any quantitative analysis of these pictures, but that tells you that you can certainly get images which are competitive with what you get with classical optics. This is the surface of the actual moon. Again, we used our meta lenses. We had a filter because this meta lens is designed for the red light. Here we look at the sunspots, and we looked at pictures from NASA on the same day. You can see we can get pretty high quality images of what these sunspots are. This is our technology, and this is with conventional optics. And finally, we took advantage. My student went up to Vermont to take an image. We have the total solar eclipse, and you can see even a solar prominence. This is basically plasmas that are ejected sort of in kind of loops. So the message is you can get really high quality imaging with actual meta-optics. And the last stuff is, a few years ago, I realized, we should start an actual company, because the merging of optics and electronics can be exploited for high volume type of applications. So I started this company, MetaLens, in 2016. And so what's the idea here? The idea is, first of all, to use mass manufacturing. There are many semiconductor foundries in Taiwan, South Korea, Singapore. So the key difference here, we enter, instead of an electronic design file, an optical design file. And this, in fact, is a 12-inch wafer, okay, with 7,000 metal lenses made of amorphous silicon for wavelengths around essentially 900 nanometer. So, and then you can separate them, you can go different ways and so forth. So, and this is now the thing. If we take a conventional, this technology is being used now by MetaLens and is manufactured over a large scale for application of face recognition. In our cell phones, there is a face recognition system that uses vertical cavity surface emitting laser. These are arrays, like a few hundred lasers that project on your face actually many spots, and then you analyze the reflection for face recognition. So if you look at the standard camera module for face recognition, you see multiple plastic lenses. So this is a different technology than the actual chip, which is semiconductor. And you have a diffractive optical element, so it's quite complex. Here we can do away with all this complication and just use a single meta-optics. So this is really a game-changing type of application. And in fact, MetaLens is now teamed up with a foundry, one of the major foundry, which is UMC, to bring to actually market for applications of this face recognition in payment kiosk. Like there is this company that makes a system called Dailu Sense, based in China. And now I can say, although I'm not allowed to tell you which phones, that the MetaLens is fabricated by MetaLens are in 2 brands of actually smartphones. So this is very encouraging for high volume optics. And again, it's based on the convergence of optics and electronics manufactured with the same technology based on deep UV lithography. And so I'm at the end. I want to thank you. I hope I highlight what are the key advantages of flat optics. You can engineer the wavefront in arbitrary ways. Using this convergence, now foundries can manufacture the camera sensor and the lenses using the same technology. So we are talking of CMOS compatible flat optics. I didn't have time to talk about what AI can do for optics. It can do actually a lot of things, and we've started to actually play with it. And I want to end by acknowledging my many collaborators, students and postdocs and colleagues, Professor David Miller, Professor Steve Johnson, MIT, and recognize funding from the Air Force Office of Scientific Research. Thank you for your attention.
Thank you, Federico. We have comments, questions? Yeah.
Hi, thank you. I have a just technical question on these meta lenses. Can we use these meta lenses as a tunable focal lenses in real time?
Well, it's a very interesting question. We are actually trying by various means. Okay, I would say we haven't done this. The key is to find a phenomenon that you can have a significant change in focal length, and that is not an easy thing to do. I mean, we are experimenting with the electro-optic effect. If we can vary the refractive index, by applying an electric field, we can achieve tuning. I would say it's not an easy way. It's certainly doable. Whether this can lead to an interesting technology, I'm not sure. I'm kind of skeptical, okay? We are also trying, using liquid crystals and things, but it's very exploratory work, and I don't see any type of application anytime soon.
Okay, thank you. And what exactly the parameter you are planning to tune or play with? If you go on...
Basically, you're using the linear electro-optic effect. You can change the refractive index, and by changing the refractive index, you can achieve tuning. Okay, the challenge when you do the tuning is actually, to make sure that you can maintain the diffraction limit, because one of the pluses of these meta lenses that if you design it, as I said, you automatically get a diffraction limited spot without any third order type of aberration, which is one of the advantages. Now, when we do the actual tuning, it's not easy to maintain this aberration-free behavior, basically.
And sorry, just one more question on aberration. You said there's no aberration. Do you correct them or?
Well, no, the aberration, I'm saying, if you design a meta lens correctly, what you can show for normal lens incidence, okay, that you have obviously no spherical type of aberration, you have no coma, and you've no astigmatism, a normal incident. Now, if you try to do this tuning now, it's difficult to maintain this aberration-free behavior. So, I'm skeptical about the way. Basically, let me put it a different way. We have not figured out a way to do significant tuning of the focal length. We still are thinking about it, but I'm kind of skeptical.
We have now one.
So thanks for the interesting presentation.
2 and 3.
I'm just curious about the aberration control. Maybe you mentioned and missed. And for example, about with single sheet meta lenses, if you look at that photo of the North American nebula, we noticed quite a lot of off-axis aberrations near the corners. And is it because it's not tuned, or they can be fixed? And also,
that is a very interesting question. Okay, I showed first the result of a 1 centimeter lens, and that you get a diffraction limit as far as you. What happened is on the 10 centimeter lens, we had to use 2 different reticles. It's a long story. Okay, if we had it manufactured by a company outside, it would have cost a huge amount of money, which we didn't have then. So we did the center. We used two type of reticles. For the center part, we used high quality reticles made by company at a reasonable cost, and for the rest, we use another reticle which is homemade. Okay, and because of this, okay, you can see that there is significant type of axis type of aberration. The center of the lens is a much higher quality, significant higher quality than the outer region. And so in fact, the diffraction, the spot for that 10 centimeter lens is not quite diffraction limited. And as you correctly pointed out also, there are significant off-axis type of aberrations. Okay.
Okay, thanks. And also,
basically, the manufacturing was not the actual best. Okay, because of the constraints that we had then.
And does it work equally well in broadband? like when you have multiple
Very
wavelengths?
interesting. These are all very good questions. Yes, this is a key thing because we wanted, you see, as you well know, if you use traditional refractive optics, you have to use multiple lenses, okay, to do broadband. And that is fundamental to refractive optics. With meta-optics, we have shown that you can make single lenses that are broadband. By broadband, I mean there are diffraction limited across the anterior visible. There is a caveat, however. Okay, this is based, essentially you can analyze them then with Fermat's principle, and you have to look at the arrival of photons. All the photons across the whole visible have to arrive at the focal length with the same time, and the wave packets have to maintain the same shape. So if you try to make a lens which is a reasonable size, millimeters and so, you have to work very hard. So we have made this achromatic lens only for small diameter up to 50 micron. So the next step we said, maybe can we make a good RGB lens for only the primary colors where we have achromatic behavior, and we have been able to do it for 1 centimeter lens. So we have to use inverse methods and eventually AI to actually try to design. The challenge is, can we make a large lens, let's say 1 centimeter diameter, which is achromatic across the anterior visible, diffraction limited. We haven't done yet. I don't think there is a showstopper, but it is a significant challenge. We have only been able to do achromatic large lens only for the primary color, RGB.
We have the very... You want to say something?
Oui. I have a microphone, so... Hi, Federico. This is Alain Aspect.
Hey, good to hear from you. Long time no see.
Yes, same for me, because of reciprocal trajectory of light.
Yes.
It is tempting to ask you the question, in which features do your meta-lenses differ from system-based either DMD or liquid crystal or etc.? Because at the end, all that is a kind of holography, okay, in a sense.
Yeah.
So what are advantages and disadvantages of meta-lenses compared to DMD, SLM, etc.?
Well, let me make it a bit simpler in the following things, okay? It allows you, for example, I showed you, if one uses a camera module, and we have the proof for this thing that is a product right now, it's a camera module for face recognition system, which is designed for one wavelength, 940 nanometer. This is, for example, the system that is in phones like the iPhone, okay? The camera module with the conventional lenses, first of all, you have to use plastic lenses. So it's a different technology than the CMOS sensor. So making the lens with lithography, which is a very new thing, we are the first doing this, and it's already commercially available, gives you a simplification of the whole fabrication. Second, you can make the lens much simpler because of this control of the aberration. Instead of having 3 plastic lenses for face recognition camera modules, you have a single one. So it's the overall simplification of the technology due in good part to the easier control of the fabrication. You can have the optically thin. Moreover, there is an aspect that I didn't have, Alain, time to cover. We can make multifunctional metasurfaces. This is a very interesting thing. You can design them in such a way that depending on the incident polarization, they achieve different function. One polarization gives you a lens, the other polarization gives you the creation of a particular beam, like a vortex beam and so forth. We have also shown you can make meta-lenses that for different wavelengths, they have different focal lengths, and they focus in one case a Gaussian beam, in one case a vortex beam, depending on the wavelengths. You can also do this by changing the K vector, the incident direction. So you can manipulate with metasurfaces vector beams in a way that simply you cannot do with SLMs. SLM is simply limited to scalar optics, basically. It's difficult to control polarization in an arbitrary way. So I guess this multifunctionality of metasurfaces is something very important, in my opinion, for many types of applications.
Thank you, Federico. It's really fascinating. Thank you for this beautiful talk.
Two last questions there. Over there, please.
Thank you for your presentation. You say that meta lenses are now in 2 smartphones brands, and most probably it will expand in many brands. What do you think about people's privacy and security? Will be there any limitations or something in technology for all our privacy?
Well, let me say the application in cell phones now comes in face recognition system. Okay, so this is a single wavelength application, but it's high volume. Because what I said, I'm not sure there's too completely your question, but the next step is now, can we substitute all the lenses of cell phones with meta lenses? That is an open question. First of all, we have to be able to achieve broadband. Now, let me tell you something that for cell phone, smartphones application, it's not really important to get diffraction limit. So we can relax the condition of design. So I am hopeful that one should be able to make lenses that are larger size and are actually broadband, but not quite diffraction limited. In fact, we have made significant progress recently. Okay. One other thing I want to tell you, I didn't have time to talk about it. I showed you a polarization sensitive camera. Now, polarization sensitivity, if applied to face recognition system, gives you a completely secure face recognition system. The manufacturer of cell phones don't tell you, but occasionally people can get through with a fake face, The company that started MetaLens now manufactures a system called polar eye identification. It is a camera module for cell phones that will hit the market next year or the year after, and basically allows you biometric or authentication using polarization. The same principle that we use to make the actual Stokes camera. So this is an example. We went from basic research into manufacturing within 5 years. So it's very exciting. So polarization can add another important element to meta lenses, again, to get completely secure system. And when I mean completely, it is completely, okay? There's no way to fool an actual face recognition system that sees polarization with even a perfect picture.
Okay, we have a last question, and then the photo. Go ahead.
Hi, thank you for your very nice talk. I wanted to ask if you see any possibility of application of meta lenses with ultra-fast lasers, so femtoseconds or maybe even Attosecond, and of course the broadband is maybe related to the other question.
Yeah, we have in fact, yes, I mean, we had a paper in Science 2 years ago where we made meta lenses. In fact, for Attosecond physics, basically they were made of silicon And what was doing the actual guiding is the actual holes, because we focus light at 50 nanometer wavelengths. At that wavelengths, silicon has a refractive index less than unity. So we use vacuum guiding. A metal lens with holes in actual vacuum, you have to use vacuum. And then, we use high harmonic generation. This is a collaboration with the University of Actual Graz, where we demonstrated a metal lens to focus light at 50 nanometer wavelengths. And it is an existence proof. It's going to take years to make it a technology, but I've been a lot in touch with the group of Ferenc Krauss, and they tell me if we can make components, good components in this wavelength region, it could be very interesting precisely for the application that you're talking about for attosecond optics. We know that we can do it. We have one demonstration of a metal lens for a 50 nanometer wavelength.
So thank you, Federico, for once again for this fantastic talk, stimulating so many questions, and good luck for everything. Thank you again.
Thank you very much.
Please stay here. Okay. Good afternoon. I think we can start the afternoon session. And the first speaker of the session is Nicolas Gézen, and he will talk about 3 paths beyond Bell inequalities. Please.
Yes. Okay, so welcome back after the lunch. Well, a bit surprisingly, it's actually my first time here in Trieste, in this beautiful ICTP place. Very much looking forward to talk to many of you, the students, the colleagues, the friends. Very nice meeting, thank you. So we heard this morning that Bell inequality, somehow that's done, tick. And what's coming next? And I want to tell you several ways to go beyond, 3 ways. Actually, of course, it's not limited to that. And what I want to tell you is joint measurements, which of course I will develop, network non-locality, a different flavor of Bell non-locality, and again, quantum non-locality, but with a little question mark. That's for the end. Okay, so let's start with joint measurements and ask the following question. So now, because of Bell inequalities, because of quantum information science, entanglement theory, all that, we know a lot about entanglement between our friends Alice and Bob. Plenty of things are known here. But what do we know about joint measurements? You know, measurements whose eigenstates are entangled. So entanglement does not appear in quantum physics only between Alice and Bob, but also in measurements. And I think here a natural question to ask each of you is, cite me some joint measurements. And I'm sure everyone here will say, oh, Bell state measurement was also mentioned by Alain this morning. Yes, but there is a continuous infinity of joint measurements. So give me a second one, or a third one. And I'm sure that essentially no one here can even name a second one, although there are infinitely many. So clearly we have a lack of understanding and familiarity with joint measurements, this other aspect of entanglement. So let me, in order to introduce these joint measurements, start with actually what Sorkin, the same Sorkin that was also mentioned this morning, named impossible measurements, and in quantum field theory. So you have space-time with time going up and space horizontally, and we have a sender with the light cone here, and we have a receiver with the passed light cone. And you obviously see that the sender and the receiver, they are space-like separated. But now in the middle, Sorkin says, let's suppose we do a measurement, a quantum measurement on a system here and a system here, and as a first approximation, we're going to describe the measurement, this measurement, in the usual, very standard way that we find in Alain's Bible, written by Claude Cohen-Tanuji and co-authors. Let's see what happens. So of course, here you can do communication at the speed of light. And here we do this measurement. And because we don't communicate the outcome, this will be a non-selective measurement. So the communication is not a problem. So if there is any problem, it could be here, in this joint measurement here. So let's focus on that one, and let's take us an example. And now we introduce again Alice and Bob. You see, Alice would be in the future of the sender, Bob is in the past of the receiver. And as a measurement, let's concentrate just as an example, and let's take a very simple example. This is an example of 2 qubits. And you see the state 0, 0, 0, 1, 1 plus, 1 minus. Of course, the plus or minus is 0 plus or minus 1, normalized. And you see that the 4 eigenstates are all product states. However, this set of 4 eigenstates is not a product basis. So it's a bit of a funny thing, but let's look at it. It seems simple. And let's start with the idea that we start in the state 0, 0. So there's a qubit coming here in state 0, and the sender emits a qubit in state 0. So of course, now in this region, since we enter with one of the eigenstates, we expect that what comes out is just the same eigenstate. with probability 1. Okay, that's a possibility, and in this case, of course, the receiver will get this qubit in the state 0. Now the sender act by flipping the qubit, acting with this Pauli matrix. Now flipping the qubit 0, this means it's going to be the qubit 1 now. This one, of course, hasn't changed. But now what enters this measuring region is the state 1, 0, so the outcome will be one of these two with probability 50-50%. Okay, so we get 1, and here a mixture of plus or minus. But of course, a mixture of plus or minus, that's half the identity, is maximally mixed. But a state maximally mixed and the state 0 can be distinguished by the receiver, at least probabilistically. But if he can distinguish them, then there is signaling. So I showed you a very trivial way here to use joint measurements to apparently signal outside the light cone. And that's why Sorkin called these measurements impossible. So clearly, impossible measurements are impossible because they are signaling. So what is going on here? What really happened here? Let's go back here, and let's concentrate really on this measurement. This measurement, I can write the eigenstate columns here. That's the first one, so the 0, 0, the 0, 1, the 1 plus, and the 1 minus. So this is a unitary that maps the computational basis onto this twisted basis. We call that the twisted basis measurement. So clearly, measuring here between these distant qubits, this observable, ideally, and by ideally I mean in a way which would be immediately reproducible, or which formally means we apply the projection postulate, one of the famous postulates of quantum mechanics, of quantum measurements. So if we do that, we run in the problem I just showed you. That would be signaling, so this is impossible. But can we localize such a measurement? And what I mean by localize, I will define it a bit more precisely. Let's do something here and something here, which on both sides gets classical data out. And this classical data should code for the result of the measurement. Let's try. And to do that, the spirit of quantum information technology and theory, we add an ancilla state, a resource, which is itself an entangled 2 qubits, or an E-bit, as we say. So one of the famous Bell states. And on this side, let's say I just do a Bell state measurement. So this is now local. So this I can do without problem. And I get a classical result, 0, 1, 2, or 3, one of the 4 possible results. And depending on this result, this already smells a bit like teleportation. So what we have here is that this qubit gets teleported to here, but with some distortion. This Pauli distortion that you get. So this is now the state of these 2 qubits. Now what can Alice do on her side here? Well, she can measure the first qubit, for instance. And if she finds that the first qubit is a state 0, then she knows that she has to measure the second qubit in the Z basis, or the computational basis. If on the other side she finds that it's a 1, then she has to measure the second qubit in the state plus minus, or in the X basis. Okay. And it's not difficult to convince yourself that now together, the result that Alice gets and the result that Bob gets, together, they really code the results. They tell you whether it was the first, the second, the third, or the fourth eigenstate as the result. So the result of the measurement has been obtained by acting only locally. However, obviously, this is not an ideal measurement. Look, this qubit, for instance, at the end is in a maximally mixed state because it was projected on a Bell state. So this is not a measurement which is immediately reproducible. Actually, another way to do also the same would be by applying U dagger, so U minus 1 here, and then measure in the computational basis. You can convince yourself that this is the same. Okay, so this idea of localizing a non-local measurement or a joint measurement is to say that I want to measure on these two systems. I add a lot of resource, a finite number of resource states. I do a joint measurement here, but this is now local. And I get a classical data, similar on Alice's side. And these classical data, they code for the results. So if I now bring them together to an observer, the observer knows the result of the measurement. And very importantly, okay, didn't write it down here, the probability of getting a result by performing this will follow the Born rule. So the Born rule is perfectly satisfied. No problem with that. There's obviously no signaling here because I'm just acting locally. There cannot be any signaling. However, the measurement cannot be ideal. And then there's a theorem, actually a relatively old theorem by Grossman, Resnick, Weidmann, that tells you that all measurements, all joint measurements, any dimension, any number of parties, so you can, of course, generalize that to more parties, they are always localizable. That's nice. However, in this proof, they require infinite entanglement, so infinitely many EBITs. So this list goes on forever. So in a nutshell, impossible measurements are localizable, hence they are possible, but they cannot be ideal. And now comes an idea, which is, I think, in this context, very natural. Since we are interested in these joint measurements, let's classify them by counting how much entanglement they need to be localized. So with zero entanglement, the only thing I can do is to measure product measurements. However, if I have one EBIT, so I can do what I told you before. Okay, now this is the unitary that I had before. Then, okay, I'm not going to go into the proofs here, but there's a theorem that it's very recent result, as you see here, that if you have only one EBIT as a resource, then there are only two possible measurements. There is the twisted basis, the one that I just showed you, and there is the Bell state measurement. Let's just look a bit at this Bell state measurement. How would you do that? Well, it's actually very simple. You do one Bell state measurement here, or one state Bell measurement here. You get the two outcomes. And if you're a bit used with Bell state measurements, it should be very obvious that this is going to do a measurement here. Because the number of the phi's that you have here should be even, and the number of pluses that you have here in these Bell state measurements have to be even. That's nice. Yeah, that's what I just said. And so we recover Born, it's not signaling. Now let's do the same for Bell state, but add one more EBIT. And now on this EBIT, I can locally act. Given the classical result that Alice got here, she can apply this unitary here, similar for Bob, and then it's not difficult to convince yourself that in this case, this pair here ends up exactly in the Bell state corresponding to this measurement outcome, encoded by A and B. And now there's another theorem, which I think is very important in this context, that says that the Bell state measurement is the only joint measurement of two qubits that can be measured ideally without signaling. So at the beginning, I asked you which joint measurements do you know? Okay, I didn't ask really everyone, but I suspect that everyone would have said Bell state measurement. Now, if you develop your intuition on joint measurements based on the Bell state measurement, you are developing your intuition based on an exceptional case. And so your intuition will be bad, because it's the only case which you can really measure at a distance without signaling. All other measurements will lead to signaling. Now let's continue classifying these non-local measurements or joint measurements. And okay, for some technical reasons, the next step is with 3 EBITs. So essentially, you teleport this one here, and then you teleport this one back, teleport blindly, so without communicating the results. And in this case, again, you have a theorem that tells you that in this case, with 3 e-bits, or the next level of our hierarchy, you have a few more possible measurements. You have another measurement which is actually quite well known, and maybe several of you thought about that, the partial Bell state measurement, which distinguish 2 of the Bell states and 2 product states. So this is also a known joint measurement, which also comes out easily with this organization of joint measurements. Another one is the so-called elegant joint measurement, which I'm going to introduce in the next slide. And then you have actually a few more, which are also kind of known, but I have no time to describe here. So let's go to this elegant joint measurement, because I think this is the one that we should all know, because it's quite simple. Now let's suppose you want now to have a basis not made out of maximally entangled state, because that would be always a necessary locally unitary equivalent to the Bell state measurement. So you want one that is partially entangled only. And let's say we want something elegant. So we want the 4 eigenstates to have the same degree of entanglement, of partial entanglement. And then because it's partial, it means that locally the block vectors on Alice and the Bob side, they will not be of length 0. They will point in some directions. And the natural thing is to say they point towards the vertices of the tetrahedron, the regular tetrahedron. So they would, these eigenstates will be some linear combination of a qubit pointing in the direction G, minus G, superposed with minus GG. Now, if you want to impose that this is a basis and you make the number real, then there's a unique solution. It's that one. OK, nice. And work in progress, cannot avoid to tell you that now we are, mostly Jeff Powell, my postdoc, is working on that. So if you have n qubits, you can localize n qubits if you go at the level n plus 1, I think, or n. The nth level will give you the n qubit case. Nice. So this is for joint measurements. Now, one thing you can do with joint measurements is go to quantum networks. So not only Alice and Bob, but A, B, C, D, and you can use all the alphabet or beyond. And you see, so here, for instance, Bob is going to receive 3 qubits. So it's more complicated and so on. And of course, now you can have one source between Alice and Bob, another source here, and so on. And you can easily imagine that the first source is, for instance, powered by solar energy, let's say. And maybe the second one is a university professor on a bicycle. And then it's very, very obvious that these 2 sources are independent. Now, it wouldn't be a scientific explanation to say that the electricity produced by the professor on his bicycle and the solar energy are correlated. So we're going to make the assumption that all these quantum states here are independent, so described by a huge tensor product of all these. And now we want to see, are these correlations here really quantum? How to certify the quantumness of such a network? And the idea will be to say, OK, now we are going in the spirit of Bell. Say we have some local variables here, some local variables here. So every source is emitting some local variables. And we are going to, again, assume that these local variables are independent. So I think this is really very much in the spirit of John Bell. Indeed, there are really 2 ways of thinking of non-locality, or at least 2 ways. I think the way John Bell, whom I know quite well, in the time, will think the following way. So you have our photons or qubits or whatever going left and right, and in their backpack, they have instructions. What to do when they will be asked questions. That's the first view. That's the historical view. But then came quantum computation. And then we started speaking of shared randomness. Shared randomness, somehow God-given, falling from the sky all over the place. We don't really think how they're distributed. It's just this computer science view. And if you have only Alice and Bob, that doesn't make any difference. But if you have now independent sources, here it's easy to say. Now, you have one source that distributes lambda, another source that distributes mu's, or some other independent variables. Here is no way any longer to talk about independent sources. So let's go to a simple case, just the entanglement swapping case, also known as bilocality. So we have two sources, EPR1, EPR2. EPR1 is emitting the instructions lambda1, lambda2. And the independence is really written here. Mathematically, it means that the probability of lambda1 and lambda2, they factorize. That's the meaning of independence, or the formalization of independence. And because you have a product here, the set of these correlations, bilocal correlations, is not convex. So a priori, that's just a not that comes here in addition, but not convex changes the things very drastically. You no longer have local polytopes and linear Bell inequalities that are facets of these local polytopes for those who know a bit. It changes the thing drastically, and it makes it way more difficult, but also more interesting. So for instance, in this bilocality scenario, don't derive it here, but here you have an example of a Bell inequality, or a Bell-like inequality. Alan showed us this morning the CHSH inequality, and indeed you have many more inequalities, possibly with more outcomes and so on, but always a fixed given number. But they are always linear combination of these correlation functions, or possibly marginal probabilities, but always a linear one. And here you clearly see that this is not linear. Square roots, okay, absolute values, that's more or less okay, but the square root is typically not linear. And you also see it here on this slice, two-dimensional slice of this space of correlations. So the square would be the local, cut through the local polytope, and this star shape is actually the set. So inside you have the sets of bilocal correlations. And so this really illustrates that if you have an experimental point here, it will be local according to the traditional Bell, but it will be non-local in this network non-locality language and picture because of the independence of the sources. So let me now show you a beautiful illustration of the power of network non-locality. We all know that in quantum mechanics, we use complex numbers. And we also use complex numbers in electrodynamics, or even maybe for Lorentz transformation, you can code them with complex numbers. But we also know that at least in electrodynamics and relativity, the use of complex numbers is just a convenient mathematical tool. It's not fundamental. In quantum mechanics, are complex numbers fundamental, or is it actually just, again, a convenient tool? The first way of answering, so if you have a complex Hilbert space, finite dimension here, obviously this is isomorphic to a real one of twice the dimension. And how can you double the dimension? Well, you just add a qubit here, or some people call it a rebit, because I want a qubit, but only considering real coefficients. So I have this trivial relation here. Fine, this is now for 1. Let's have a little network, but notice with a single source. So here I will have all these complex Hilbert spaces, obviously isomorphic to this one. So again, I could double here, but instead of doubling, I add a qubit with real coefficient. Okay, this is still isomorphic, obviously. Now here comes a first problem. So where shall I put these green qubits? Shall I put it to Alice? But then Bob and Charlie cannot act on it. Well, we know that according to quantum mechanics, everybody can flip the phase or change the phase. So here the answer comes actually from error correction quantum computation. We are going to add a logical qubit, not a physical, but a logical one. And we do that by adding 3 physical qubits, so 1 for each. And the logical qubit 0 will be the superposition of all the odd number, all the cats with an odd number of zeros, and the one is an odd number of ones. And then obviously, everyone can flip this qubit and do the analog of changing a phase. Very nice. And when we found that already quite some time ago, we concluded, actually, complex numbers are not really necessary in quantum mechanics. Everything you do, for instance, violating any Bell inequality, however number of parties, you can always do it also by just replacing your complex Hilbert space with a real Hilbert space, possibly of larger dimensions. However, what happens now if you add this natural assumption that you have independent sources, that independent sources exist? And you immediately see that this is no longer going to work, what I showed you before, because I needed this logical qubit, and the logical qubit has to be shared by all the parties, and so you would need some entanglement among every party, this equal superposition of even an odd number of 0 and 1s. This is no longer going to work. Okay, maybe there is a more clever trick. No, there is no more clever trick. This is a recent result, already 4 years ago now, that says that, so in this entanglement swapping scenario, if you have, some inequality with many settings, there is some inequality that achieves a maximal complex quantum theory value of 6 square root of 2, while with real quantum theory, and here I mean real Hilbert spaces of arbitrary large dimension, you can never go, is limited. You can never go above the 7.66. So this really shows you that with networks, with independent sources, you cannot describe them using only real Hilbert spaces. So for the first time in history, I think, you have here a very successful scientific theory where real numbers are for sure not sufficient, and hence the next step after real is complex. And so complex numbers are really necessary to describe quantum networks with independent sources. And actually, in this very recent paper, preprint, we have even proven that if you have only partial independence between these two, this is sufficient already. Now, maybe some of you have seen that there were quite some reaction to this paper, and some authors claim that no one puts in doubt the mathematical results. I think that's solid. But people said, yes, we are using tensor products to describe joint systems. And admittedly, that's the way we do it, because that's quantum mechanics. And they say, no, but maybe we should replace the tensor product by something else. Why not? But if you replace it by something else, you need also to define what does it mean, independent systems. Now, with the tensor product, we understand independence very well. If you change it, you have, again, to argue the right way of doing things. And you see the intuition, if this source decides to use the convention I, at least one uses the convention minus I. I and minus I is just a convention. It's a square root of -1. And somehow, in any frame, you must find a way that this convention, whatever represents this I, there would no longer be an I, but something has to be there that represents the I and represents here the -I. And we have to get coordinated, and at the same time, you want to say that they're independent. So you feel the tension. Anyway, there is an ongoing debate about that. But frankly, I find that this is a proof that physics is beautiful. But it's not the end. Now you have this kind of network, just a triangle, and you could now everywhere on the three edges do this elegant joint measurement that I showed you before, introduced briefly before. And you see that the resulting distribution, and notice that here there is a fixed measurement. You don't change the measurement. You're no longer any input. You don't need to choose an input. You just do always the same. But of course, you assume that the sources or the local variables are independent. And you need so that this probability of ABC get very simple and elegant results, probabilities. And so for a long time, I was asking the community to prove that this is local or non-local. And actually, there is a very recent result by Victor Gigon and Renato Renner that proved that it is non-local. But I want to emphasize, and they know that I'm saying that they have a result. I think it's a solid proof, but it's really not elegant. So for such a beautiful problem, you should have a beautiful proof. So there's still work to be done here. And another question now, let's again have this triangle, for instance, fixed measurements. So you have, and you get random. Okay, since you perform a quantum measurement, you expect that these results are random. That's what quantum theory tells you. But now we really want to prove this randomness. And in Bell inequality scenario, so the standard one with the input and output, what you can prove is that there is more randomness coming out than the randomness that you put in. But you need to put some randomness in. So the only thing you do there is randomness amplification. You amplify it. Here, no inputs. Is there still randomness in the outputs? Yes, there are some results by these people here. But still, I think really the minimal assumption to get randomness is that you must have at least epsilon independence. What exactly it means, epsilon independence, is still to be defined. But clearly, if you have zero independence, then you have superdeterminism and no randomness. If you have epsilon independence, I believe that you will get randomness, but this is a conjecture. We don't know here. So in the last few minutes, is nature non-local? Well, Alain told us, yes, and I agree with him, yes. But we are scientists, so we want to really push that question really to the extreme. Remember, John Bell said, if a hidden variable theory is local, it will not agree with quantum mechanics, and if it agrees with quantum mechanics, it will not be local, period. Okay? Okay, maybe I jump over that. So the usual way, we do that, and somehow we make sure that nothing goes from Alice to Bob, nor from Bob to Alice. And the usual way of avoiding any possible hidden communication or hidden influence is just what Alain also told us, standard space-like separation. Very good. But here we want to test quantum mechanics. And in quantum mechanics, or in Hilbert space, there is no speed of light. All what quantum mechanics tells us that when you do these measurements, there is nothing according to the theory that goes from Alice to Bob, nor from Bob to Alice. But if we want to test that, how do we know how fast it goes? So I think we should continue testing quantum mechanics by assuming that possibly some hidden stuff propagates, possibly at superluminal speeds between Alice and Bob. Somehow, as John Bell was saying, something is going on behind the scene. So of course, that is not in agreement with quantum mechanics, and it is not at all in the spirit of relativity. Now, relativity doesn't tell you that nothing can go farther than the speed of light or that you don't have a privileged reference frame. Actually, there are privileged reference frames. There is one in which the cosmic background radiation is isotropic. This is not due to the equations, but it's due to the distribution of mass in our universe. So you get some privileged reference frame. And maybe in this privileged reference frame, something goes on faster than the speed of light. So we did some kind of experiments like that. Okay, it was not in Bernet-Bellevue. This time it was Jussi and Satini. And these experiments were reproduced by these other groups in Italy and in China. And all these experiments, okay, you have a lot of details, which are, of course, super important. But roughly, we always say that if you want to explain the correlation, so the violation of Bell inequality by some hidden communication, this hidden communication would have to go at speeds 50 to 100,000 times the speed of light. Wow, that's really fast. And for, of course, 99.99% of the physicists, that's good enough. But not for me. Because actually, that is just an argument. The speed of light compared to the speed of sound, whether it is in air or in solids, is roughly of the order of 1 million. So I think we should imagine the possibility or consider the possibility that next speed is again 1,000,000 times faster. So we should actually repeat this experiment, but aiming at bounds of, let's say, 10 to the 7 to have a bit of margin. And the reason also why I think we should do that kind of experiment is that today we can do that. It's really a feasible experiment. Here we were using semiconductor detectors. Today you have SNSPD, superconducting nanowire single photon detectors, which are really way better. The sources, as Anna said, have even improved now. And so we get also faster data acquisition. So this is a feasible experiment. And since physics is an experimental science, we should do that. Someone should do that. So let's just jump here. OK, and so my conclusion again, so joint measurements, we have to understand that. We're starting a classification in terms of the entanglement cost to localize them. Network non-locality is the natural way to go really beyond Bell inequality, still talking about non-locality, but this one network non-locality. And also this idea that something could be going on behind the scene. Thank you very much.
Thanks for the talk. I wanted to ask a question about the necessity for complex numbers, because the
necessity of
complex numbers.
Yeah.
Because recently there was a paper doing a Paris test for the use of quaternions, or like generalizations of complex valued fields, let's say. And can you construct a network that tests for these as well, or is this just the test you design? Is this just a test for complex numbers? Because then you could sort of do a test of numbers beyond complex numbers.
Yeah, I understand. So we excluded real numbers, and you're asking, is there a test to exclude complex numbers? Of course, if you exclude complex numbers, that would mean that you have falsified quantum mechanics. And okay, it's certainly an interesting program, but I don't know exactly what to do here with this quaternion, for instance. So you could indeed base Hilbert spaces on quaternions. I think there are some problems that appear if you also want to describe joint measurements, because again, I think then the analog of the tensor product is maybe no longer associative or something like that. I think it's associativity that starts to fail. But this is not an experimental argument. It's a challenge to face. But indeed, it would be very nice to get inspiration maybe from this quaternionic quantum mechanics to design or to propose experiments that someone could then test in the lab. You have some. Why don't you come to me afterwards and you tell me?
So I have a question concerning point 1. Is it possible to extend this classification to multipartite?
Yeah. So we are indeed. So these are very recent results. I mean, the paper appeared maybe 2 months ago, but that was only Alice and Bob, 2 parties. But now we have results, preliminary results that go to n qubits, and so for n qubits you can also have this idea of localizability in function of the number of the amount of entanglement. And so we have first results there, but for sure you can do it. And you can also go to higher dimensions, so Q-treats and so on, where also we have very few results. I guess this is really a field which is so young that it's still a good time to jump in, because we are probably still low-hanging fruits.
Okay, well, yes.
Thank you for the talk. Can I ask you, first question is about the triangle network. Do you think there is a fundamental difference between the independence of the sources and the freedom of choice assumption beyond?
Yeah. I think there is a fundamental difference, because here you don't need to make any choice. So there's just no choice. You don't need to look at, I don't know, faraway galaxies to make your choices, or use a free will, which anyway no one has ever really used. You just need this idea, which is kind of the minimal natural assumption in all sciences, that you have some independence. Okay. You know, the argument saying that Alain on his bicycle is fully correlated with the sun is not a scientific explanation. It doesn't make any sense. Yeah, but superdeterminism is not scientific. But so you need a bit of independence. And this is the kind of the minimal assumption. And with this minimal assumption, going to these networks, you can already do everything that we have been doing with Bell inequalities.
I think because if one, from a naive point of view, the freedom of choice is like an independence of, you can use another source. And as postulating the independence, you, like in the Fritz distribution, or you can...
You agree. I agree. Instead of having really a quantum random number generator here, which is just another source, let's say, of entangled photons, for instance, and then by measuring the second photon, you are somehow determining the measurement choice on this side. So indeed, this kind of this way of choosing the measurements is really in the spirit of these networks.
Yes.
Alain, quand même.
I would like to have your opinion on another example of non-locality, which is, for instance, the experiment which was done by Grangier and Boes, where you have two photons emitted by two independent sources, and they are emitted in modes which are conjugate on a beam splitter, and you cannot avoid, if you want to understand that experiment, you have to symmetrize. Although they have never seen each other, you have to symmetrize, etc. This is another example of non-locality. How do you fit that example into your vision?
I guess it's not very different from this entanglement swapping, because so you have your two sources that come together. One way of producing these two sources is to have two independent sources here of entanglement, and you measure the two wings. That brings you that prepares your two photons that will then interfere. So I guess, and maybe I should really have mentioned that, but these two times single photon is actually, I think, can be really understood as one example of network non-locality. Probably you agree, which is already good.
Okay, thank you very much.
Thank you.
Thank you.
Thank you.
Will be given by Guglielmo Tino, and it's about testing gravitational physics with atomic quantum sensors.
Devo attaccare questo. A 35. Poi hai altri 5 minuti. Va bene, grazie. Poi a 35 mi... voglio pure attaccare questo. Sì. Intanto faccio partire questo.
Okay, so first of all, I would like to thank the organizers for inviting me here and letting me come here again after a few years in this nice place, nice institute, which has the scope of letting people interact, exchange ideas, building bridges rather than building walls, which is getting more and more common in different parts of this crazy world. So I will be talking about testing gravitational physics using quantum sensors. And this is interesting by itself, I would say, because you know that putting together general relativity, gravitational the way we understand gravitational physics and the way we understand quantum mechanics is not yet an established theory. So at least we try as experimentalists to do something in that direction. And since I think I will be showing experiments mainly done in Florence in my lab, but also in other labs, they are based on ultra-cold atoms. And since I think I'm the first one to explicitly showing experiments with cold atoms, I will take a few slides just to introduce that for the people who are in different fields. And I apologize for the big experts who are here for this. So when we say cold atoms, historically this started with laser cooling of atoms. And the idea of laser cooling is that you shine laser light close to the resonant frequency of the atoms. And so the atoms, because of the Doppler effect, depending on their velocity, they feel a force, a radiation pressure equivalent of a radiation pressure. And since there is absorption and re-emission by stimulated by spontaneous emission, which is a random process, there is a dissipation. So the kinetic energy of the atomic clouds is reduced and taken away by the light. And when you take this simple model for laser cooling, you find that there is a limit called the Doppler limit, and then there is an intrinsic limit for the temperature given by the equivalent of the recoil of a single photon. So all of this is to tell you that essentially when we say cold atoms, we are talking about temperatures for this cloud of atoms that is from a few microkelvin to nanokelvin. Then depending on the experiments, you will see specific numbers. But cold atoms means, as I said, microkelvin to nanokelvin temperatures. This is about cooling the atoms, reducing the velocity. The other important point is confining the atoms, having the atoms in a well-defined volume. And for that, one system which is often called horse work, I mean, you find it in most of the experiments with cold atoms, is called magneto-optical trap. Essentially, you have the same configuration that I explained, let's say, for the cooling, but you add this inhomogeneous magnetic field with a zero at some point. And so the combination of the Zeeman effect and the radiation pressure gives rise to a force on the atoms which has a dissipative part, as I said before, but also a force that is pulling the atoms towards the center. And so essentially with the magneto-optical trap, you typically trap 10 to the 9, 10 to the 10 atoms with a density of about orders of magnitude, 10 to the 10 to the 11 atoms per cubic centimeter, with a temperature, as I said, of tens of microkelvin in a size which is of the order of the millimeter. And for example, this is a video of the magneto-optical trap of strontium atoms that we realized in our lab in Florence several years ago. And this light, so this is the vacuum system. The vacuum system, again, for the non-expert, is at room temperature. So there is no cryogenics here. You have a vacuum, which is a vacuum system at 300 Kelvin, and then you shine the laser light, important field of development, and numbers are getting incredibly precise. And to give you an idea of the precision, of course, you can say this clock would be wrong by 1 second over the age of the universe or things like this. But since we are talking of physics and gravitational physics, if you take the gravitation redshift, the dependence of the passage of time on gravity, you find, based on general relativity, that on the Earth, the change, if you move a clock by 1 meter on the surface of the Earth, the frequency changes by 1 part in 10 to the 16. This had to be taken into account, for example, on the GPS, which is based on 24 clocks, rubidium or cesium clocks, which are orbiting at a distance of about 20,000 kilometers from the ground. So if you did not take into account this general relativity effect, our GPS system in our mobile phone would be wrong by 10 kilometers per day. So this is a general relativity effect which has important application. But with these optical clocks, because of the much higher precision, now it was shown experimentally that you can detect this general relativity effect, the dependence of time on gravity, over 1 millimeter distance. And this opens a completely new field of research, both for fundamental physics and also for applications, because again, now you can use this general relativity to measure the potential of the Earth, with all the applications also in this case. So very quickly, because I think I have only a few minutes, this is to say how you can improve, based on the simple expression I gave you before for the sensitivity of an atom interferometer. You can improve the sensitivity either improving the resolution in the measurement of the change in phase, or improving the momentum transfer from the light to the atoms, or increasing the interrogation time. That also in this frame, entanglement is very important. So we fall under the definition of the second revolution given by Alain Aspect before, because as was done, and this was mentioned again in my talk before, as was done already in the gravitational wave detectors with the light, using squeezed light to increase the resolution. Here you can use the squeezed atoms, producing an entanglement between the atoms, to go from the standard quantum limit that depends on the square root, the inverse of the square root of n, to 1 over n. So for example, with 1 million atoms, you increase your sensitivity potential by 1,000 times. This is not easy. There are preliminary results, and we are working in Florence on a scheme that we proposed some years ago in collaboration with Vlada Vuletic of MIT. The other possibility, as I said, is to increase capital T, to increase the duration of the interferometer. And in this direction, instead of using fountains which are, let's say, meter scale, in different labs, fountains of 10-meter scale have been developed. One is also under construction in Florence. And in these fountains of this stage, you can have that the splitting between the two parts of the wave packet that I showed before can go up to, for example, in this experiment done in Stanford, 50 centimeters. So each atom is described by a wave packet given by two parts which are separated by half a meter. And so in terms of discussion of second revolution, people are also claiming that this is another aspect that could be defined in the frame of a second revolution. Second revolution is all based on things that were present since the start of quantum mechanics. The difference, as was said this morning, is that now this aspect become not an abstract concept, but you can see it in the lab and use it to increase the performances of your sensors. This was done in a 10-meter fountain. There are projects now to go to 100-meter fountain. This is done at Fermilab in the United States. We propose an experiment, an apparatus, a possible project to be done in Sardinia, where there are shafts which are even 500 meters deep. And then the last solution to increase the interrogation time is to go to space in microgravity, where you can interrogate atoms for seconds and seconds. And this is something which is growing, at least in number of people supporting the idea, both for very large, long baseline interferometers on the Earth, and also for future experiments with optical clocks and atom interferometers in space experiments. And so I would like to close by acknowledging the people of my group who performed the work that I showed to you today, and thanking you for your attention.
Thank you very much. Questions? Yes.
Thank you. I just would like to maybe to hear like more details, or how you're planning to use squeezed excitations, like to measure gravity. So is it like combination of squeezed momentum states and atomic clocks, or like how you are planning to measure J?
Maybe I'm a little bit, I'm not sure I understood the question. Can you?
What is the plan of the experiment with the squeezed states?
With the squeeze, sorry, I didn't catch the word. Generally speaking, the standard quantum limit comes from the fact that even if you're using ultra cold atoms and so on, they are still uncorrelated atoms. So essentially, when you detect them, they follow the Poissonian statistics, and then you get this square root of n dependence on the fluctuations, and then you divide by the number of particles, and you get, for the relative precision, 1 over the square root of n. In our experiment, but this is rather general, what you want to do is to have, instead of uncorrelated particles, correlated particles. And this you can do with different schemes. Here you have Augusto Smerzi, who can tell you all you want to know. Essentially, you need some interaction between the atoms. So this has been done, for example, using Bose-Einstein condensates and using the interaction between the atoms to establish some correlation. But for precision measurements, as the one we want to use then these sensors for, I don't think that that's the right direction. So just to answer the question, what we are doing in our experiment is to have the atoms in an optical trap where there is laser light circulating. And so we use the light to induce an interaction between the atoms. The presence of the atoms affects the light. The light is, and so at the end you get, mathematically you can show that you get an SZ square in the Hamiltonian, and so you can get these squeezed states.
Tino, in the very beginning of your talk, you said that there are people thinking about quantum gravitational effects. What kind of thing can we measure with this, with improved clocks and things like this?
So even the terminology here is a little bit complicated. So you know that there is quantum gravity, and I don't think what I discussed today is really connected to quantum gravity. I could say there is almost nothing to do. In the community, what I discussed today is defined as gravitational quantum physics. This means studying gravity with a quantum sensor. So having said that, so we are not at the Planck scale, unless you go to very small distances, and then you can see that probing gravity at some macrometric distances, you are entering string theory models and things like this. But that's rather indirect. There are proposals now, for example, to, this is, for example, mentioned in Holger Müller's paper, to study possibly entanglement induced by gravity. And this is considered always under some model showing that the gravity has some quantum effects. That's an example. The other possibility in terms of precision measurements, as I said, is that you perform an experiment. We never know that you start seeing some discrepancies with respect to what you would expect, and then you have to understand if this is due to the fact that your probe is different from, for example, in the measurement of big G, or gravitational constant, if we perform 10 experiments and you find that they are all different, of course, we will like to check all the possible systematics, but you might find that, and there are papers in that direction already investigating if the value of gravitational constant depends on the specific probe that you're using.
When you speak of entanglement induced by gravity, is it by quantum gravity or by classical gravity?
By classical gravity. Okay. And that's why I said it's within some models. I'm not supporting the idea, but it's interesting. I think it is interesting. Then what that would demonstrate, I'm not ready to push too much on that. But it would be nice to see the effect.
Actually, Guglielmo, I wanted to ask you about this quantum gravity as well, and maybe you've said this is maybe a more deeper question, but simply speaking, if you want to do entanglement with gravity, is it correct to say that you are simply testing if the gravitational 1/r interaction does the same as the Coulomb 1/r interaction? So we are so used to write the Coulomb 1/r interaction into our Schrödinger equation. We have exchange terms, we have all that, and we have entanglement, which comes from electric interaction. But simply to show that for the non-relativistic Schrödinger equation, gravity is a 1/r potential. Is that the goal, to show that gravity has not something special and would behave differently from, let's say, a very weak Coulomb potential?
Yeah. Yes, that's much more direct to explain what would be the interpretation of such an experiment. Closer to quantum gravity, I think, is some proposal to test, if you consider some foam-like feature of space due to real quantum effects at the Planck scale, then people have been proposing looking at the coherence effect induced by that's maybe closer to the real quantum gravity, but as an experimental setting that would be 100 reasons stronger than quantum gravity to destroy an interference pattern. So that would be nice, but I don't think it's realistic, even in space. But that's an example. If we could have a nice interference fringe that is not affected by any spurious effect, and then we find the coherence, then you could attribute it to the, but on what you said, I think I agree, if I understand the point. Instead of using an electric field, you consider another interaction which has the same dependence on R.
Okay, so let's thank Guglielmo again. There is coffee break upstairs. We come back at in half an hour, 20 past 4. invite Vanderlei Bagnato for the next talk. And the title is Far from Equilibrium Quantum System, What We Learn Establishing and Relaxing Turbulence in a Quantum Atomic Superfluid. Vanderlei?
Okay, thank you. And for me, it's a big honor to be invited for this talk, and especially because we are commemorating an important issue for all of us working in cold atoms, and seeing so many people that we know and meeting others that we do not know. I'm from Brazil, and the work I'm going to describe to you is related to quantum turbulence. We produce the condensate, and we introduce vortices and solitons, because the way we do, we cannot really introduce only vortices. Otherwise, we will have a hydrodynamic limit, which will be very nice. But we introduce a little bit of everything. And that's established. We have to characterize. And there are a lot of people interested in turbulence in general, especially in quantum turbulence. This is not a new topic, right? I mean, people are working in turbulence with superfluid helium, both 3 and 4 for a long time. And we always believe that understanding the turbulence in the quantum system will easier make us to understand a little better turbulence in general, because this is a very old topic. Even Leonardo da Vinci has turbulence in his pictures. But even though it's still in the very beginning, in the very primary understanding, all these things about turbulence, as you may know. I'm not going to speak too much about turbulence, but I'm going to try to use the turbulent cloud to do something else, right? So I also started this because, and I'm working on this for more than 10 years, I thought that I could understand a little better what people were saying. And I end a decade of things, and I realized that basically I only understood what people knew already about the quantum turbulence. But we were able to evolve many things, way to look, quantities to look, and characterization of the atomic superfluid trapped in many different quantities that allow us to follow up what's going on. But then at the end, I realized that this was much useful tool to understand, to apply, use the turbulent cloud for many other things. And one of them is, I'm going to show you 2 of the applications we have done. One is a speckle of matter waves, because a turbulent cloud in expansion, it looks very much like a speckle of light propagating. But now matter waves, right, which may have some applications, as a speckle has a lot of applications, and is a fundamental tool for quantum statistical optics. And then on the other hand, we take this as a far from equilibrium system. And then we try to see the evolution. What are the stages that a quantum system that is out of equilibrium has to pass through to rethermalize, to find again the equilibrium condition? Okay, I'm starting. Normally people put the people that really work on the experiment at the end. I'm putting the very beginning. And I have a large group in Brazil. It's not only in cold atoms. We have 3-4 fields involved in quantum, in optics in general, and photonics. But the people that really contribute for this work is listed here. On the lower part are the graduate students. On the left part, the postdocs. In fact, Lucas Madeira is here with us. And then I have researchers in Brazil that are also contributing. And I have, as you see in the last line, I have a collaboration with many people, including Professor Fetter from Stanford that has given us a lot of hints and contribution in this part. Okay, well, when we speak about the equilibrium, it's very intuitive. We all know equilibrium, you know, because we try to live ourselves, even though we are out of equilibrium, but we try to find equilibrium. So it's very intuitive when we try to do that. But non-equilibrium dynamic, especially in the quantum many-body system, is not so much intuitive. People has even a hard time to define exactly what we call by non-equilibrium in the many-body system, because it's everything that's not the standard equilibrium. And so how that evolve in time, how that find itself in the way that should be is still an open question in many situations. People has a lot of interest in quantum systems out of equilibrium for many reasons. I'm listing a few of them, you know, because beyond equilibrium physics is always a challenge, and studying the things that are far from equilibrium may allow us to explore different frontiers. You may find the new phases of matter in this non-equilibrium condition. And of course, everybody wants to know exactly how system finds the quantum statistics we work with. They are not born in that situation, and they have to find that situation. And that they needed to thermalize, they have to go there. And there are many concerns for a long time. Pre-thermalization is a concept that's around for at least 3 decades and things like this. What are the good systems to do that? Cold atoms, of course, is a condensate, is a good system to do that. And it's easy because we can find different quantities to measure, and including turbulence. The turbulence scenario is a kind of not so hard to reach and characterize. And ultra-fast process also is another very interesting system to study non-equilibrium, as we saw in the first talk of this meeting. But I'm not exploring that. I'm going to the cold atoms and Bose-Einstein condensation, even though we're starting to see elements to do pump and probe, but not with short pulses, but with pulses of excitation in the superfluid, following the roots of people doing ultra-short pulses. Okay, so I don't have to tell you how important is turbulence, even though everybody avoids, right? Even when I told some of my formal advisors that I'll be going to that, say, oh, you should avoid a little bit that. But it is a nice, because it is everywhere. We could not exist without turbulence, as you know. When you breathe, your air has to undergo turbulence in your lungs to be able to exchange the gas that needs. Your body, when flows in your veins, also has to have turbulence type of regime. So everything seems to be important to understand this thing. And, but we don't. And Bose-Einstein condensate is interesting because, in my view, you can reach turbulence with not a very large number of excitations, vortices. And you'd have a possibility of vary the intervortice separation. There are a few spatial scales that are important. The size of your system, for us, the Thomas Fermi radio is one. The intervortice separation is another, and the size of the vortice, which is the healing length, is another. So we have to travel in those 3 scales. There are many, many magnitudes sometimes. Okay, so, and relaxation. Here we can see, they can see in helium too, but helium, normally they are very big experiments. Here we can actually observe the recomposition of the condensate, which has very good signature. So it is a nice system to do that. When you're speaking about turbulence in superfluids, there are many types. You know, like people in helium, they produce a lot of vortices filaments, and those vortices can tangle together, can create a bundle, and then many quantum tiny objects together looks like a classical, and that they call that Kolmogorov regime, and there are many people working on that. That is what they call super quantum, which is almost like the way we do. We produce vortices, and they are kind of tangled in the sample in a way that they start to react, and they evolve to turbulence. And there are wave turbulence. That's this collection of excitations of the density, random distribution of densities, peaks, and phase in your system. Also is a very common type of turbulence in the quantum system. How I do that? Well, the way I do, I like to call atomic washing machine, because if you go to the washing machine, you put your clothes, it doesn't rotate, it just shakes, right? Because that's a way to generate turbulence and make sure that the liquid gets very close to all the dust you have in your clothes to remove. And that's what we do. We do a tiny little shake and squeezing of the condensate by adding extra fluids that produce the trap. And by doing that, we started to generate, to nucleate vortices, tiny rotations. And those vortices, we generate enough vortices that sooner they start to react, and they evolve to a turbulent cloud. If you have individual vortices, that is a very specific way of, I think I may have a pointer here. No. But you can see in the top, you see individual vortices in the sample. But if you go to turbulent, this change a little bit the shape, and it's a little different from the top. Okay, so here are vortices individual. This is turbulence. This is more or less what we do to your sample to produce those excitations. And this is a kind of timeline. We produce the condensate, we excite by cycles of this extra shaking, and then we hold for different times, and then we observe what's going on. And what you see, well, depending where you stop, you see vortices being nucleated, you see vortices getting in the cloud, you see production of vortices and anti-vortices, which is, for me, an essential ingredient for the evolution to take my sample to turbulence. And you have vortices in different configurations, so if you kind of start to count the number of vortices, you reach a number of vortices. Remember, we are dealing with a sample that's 10 microns across. You cannot put too many vortices in there. Vortices normally is like 0.5, 0.3 of these microns, and you cannot populate infinitely your sample, and then these start to disappear and you evolve to turbulence. Depending on the amplitude of excitation and the time that you excite your sample, you observe different things. If it is too modest, the composition of time and amplitude, you see vortices being nucleated and they stay there. If you go a little further, you find this region that I'm going to show how we characterize as being turbulent. And if you go even further, we find a region that we call granulation, that we're still working to understand what's going on. If you want to see the simulation, what we do, this is the sample, we start to excite, and this is the final picture you see with a composition of vortices, anti-vortices, ring, all like swimming on the condensate, and then they're going to start to react and produce the turbulence. Just the presence of vortices does not characterize the turbulence. They need to react. There are a few things that has to take place in your sample for you to evolve to turbulence. And one of those things is energy start to migrate from the large scale to the tiny scale. And that is the reconnections of your vortices and excitations you have. So basically, in a one view graph, what's going on, we put energy, we inject energy in large scale. This start to establish the turbulence, and then this start to produce reconnection two vortices, when they encounter each other, they reconnect. So it's like an avoid crossing that we are used to in levels. And then if you do this many, many times, you start to have oscillations on the vortex. That's normally referred to Kelvin waves. And energy is going there. And if you keep going, you're going to go to oscillations that reach the level of the atomic scale, which then became phonons in your sample. And of course, when you see those vortices reconnecting, you may make a lot of rings. And there is also a kind of cascade that's called Richardson cascade. Big vortices, small, small, small. And the energy start to migrate to a small scale, to reconnection, to distributing this energy in a large number but smaller dimension. Okay? So, and that's what we have. And I'm giving now a kind of tour to the turbulence, and then I start to show you the experiments we have done. When you're speaking about quantum turbulence or any turbulence, people want to know the energy spectrum. They want to know in what scale your energy is located or in what momentum your energy is distributed. So normally the energy spectrum, which is the E of k, needs to be known to find out if there is evidences of turbulence. And how we measure this? Well, we measure this in two different ways. One is just introduce the excitations. We have introduced so much rotation through the vortices that this system is no longer interaction dominate. It's kinetic dominated. And therefore, if it is kinetic dominate and you do time of flight, you just take the trap that's holding the sample, let expand. What you find is the distribution of momentum. And this is one way of doing is just do a time of flight expansion. And by looking the distribution of atoms in space, higher momentum go farther from the initial point, lower momentum stay closer, and then you can find the distribution N of k, which is the distribution of momentum occupation. But since this is kinetic dominate, basically the spectrum of energy is N of k, k squared. And there is some papers. I'm always putting some papers here where we have proven that the approach is correct and things like this. Or you can do this power spectrum, which is a very well-known technique in physics. You do many shots, you remove the average, you get the fluctuations, and you assume the energies are there, and then you do the Fourier transform, and you get the energy spectrum. And this is a well-established way of getting the power spectrum of many different physical systems. And there is a very famous Wiener-Cincini theorem that explains very well how that is valid. And when you do that, of course, you obtain the energy spectrum. And when you do this, you get a very interesting signature of the turbulence, which is a power law on the energy spectrum, or in the momentum distribution, which is basically the same here. They are related. And when we use the power spectrum technique, of course, if you excite it to very low excitation amplitude, and you don't establish turbulence, this is not kinetic dominate, so you're not going to get what you need. But when you reach the turbulence, I think you have both agreeing quite well, and you can find out what is the energy spectrum you get. And normally you have this region which has the power law, and in your case, the power law in the energy spectrum is -1. The momentum distribution is -3, and this characterizes something between wave turbulence and the hydrodynamic turbulence regime. And with this, we can study, even if the sample is not fully symmetric, you can understand basically in what regime of momentum you have this power law dependence. And this power law dependence is very important because it restricts to a space, a region in momentum where the cascade goes on. And the cascade means energy is now migrating without the dissipation from large scale, small momentum, to high momentum, or means smaller spatial scale. So this is very characteristic of the turbulence. Okay, and then together with the whole team, we have been able to find different ways to characterize. One of them is if there is a flux of energy, we should be able to measure and find regions where is a constant flux of energy between the different classes of momentum. We characterize this inertial regime where energy should migrate without changing, which is the inertial regime that energy flows in different scales without dissipation. Another thing that we can measure is integrable scale length, which will tell you as a function of time in what kind of scale size your energy will be located. And by doing all this, we try to understand and characterize and make sure that people accept that we have a sample with, in the turbulent regime. So once you have the turbulent cloud, you either understand a little better how turbulence is evolving in time, or you try to apply it for something. And the first application we found is the turbulence, it's well characterized by at the end of the evolution, or as evolve, is a collection of random amplitudes of the density and phases, of course. Each excitation you introduce phase in the sample. And that is very much like speckle, right? In a laser, I don't know if you're familiar with speckle. When you scatter laser from a rough surface, you get a very interesting pattern of interference. And, but now here we have matter waves that's going to do that. So then we have, I'm going to show to you two applications. One is this expanding cloud, which it is equivalent to a speckle of matter waves. And the other one is an in situ, which is, will be the relaxation of the far from equilibrium quantum system. And there are some thinking about observing Anderson localization here, because you have introduced randomness, but this is something else. So the speckle field, as you know, when you have a laser, we're going to make analogy with the laser, right, which is the most equivalent massless particle we have for the Bose condensate. And when you have a laser and you let it propagate in space, whatever is more squeezed is going to diffract more. And then if you have an elliptical beam, it's going to invert. You'll be as propagate, will be elliptical in the other direction, because there is more diffraction where you are more squeezed. And, but if you have a speckle of laser field, that doesn't happen. It keeps the shape, because the diffraction is no longer determined by the ratio between the wavelength and the width of the Gaussian beam or the laser beam you have, right? And normally, that happens for the condensate as well. As you know, everybody working condensate, we use the inversion ratio during the expansion as a signature that we have the condensate. But if you have a turbulent cloud and you let it expand, it's a self-similar expansion. It doesn't change. There is no changing aspect ratio. So normally, a condensate will do this as expand in time. So there is a point where they invert the dimensions. When you have a thermal cloud, it always goes to 1, right? After some expansion, you don't remember anymore the shape. But if you have a turbulent cloud, it keeps the same ratio, basically. And this is exactly what made us to think that that was a big equivalence between speckles, which is basically the same kind of characteristic in a laser, in a coherent laser beam, and the turbulent cloud. And then what we did is experiment to make the comparison between both. And they look very similar, right? This is the Bose-Einstein condensation, a Bose condensate in expansion. So that is the inversion ratio there and everything. And this is the turbulent one. There is never this inversion. And this is the optical beam, the same if it is a regular optical beam, laser beam propagating, but if you produce a speckle, they're not going to invert anymore. And of course, speaking for this audience, what you want to see is correlation, right? So we did the density-density correlation on those two systems, and they are very equivalent. And the reason that they are very equivalent, because as you know, when you have a coherent laser beam, the diffraction, the angle of diffraction as propagates is lambda divided by the waist, by the dimension of the beam. But when you have a speckle, it is the wavelength divided by the correlation length. And the same on the turbulent cloud. The condensate will diffract, will expand, changes shape following this rule. So they are very equivalent. So this was a nice application, and basically what I think we have done is merging quantum turbulence with statistical atom optics. Atom optics we see today, even the experiments of Tino is a kind of atom optics, right, in the interference and everything. But this is, you getting the statistical involved in this, which is what they do with the speckle. There are many applications of speckle, of light beams, and well, hopefully, eventually, they'll be with matter wave beams. This is a three-dimensional one. So basically, we all know that lasers, back is for lasers what thermal gas is for conventional light. But now turbulent BEC in expansion is like also equivalent for the speckle of light field. But there is some interesting property of when you produce the turbulence. One of them is that the tail of the distribution goes from exponential to, goes from Gaussian to exponential. So as you know, we have the BEC, we always have a thermal cloud, even small, and when you observe in expansion, that's a Gaussian, which is the thermometry we do. Most of the time we get the temperature out of this fitting of the Gaussian profile. But when you develop turbulence, what happens is you go from Gaussian to exponential. And then, of course, this is, in the first observation, is a non-thermal state. So if it is a non-thermal state, it's like a far from equilibrium state. So it's a good sample to study equilibration. If we need to recover the thermal characteristic of it. And this is what we're going to do. But there are many other applications that I don't have time to explore now on the transition between going to a thermal gas for a non-thermal system. And of course, you go from Gaussian. This is, you imagine that the distribution is exponential to the minus r squared, r to the gamma, and this alpha, sorry, and then alpha is 2 is a Gaussian, so it's a thermal system. And as you let the system evolve, or as you increase the excitation, there is a transition to an exponential type of behavior. And that depends, of course, in the fraction of your condensate. Very tiny condensate will not take place. It's very hard to do the turbulence in a very tiny condensate. And it's very hard to do also when you have a full condensate. Even though we never reached that regime, but simulation shows that you do need some dissipation there for everything to happen. This is, we're still exploring this transition. If you have a non-thermal kind of state, well, let's see how that evolves in time. So if we know, and this is evidence that we have a far from equilibrium quantum system, let's see how that evolves in time, because the idea is eventually this needs to reach thermalization again. And, well, the first thing we look for is if it is an evolution of a non-thermal state, maybe we're going to have non-thermal fixed points in this system, which is during the evolution, you produce the non-equilibrium system and let evolve. Whatever is the time of evolution, that made the system to lose the memory of the very beginning, many different things start to happen. And one of them they claim happens is you may find a region in a window of time where this shows a universal type of behavior. So even though it's not in equilibrium, but evolve in time following a well-established scaling law. Right, this is reminiscent of phase transitions and renormalization where you do the kind of thing, you readjust the scale, and then you can readjust the amplitude and you get the same system evolving. So the first thing we did is that exist in the turbulent cloud evolving? And when you do that, your momentum distribution, you should prove that your momentum distribution, even though it's not in equilibrium, is evolving time following a scaling law like this, where F is a universal curve. And so this is like belonging to a class of universality. And the class of universality is all characterized by alpha, beta, and the universal function. And alpha and beta for the system that we have closed is related by the dimension of the system. So we have done the experiment, and there is, of course, a window of time where all the momentum distribution can be fit into a universal plot by doing the scaling. And in our case, alpha and beta has those values. And the negative just means that you have a directly cascade. Things are flowing from low momentum to higher momentum, as expected in the evolution of a turbulent cloud. And then we have tested this and coming to comproving that exists. But then we want to see the recovery of the condensate or the destruction of the condensate. And to do that, Lucas was able to reformulate the way to look in this. Instead of fitting by a plot, by a universal curve, we can analyze through a differential equation. And if you parameterize all your variation through time, that is, the amplitude will vary relative to time with the exponent, with a coefficient, that is the alpha exponent, and the momentum will also scale with relative to time with another exponent. And then you can construct this equation. And what is interesting, the solution of this equation is what I showed to you, is a function that presents scalability and universality. But what is interesting here is that we can now make approximations. We can go to the region. You see, if you see there is a region of momentum that seems that not vary in time. So this is what we call minimum variation of time region. And then dn dt must be 0 there. And if you do that, you find that around that region, it has to have a power law type of distribution in the momentum. And this we have find that it is true. But more interesting is that I can go to the small k limit. So I throw away anything here. I just keep the other terms. And then I find that in the very small momentum limit, if it is a non-thermal fixed point, which we prove it is, it evolves with t to the alpha. So that gives me a chance, and we have proved this. I'm going to jump this. We compare with other papers in other systems that people are doing the detection of non-thermal fixed points, like in Cambridge or in Germany. And once we have done that, we can now focus ourselves in one class of momentum, which is the lower momentum. And then by looking the time evolution of the lower momentum class, we can find how the system is evolving. And this is what we have done here. So by looking the lower momentum class, we see that there is a period of time where there is evolution, the cascade is established, and then there is a region that's the non-thermal fixed point. And then there is a region of time where things doesn't evolve, seems to be almost like steady, which is more or less what you expect for the pre-thermalization region of equilibration of your system. And finally, a shoot up with the momentum 0, which is the reconstruction of the condensate. And then you go and find out that you actually have the condensate there. What's interesting is that when you shoot up, you have an inverse cascade. Now your system creates a mechanism to repopulate the lower momentum. And construct back the condensate. And that also obeys a kind of power law here in time. And some of our collaborators, Nazarenko, was able to even calculate the exponents of these shoots up in the momentum distribution, and even point out that the mechanism that's taking place for this thermalization is a four-wave mixing type of procedure. Okay, and of course, just to finish, we have done the opposite. If you put too much energy, at the end of the day, we're not going to revive the condensate. We're going to produce a thermal gas. And the thing is, where the system will discover, what will be its new personality. And then we have done an equivalent experiment, but now you have a collapse of the zero momentum class with reconstruct the thermal gas. And that's all depending on the amplitude. Big amplitude puts so much energy that at the end of the day, you are above the critical temperature. So you should end by having a thermal gas instead of the condensate. What is interesting is that all the steps are present independently of the system to revive the condensate or to shoot down and produce a thermal cloud. Cascade, non-thermal fixed points, pre-thermalization, and then the final thermalization of your system. We are doing many studies now, working with the different momentum class, because since there is no theory for this equilibration of quantum system, we may give hints about how different classes of momentum are moving around to be able to give ways to construct this. And then just to end, really, I'm going to show you a movie that there is one very nice peculiarity about studying turbulence in the quantum gas, is that in opposite to classical fluids, if you put the two vortices of high circulation together, spontaneously the system evolves to turbulence. So in quantum fluid, you have a chance to spontaneously generate turbulence, not in the classical fluid. And this is a very interesting peculiarity. Everybody asks, what's the difference between the quantum fluid and the classical fluid? Well, this is one. And there is all the stages of this spontaneous generation. Okay, well, in conclusion, we are trying to understand what stages a non-equilibrium quantum system takes to reach the thermalization and the reconstruction of the quantum statistic at the end. Thank you very much.
I have a question concerning the choice of bosons for exploring this turbulence phenomena. What about the possibility of using Fermi systems? In particular, we know that Fermi gas at unitarity is much closer in the behavior to liquid helium rather than a standard BEC.
Yeah,
and so the hydrodynamics is more easily achieved in the Fermi systems. And so a comment on this. I understand that bosons are easier experimentally.
I have many Bose condensates in the lab, but we are all bosons. But George Seman, that's from Mexico, is construct a fermion system to try to go to fermion system turbulence. And there are people in Brazil now also wants to go to fermion and to dipolar type of gas for studying similar things. It's a new world to explore, which is this time relaxation of this non-equilibrium. But you're right. I mean, you should go for a system that's even easier to understand and compare with existing data in helium. Wolfgang?
I wanted to ask you to comment on dimensionality, 2-dimension versus 3-dimension.
Okay.
you have, in two-dimension, of course, you have the experimental advantage that you don't do line-of-sight integration, but then you also lose some fundamental processes like reconnection and vortex rings. So could you comment on how much could you learn from 2 dimensions and how it connects to 3 dimension?
Yeah, in 2 dimension, many things will be easier. But, you know, we have to follow Onsager type of theory that then what's happened, vortices and anti-vortices, the way that the system will go to turbulence is in a different process. They will clusterize. So you're going to separate them and produce big structure. Is the opposite arrow of evolution in the 2D. But people in Australia, you know, Chris Helmerson and everything, they have done some work on this. But then I don't think they can explore very much the thermalization. I think on 3D we have. In 1D, I have done with Randy Hewlett another experiment, which is big oscillations of the interaction, the scattering length in lithium-7. And then we see, but of course, you're not going to see vorts or anything, but you see the evolution of granulation. You see the things going, Faraday waves appearing, and suddenly that breaks into domains, which is equivalent. And it will take, but takes too long to recover. You know, we wait for about 6 seconds, and there was no re-establishment of the condensate. Here I do everything in a second, so it is time enough, because in 10 seconds, you know, in those experiments, many other things start to take place, as you know.
Okay, so thank you very much.
Thank you.
Thank you. So last talk of this afternoon will be given by Peter Zoller, and the title is From Observation of Stream Breaking to Bounded Error Quantum Simulation.
Okay, Peter.
No, this is the manual. Okay. So I want to thank the organizers very much for inviting me here. Alain just left before. He asked me when he went out, you know, you have a title on string breaking. Does it mean that you've become now a string theorist? It sounded very concerned, but I will talk about string breaking now in the following as one of the topics. So we have now 100 years of quantum mechanics, and we're also celebrating 30 years of quantum information. So based on that, I sort of felt that maybe I should start out my talk with a few historical comments in this context and then connect it to things that we are doing at the moment. 30 years of quantum information also means that we are now celebrating basically the connection between AMO physics, you know, quantum optics, atomic physics, and quantum information. And so in this sense, I will say a few words about history, but then move on to sort of recent stuff that we have done, in particular the work done together with Misha Lukin and his company, Quera, you know, on string breaking, which will come out in a few weeks from now. And also, you know, talk a little bit about ongoing work that we have on what we call bounded error quantum simulation via Hamiltonian and Limpladian learning. This is the attempt to, you know, construct quantum simulator or run them in a way that they produce not only mean values of observables, but also corresponding error bars. So this is, you know, making bounded errors, and this is some unpublished work over here. So let me start out with a sort of historical part. You know, it's now 30 years ago that we have quantum information, and I put sort of the 0 point in this context to the Shor algorithm. That was invented in 1994, but immediately after that, you know, was also error correction. And what Shor has shown, and this is what I would like to call the, you know, birth date of quantum information, is that first of all, quantum computers solve problems that are classically hard, you know, in the problem even outside of physics. And second, that we have, for example, quantum error correction, which allows us to do quantum computing with imperfect component. And of course, this triggered at the same time that also that, you know, atomic physics got interested in this thing. And my own history in this context is that Ignacio Cirac was a postdoc in my group at that point in Boulder in Colorado. And we thought about trapped ion quantum computing in this context. And, but of course, there were many things afterwards that were sort of related very much to AMO ideas, AMO platforms becoming then platforms for quantum computing, like the Rydberg work and also photonic quantum computing. And I always like to include the superconducting quantum computers over here, because there's also circuit QED. I mean, they have artificial atoms, and we have real atoms, and we have a benefit from that, I guess. But I would say in spirit, these things are, sort of very close. And the question at that point was, how to build a quantum computer. And it's sort of interesting that these early ideas and proposals, they survive basically until right now, today, which is now almost 30 years later, and are still, I guess, candidates for doing some of these things not only well, but also actually leading candidates in this context. So if I go to this history, I think that the community, really should thank Arthur Eckert as the ambassador for quantum information. It was at this conference, the ICAP-14 in Boulder in 1994 that Arthur was invited. And I think it was actually Dan Kleppner who was the one who suggested that he should speak. There was always the idea at the ICAM that people that are a little bit outside the community would actually come and give talks that are stimulating for the AMO context. And he talked about quantum computation here. And the kind of things that he introduced was, we never had heard about qubits or quantum gates and readout and all of that, quantum registers and controlling entanglement. Well, we had heard about it, but not in this some very general form that we have it over here. And this sort of taught the community what kind of things they have to do. And Ignacio and myself were sitting in the audience of this talk, and we were just at that point working on linear ion traps, where you have ions or charged particles, they repel each other. They form some Wigner crystals over here. You can laser cool them down to very low temperatures. And it was sort of playing with some, you might call it cavity QED, not with photons, but with phonons. And then at that point, all of these things got a deeper meaning, because we sort of realized that the model that we were playing with, based on the work by actually Dave Wineland, who built atomic clocks, was really that allowed us to implement these things. But let me at that point sort of go a little bit back in history and ask the question why the AMO community in general was sort of ready for quantum computing. And it had to do with the fact that a lot of work in AMO physics has to do with quantum metrology. And it was the time, very early time, when people started to think about entangled atomic clocks. And entangled atomic clocks and quantum computing, they share a lot in common. And this was sort of the overlap between the two developments. And in sort of thinking about AMO systems and using them for quantum computing, this is really what sort of brought the corresponding synergy. So when people like, for example, Dave Wineland, with ions, and Jun Ye with an optical lattice clock, thought about quantum metrology in the sense of constructing an atomic optical clock here, you think about Ram's interferometry. And when you do Ram's interferometry, you take a two-level atom, bring it in superposition, and you print the phase that you would like to read. And then you see this in the interference fringes, that has applications not only in atomic clocks, also magnetometry, and we just heard to talk about all of that. When you take uncorrelated atoms, you have the so-called standard quantum limit. And Dave Wineland had a string of ions there, essentially with the idea, but only very few of them, to sort of build with that an atomic clock. And since there was only very few ions, he thought about improving the signal-to-noise ratio by making these atoms entangled. And this led at the end, then in larger systems to these optical lattice clocks. And Dave Wineland, brought up this idea here of, for example, squeezing, on the Bloch sphere, our spin distribution over here. And you can see very obviously that you actually reduce the noise by having this distribution squeezed while you imprint the corresponding phase. This, of course, led at that point, to this entanglement of atoms discussion like spin squeezing and so on, GHD states. And the question was how to do that. And of course, there was a long way in going there. It was sort of historically going from Paul traps, to single ions to laser cooling. And then here was the trapped ion quantum computer. And it always had to do with the fact that you wanted in your quantum systems more and more control, exactly what you also want to do when you're doing quantum computing. So if I take a single ion, there's a harmonic oscillator, that's for the external motion. There's the internal degree of freedom. And first, one learned how to do sideband cooling, basically to the motional ground state down here, which is also some prerequisite if you want to do quantum computing. Then, of course, came all of these sort of maybe more foundational discussions about the existence of quantum jumps in single systems, that you observe. This was brought up by Demel, Doschek, and also again Wineland. There were these experiments where you had a metastable state up here, representing in today's language now actually a qubit, and then you could make a detection over here and sort of do a continuous observation of single atoms here in this context. On the theory side, this of course triggered that there was some work on quantum noise, and together with Crispin Gardner, we have thought about some of these things, and we wrote papers about these quantum jumps, the whole community. And so at the end, then it was quite obvious that you could put all of these things together, including now a general mechanism for entanglement in these trapped ion computing ideas, that we got a string of ions over here with internal states. We can manipulate individually them with a laser. And you take, for example, again, this kind of a Demel 3-level system. You take an, for example, optical transition over here in this context, which would be an optical qubit, and then you can read these things out using the techniques of quantum jumps. And so we had to do gates, qubits, single qubits, 2-qubit gates, and all of that, think about decoherence. And it's sort of interesting if one goes through these original papers over here, that we have here 2 states that we identify here as the qubits. These are exactly the optical clock states that people might use in this context. Then we have this independent manipulation of these ions over here that, of course, can be done by the laser addressing, because the distance between these ions is maybe, 3 or maybe 10 micrometers or something of this order of magnitude. And then, of course, we have here, all these gates that could be done, like the one in the 2-qubit that uses the Coulomb interaction as kind of the data bus, phonon data bus between these ions that we have over here. And finally, the readout, just mentioned quantum jumps that I mentioned earlier already. So you can see that atomic physics, you can take these ideas and implement them basically over a very broad range of different platforms. And so this is rather generic. And the reason why atomic physics knows how to do these things well has very much to do with the fact that atomic physics is good in quantum metrology. And quantum metrology is sort of, I would say, the mother of all of these things which is being done here. So AMO had an advantage in starting, to think about quantum computing. So today, when you go to a web page like the one of Quantinuum, you can see the fidelities for these gates that we talk about over here. They have a lot of 9s, and this is exactly what you would like to see. And of course, there's now several model systems around where people are building these kind of machines. And so it took now, I guess, 25 years or 30 years to build these things. But of course, you can also do that in 2D. And I've stolen here a slide from Misha Lukin, I guess, who will talk about some of these things here tomorrow, about the future of all of that we have, of course, now different platforms in this context over here, where the big challenge is always the controllability, when we scale up to a very large number of particles, while we fight also decoherence. And again, the sort of cite here, Misha, in this context, that the current frontier is maybe on the order of about 1,000 of these qubits over here, and finding and testing useful algorithms and applications, and also doing the error correction that I guess he will talk about now actually tomorrow, and then to do fault-tolerant quantum computing here. So I should talk here about Rydberg states, but Misha will do that tomorrow. And I just want to mention that, in these early days, in collaborative work with Misha Lukin, we came up with proposals how to do also for neutral atoms. There was no mention yet of optical tweezers that we have right now. But if you take an optical lattice, you can excite atoms to Rydberg states and make them interact. We came up with these ideas. Underlying this is a so-called dipole blockade mechanism over here. And today, of course, this is the heart of these quantum computing ideas. So let me switch over now to the part that I actually really would like to speak about, which is now a quantum simulation part. So when we talk about quantum computing, we have in mind, of course, a universal quantum processor where we can program single 2-qubit gates and all of that. In quantum simulation, what we rather want to do is solve a quantum many problem, and this is sort of like, programming on a special purpose quantum computer, you might say,
and you can do this in an analog or also in a digital way. Essentially, what it comes down to in analog simulation is that you have some maybe material in mind. You know, this could be a condensed matter system over here, could also be a molecule or whatever. And you write down a corresponding Hamiltonian, and you find it advantageous to sort of solve for this problem, either in time dynamics, equilibrium, or non-equilibrium, instead of doing it classically by either building, for example, say with optical lattices and a certain analog model. You know, the number of Hamiltonians that you can realize there, of course, will be restricted. Or you can just take, you know, a quantum computer per se, digitally program it as a sequence of trotter steps, or then sort of combine these kind of ideas and then do analog and variational quantum simulation is sort of one example along these lines. So the reason, of course, why we want to do that is always that we have in mind that at the end there should also be some advantage in doing these things. So what these systems can do is, of course, you know, represent entanglement on a very large scale, and this sort of, we believe, gives at the end the advantage to these systems. Again, historically, this is connected, of course, very much in going to lower and lower temperature. This is, again, this quantum metrology effort where we have now weakly interacting quantum gases. There was a BEC and then also the Fermi gases. And, of course, you can think about atoms and optical lattices here. Much like this morning already mentioned, you know, this BEC mod insulator transition that was sort of, you know, I guess a starting point on the experimental side of thinking about analog quantum simulation. But what I would like to do here today is to talk about systems that I've sort of close experimental relation to, which on one hand is the ions, you know, as quantum simulators, and on the other hand also the Rydberg tweezer arrays of the work on these, for example, lattice gauge theories that I mentioned earlier. So I would like to focus in the following talk on some of that, and I have here one slide that, you know, outlines what the underlying Hamiltonians are in this context here, and what we would like to do with these systems, you know, when we collaborate with our experimental friends. So in trapped ions, here's a 1D string, but in the meantime, this is also for 2 dimensions, for example, you know. Luming-Duan has now 2-dimensional crystals with 1,000 qubits like that. If you can control them all is an interesting question. And when you take a system like that, you can see here that we have ions representing a spin 1/2 or a qubit sitting in this Wigner crystal that will oscillate. And if you got somehow, you know, and if you shine lasers on these things, like over here, and you might have even single side control, for example, that you also need for the readout, here, then you will have a situation where you can eliminate this phonon mode here adiabatically, and at the end write down a model for the spin by itself, which is just an Ising model. And the interesting part is that this is an Ising model with long-range interaction and also having a transverse field, which can be controlled by the laser parameters. Similar on the Rydberg side, you know, you have here an excitation from a ground state to a highly excited Rydberg state, at which point these atoms start to interact with each other according to a van der Waals force over here, and there will be a corresponding detuning. And these systems now exist in the lab, not only in 1 dimension, but also in higher dimensions. And in the following, I would like to tell you a little bit about, you know, playing with these systems as a theorist. You know, 25 years ago, we thought about some of these systems in the context of, you know, proposals, but now, of course, they exist in the lab. And so when we had, you know, ideas now what we would like to do there, very often we just go to our experimental friends and we are able to do experiments sort of directly, you know, based on the systems that we have here. So based on that, let me switch over to the part of my talk, which is now telling you about sort of ongoing research here. I should mention, first of all, that we did a lot of work during the last few years on learning how to measure entanglement. So, you know, when you want to measure entanglement, very often you have to measure, for example, density matrices, like, I don't know, a Rayleigh entropy, or you want to measure something like a von Neumann entropy. And we developed protocols, you know, that can be implemented in these experiments here, that by readout and post-processing of corresponding data, you know, these protocols at the end allow you to, for example, measure entanglement entropies over here, or even an entanglement spectrum. You know, we did, for example, an entanglement Hamiltonian tomography, you know, in some cases where we prepared an approximate ground state in the system on this quantum simulator corresponding to a Heisenberg model. And then we did, you know, an entanglement Hamiltonian tomography that allowed us to find, for example, Bissignano-Wichmann type behavior, for ground states. And if you go to highly excited state, it would look like thermal states, sort of in relation to the eigenstate thermalization hypothesis and all of that. And underlying this discussion of physics that became then at that point experiment was ideas like randomized measurement toolbox. John Breskill called these things classical shadows. We had sort of parallel developments over here. We were focusing on Waney entropies, and he was more interested in these things from a sort of general quantum information perspective. And we also applied this to variational quantum simulation. So I just want to say there's a whole toolbox out there that we developed over all these years in close relation to experiment that allowed us to make these things accessible, okay? So what we would like to do now, given this toolbox, ask the question if we can do some other interesting new stuff. And I had the opportunity of visiting Misha Lukin now 2 years ago, and 2 of my postdocs came along. They were working on lattice gauge theory, and then this was the starting point of this experiment, at the company, Quera here, that actually builds, analog machines, analog simulators in the way that I explained now earlier, based on these Rydbergs with 256 qubits, which can be run as a 2D analog quantum simulator. And one of the questions that we had, or one of the ideas that came up, is this: if you can study the phenomenon of string breaking on this 2D, 2+1 dimensional Rydberg quantum simulator, in the sense of both equilibrium but also non-equilibrium dynamics. And I would like to tell you a little bit about this work that will now be published very soon. And as I mentioned also before, I then want to speak briefly about this bounded error quantum simulation that is, I think, very important. Maciek wrote a review some time ago, Can We Trust Quantum Simulators? And we would like to find here quantum simulators that, as I mentioned before, not only compute expectation values, but also error bars. So it becomes a quantitative computational tool and can be developed in our systems along these lines. And we have some first ideas or results along that. So that's really ongoing research. So these are the papers I would like to refer to. This is the paper with Quera and Harvard and Innsbruck Theory. Daniel Gonzalez was the main theory postdoc, and also Thorsten from Innsbruck. And most of the group here, except Misha, who is from Harvard, is really from the company Quera. And we had a very productive collaboration over all these years, and it took a long time to get these things running. What sort of stimulated the final kick in the whole thing was the fact that Misha told us that Google was just ready to put their own string breaking results on the archive, also submitted to some prominent journal called Visualizing Dynamics of Charges and Strings. They, of course, have a superconducting machine here. And they are not doing analog simulation like what we're doing down here, but rather they're doing a digital simulation in their experiment. So it's really kind of complementary what we do in this context over here. And then, of course, Maryland came along, and they had a 1D ion string that was also roughly submitted. And this then triggered actually a whole bunch of more papers. I think there were about 6 or 7 string-breaking papers done on the archive within a few months or so. So let me tell you a little bit about this experiment here, what the ideas are and where we are in all of that, in our understanding. And I think it's sort of interesting to see interesting physics here on these machines, really for the first time. But I think it is also a complement, for what the experimentalists are able to achieve now in the lab and building machines that really do what they're supposed to do, and this was not always true in the early days, at least, of quantum simulation and quantum computing. So what's the motivation for looking at, quantum simulation of lattice gauge theory? The answer, I guess, is very simple. At the end, it is high energy physics, even though we are very, very far away from being able to make a contribution with these machines that we have right now in this context. So we have here the phase diagram, for example, quantum chromodynamics as equilibrium. We have non-equilibrium phenomena. And when you ask here, of course, what quantum computers might be able to contribute, then it's really based on the computational sign problem. Matthias Theuer wrote a paper some time ago about this thing being then computationally hard. So would be real-time dynamics and maybe also finite baryon density over here. But of course, where we really come from is much more kind of a condensed matter perspective, where we talk about topological order and all of that, and lattice gauge theories in this context. So I'm saying that lattice gauge theories are, I think, highly interesting and relevant. But of course, we are very far away in making contributions along these lines that we have over here. But I guess it's getting kind of interesting. So let me briefly summarize this, challenges of doing quantum simulation of lattice gauge theories. So a prototypical example is the one of quantum electrodynamics, and we're writing down here basically Kogut-Susskind kind of Hamiltonians, that live on some lattice over here. And you can see that we are writing here Hamiltonian, which in quantum electrodynamics would be an electric energy. There would be then a Plaquette term, which is magnetic energy. There would be an interaction term of matter, that sits on these different sites over here, interacting with the gauge fields, which sits on the link over here. And then there would be mass terms. These are the typical problems. And let me just tell you why this is so hard, but on the other hand, why this becomes kind of easy in the Rydberg context, based on ideas that actually Marcello Dal Monte had developed also here at ICTP. So the challenge in doing lattice gauge theories, from this perspective of quantum simulation, is that first of all, we have here Gauss law that needs to be implemented. Implementing constraints, local constraints, is sort of always difficult. In the early days, we thought about doing that, by, for example, punishing in the Hamiltonian certain configurations that basically implement the Gauss law over here. And of course, the second challenge is how to implement the Plaquette terms. And I have to tell you right away, the analog simulation afterwards, this term is essentially is not there, okay, yet. It's probably very hard to engineer. Then we have, of course, large local Hilbert spaces. If you would like to represent a magnetic, some electric or magnetic field sitting on these links, you need high dimensional spaces. So again, you take the most simple case now in the following, which will be just spin 1/2 systems. Then, of course, we have here coupling of fermions. We don't have fermions at the moment in the kind of things that we do because we only have spin models available. So you can see that we are pretty far away from realizing these things here sort of directly on the machines that I just talked about. But I think that we can do interesting problems and nonetheless look at the basic phenomenon per se, that illustrates the string breaking as a concept or as a phenomenon rather than, of course, to do really what one should do if one has some high energy ideas in mind. Of course, we never think about the continuum field theory limit because it's sort of too far away from us at the moment. So the idea, I think, in this context is always now to find certain phenomena that we believe to be very generic and very general and illustrate them in these sort of simple toy models that we can realize in our experiments over here. So explore the characteristic, lattice gauge theory phenomena on quantum simulators. And one of them is, of course, the so-called string breaking. And if you think about quantum electrodynamics and you think about having two classical charges, plus Q and a minus Q over here, there will be a field line or a flux tube then connecting the two. And of course, if I make the distance between them, their classical charges larger and larger and larger, of course, the electric field at the end, the E squared, the energy which is stored in here, will increase and increase and increase. But in a quantum field theory, what can happen if you have matter, that you can at one point, of course, break the string or the flux tube from over here because you are creating then antiparticles from the vacuum. So it is really the competition, of the electric field energy here, and then the corresponding creation of these particles from the vacuum. That is the phenomenon that we would like to see when we talk about string breaking. And this means, of course, that we are always in the confined phase sort of by construction over here. If you would like to see a confinement-deconfinement transition, you would have to do then, things like adding Plaquette terms and all of that, which at the moment, as you will see in a minute in the model, does not really exist. So these are experiments, that were sort of done along these lines with this kind of phenomenon here in mind. And again, what we want to do is to implement string breaking in this synthetic quantum matter with these Rydberg arrays that I just mentioned now before. So we had this Hamiltonian before. Let me write it again. We look at the 2D situation where we have atoms in these Trieste arrays that realize a certain spin model. These are Rabi frequencies, omegas, that excite atoms from ground to excited state. And this is a sigma X operator over here for the excitation. There's some detuning over here, and then we got some interaction. And the interaction here is the strong van der Waals interaction to Rydberg state, that, for example, has this property that if I take two atoms that are a certain distance apart, within what we call the blockade radius, which is defined over here, that it is impossible to excite two atoms at the same time because it becomes energetically not possible. And this is very much related to having like a Coulomb blockade in a quantum dot. Here it's called the dipole blockade, and this is one of these things that Misha and Veit discussed now 25 years ago in this context, and it's sort of now the working horse of all of these ideas over here. So this is the quantum simulator and what it does, and what we want to do now is this, and this is the idea that I heard first from Marcello actually, is that we have here the Gauss law that can be mapped on this blockade phenomenon that I just discussed about, And so blockade plays the role of the Gauss law. You get this sort of in this sense for free. And now you can try to rewrite this model in a form that makes now this analogy or similarity to a lattice gauge theory much more obvious. So we want to do now an analog 2D U1 quantum link model. A quantum link model refers to Uwe Jens Wiese, who basically said that the gauge field, sitting on the links, he wanted to replace these things by finite Hilbert spaces and spins, spin 1/2, for example, in our case, which is the absolute minimal model and really very much a toy model in the Rydberg array, and this is what we want. So the geometry, that was studied over here is that one has a honeycomb lattice, or should rather call it a Kagome lattice geometry. And you can see what's happening is this. Suppose that you start filling this atom here, from the left down here, in a certain way that I want to discuss now. If you take one of these atoms over here, say the one over here, then you can see that this blockade radius will have a certain range. And this is this circle over here. And you can tune, of course, this circle by either the Rabi frequency or maybe by the geometry of the lattice that you can always adjust. But of course, so this means that, within this radius over here, there will be complete blocking of the double excitation. If you move away from that, there will be this long tail from the van der Waals interaction that goes out here, so that there can be some excitation out here, but this is sort of a more perturbative kind of a small energy and not a complete blockade. So these rings over here plot the radius of the blockade, plus then sort of, when you move further and further out, you got some weaker interactions that you switch on between these atoms. How do you, so this amounts now to this lattice geometry. And what's sort of now interesting is the following. If I start, filling the lattice from down here, with a certain pattern, that respects this dipole blockade here, you're generating over the lattice here a certain state, which is now the reference state, or you might call it the vacuum in our context over here. And now, when you have, go to this, particular sites on the lattice over here, there is now a translation table, and this is the one that Marcello learned from first in the 1D context, but it also translates to the 2D context, that we have here these different atomic configurations here, for example, the upper one, and then also for the lower ones here, for the Rydbergs. So all of these occupation patterns can be translated into something that looks like charges and strings. So you have here, for example, no atom, the Rydberg state, and down this would be translated to having a charge over here, and then there would be a string here, and so on and so on. And if you do this kind of a translation table, then this hardware over here of our spin model gets translated into something which is now an effective Hamiltonian, which turns out to be the lattice gauge theory that we're interested in. Namely, you can see that the first part, which was now the excitation with the Rabi frequency to the Rydberg state, contains now terms like this A dagger and A. And we have now here a bosonic matter, which is like in a sense of a hardcore boson jumping between the lattice side. This is now fermions. It's just that hardcore bosons. And in between, you got, according to the link model that I discussed now, operators S plus and S minus. These are spin operators. And this, therefore, is sort of the matter-gauge interaction if you reinterpret this first term for the laser excitation of the system in this particular form. Similar way, you got here a mass term, in the sense of a staggered fermions that we know well from simulation of lattice gauge theories. And you can see that it depends on the tunings delta. Of course, we can also change these two parameters here externally with our lasers. And finally, in the last line over here, we have something which is sort of a strange form but mimics an electric energy, because there will be, as I said before, the blockade, which is also part of this hardcore bosons that we have over here, but there will be long tails in the Rydberg interaction. It turns out that these long tails in the Rydberg interaction sort of mimic, in some sense, some very crude sense, an electric field energy. And now you can see that we have all of the ingredients here, matter-gauge interaction, mass, and then the electric energy down here. And then you can try to do some theoretical simulation for that, and you find indeed, that you can find ground states, depending on what parameter regime you are, that are either, connected by a string, according to this interpretation here, or that are sort of, showing this formation of mesons, you might call it, where we got these fixed charges that are just defects in our lattice. You just don't put an atom there at all. And then these things can form in this way. And this is sort of the theoretical expected DMRG-based calculation for the string breaking here. And if you plot the corresponding potential, you can see very nicely, this is a string tension over here, and then it gets flat over here because this is this particle, the particle-antiparticle equation that we have over here in this model. When we reinterpret, of course, that. So let me mention here that we have here then the experiment, Quera experiment. These are the possible string configurations that we have down here. You can see this is the broken string. All other ones are sort of strings that are not broken. And if you do a phase diagram, you have here the control parameters that are, for example, here the blockade radius that represents the string tension, and the mass, which is like the detuning over here. And then you find sort of, I don't want to call it a phase diagram, though these different regions where you have a string, the broken string, and I want to point out the work by Subir Sachdev and other work, also theory work at Harvard, that explored, not for the case of the string breaking, but otherwise, the different parameter regimes of the string breaking here. And now you can see that we have here strings here that this is sort of the string part and the broken part. These are these different regions in this phase diagram under quote. And if you go to this point over here, where you should have a string, when you do the corresponding experiment, indeed you find one of these configurations down here, when you do your quantum gas microscope or your observation, leading to this readout of these, these configurations are realized. Whereas in the way where you have a broken string, you only find that configuration number 1, where 0, which is the one over here, is actually experimentally realized, and the other ones are basically absent. So this shows here, in this particular case, that we have here, prepared ground states that show this phenomenon. And I can just say that for the excited state, something very similar for the quench dynamics. When you suddenly form a configuration and then you have a time evolution where you should see the string breaking, also these things can be studied. How much time do I have? 1 minute? 2 minutes? Okay. Let me just tell you about the basic ideas. Okay, here. So what we want to do is sort of address a very important problem in this quantum simulation context, which is, can we trust quantum simulator in the sense of doing bounded error quantum simulation and we do that via Hamiltonian and Lindbladian learning. And I can tell you these things sort of, with my hands in 2 minutes. Yeah? Basically, what it comes down to is the following: that if I give you a quantum simulator, making quantitative predictions about, quantum simulation amounts, you knowing the Hamiltonian, this is the Hamiltonian I would like to simulate, the quantum simulator should return a number for an expectation value that, for example, is quench dynamics, of the given Hamiltonian. So when you give this Hamiltonian to your experimental friends and they come back and say, I did it, of course, to zero order, you trust them, or, yeah, well, okay, or maybe not, okay. You ask, can you assign an error bar, to this measured Hamiltonian or to this measured expectation value on your quantum simulator, by sort of performing extra tests. And our approach to this whole thing, and this is what I mean by this thing here, is that we are first of all using, the quantum simulator as a black box where we learn the Hamiltonian. Hamiltonian learning is a way of doing quantum process tomography, and it can be done efficiently in the regime of quantum advantage, because typical Hamiltonians that we have in systems, they have maybe 2 body interactions, maybe 3, but definitely not 100 body interactions. This allows you to learn the quantum dynamics of your sort of experimental quantum system back using machine learning. but not only getting the Hamiltonian back, sort of in terms of quantum, in terms of machine learning, you also learn a corresponding error model, okay? And if you have an error model that you learned at the same time for that, you can ask, I mean, we know now the Hamiltonian purely experimentally based on the Hamiltonian plus an error model. How do we translate this thing then over into something, you know, where this error, knowing the error of the Hamiltonian that we now know based on measurement, sort of translates now into this uncertainty of the expectation value that we have, that we measure on our quantum machine, okay? And this is what we've implemented, and I just show you here very quickly 2 slides in this context. So one is over here that we can do Hamiltonian learning. This is for trapped ions. So this is this power law dependence that you saw. And so I can only tell you at the moment, believe me, that we can do that with very, very high precision, not only for 10 particles over here, but we also know how to do it for 50. And then we move on, okay? And then we have here error bounds, and actually Breskill derived some of these things and some of these papers in a completely different context. We can use that. But now we can do then second the following. We can take, you know, do Hamiltonian learning in quench dynamics over a certain time window over here. And now we know the Hamiltonian, including the error model, okay? And then we can do at that point, first of all, classical simulation, you know, with this error model to predict the future. And sort of, for example, certain observables out here. And these are these blue bands here, and the measured quantities of the real simulator are well with what we predicted based on doing the Hamiltonian learning in the first part over here. At that point, you're still using theoretical simulations that it must be able to do. But of course, we would like to do that in a regime also where we cannot do classical simulations, sort of go into this quantum advantage regime. And again, Breskill has derived bounds in the context that we can use. You can see that these bounds are now only experimental data, okay? But a quantum simulator tells you what the bound is. You can see the bounds are not very good because this is the simulated error that we sort of know. But we are sort of on the way of improving these bounds more and more. And depending on how you do your machine learning over here, we are sort of on the way, at least for not too long times over here, be able to make statements like, you know, this quantum simulator gives you a mean value, but also based on this Hamiltonian learning that we do, gives you the corresponding error power. So it becomes, in this sense, a self-verifying machine, if you want to. And, well, there would be more to say, but I guess I should stop over here. I wanted to include a part about your Hamiltonian learning also, but okay, I was hoping to put this at the end, but it doesn't help very much. So thank you very much.
Thank you. There is a question.
Peter, do you agree with this string breaking that you observed or is really analogous? It's really a strong coupling gauge-like theory.
That's right. Okay.
Yes.
Yep.
And what it seems to me what it really is a model for is the Schwinger effect. Schwinger. So what you're doing is taking first of all, it's totally abelian, and you're taking charges and creating a strong energetic electric field. When you pull them apart,
that's right.
At some point you're going to tunnel a la Schwinger to pull pairs of charges out of the vacuum and get 2 strings. It's exactly what happens in any dimension a la Schwinger, right?
Yeah. No, I think that I would agree with that. Yeah. Yeah.
So it's,
of course,
it's a
we are
long
not in
cry from
what it is
non-abelian weakly interacting theory.
I had an outlook slide over here where we are trying to do some of these things now also for a non-abelian. You know, we can do something like SU2 and so on. Maybe not analog, but in a digital way, and there's some things that can be done. But they're toy models, okay? So,
but you have to go to the weak coupling limit. So these strings, you know, there are many transitions that occur because of the plaquettes. Strings
here the plaquette term was missing because we didn't know how to do it, but it could be added maybe with some hybrid, whatever, simulation techniques.
Right.
So I guess this is the beginning.
Continuum limit, it dominates.
Yeah. We'll make you happy in 10 years. Okay.
I said that 10 years ago.
Well, but you look much more happy now than 10 years ago, you know.
Okay, more questions? So I have a question meanwhile. So in the last part, do you have to guess the noise model or you just learn it? I did not get
We are
this.
learning the noise model. Okay, so I mean, what you do in the Hamiltonian learning is that you prepare different initial states, and we take product states because you know how to prepare them with very high fidelity. And we're using randomized measurements at the end. And then we measure certain observables that you decide based on these randomized measurements, so these classical shadows, and we write then from the experiment a long list of constraints. And based on that, we're doing regression, a sort of a primitive form of machine learning that gives at the end, you know, both the Liouvillean, and we also get the noise out from the model, but at the same time also this Hamiltonian. And we do this systematically by, you know, in these experiments, they can do up to maybe 10 to the 6 or 2 million runs or something like that. Then the happiness increases exponentially among the graduate students. If you do that, then you got shot noise. And you can see when you do an error assessment, you know, in your machine learning, you can plot the error that you get over here as a function of the number of runs. And then there will be a part which is dominated by shot noise, and then you go to a plateau because the ansatz that you made for the Hamiltonian that you're trying to systematically improve tells you, okay, now you got systematics. And then you can reparameterize, you know, in this machine learning. And we have in a systematic way done these things, where at the end you learn a model where you know that you are shot noise limited, and this is then Gaussian noise, you know, in the sense of the central limit theorem. And this gives you then the error model, and this is the one that we then compare with the experiment. Okay, there would be many more things to be said here, but.
More questions? No? Okay, so thanks a lot, Peter.